Okay, hello everybody. It is a great pleasure for the organizers and myself to welcome you in L'Aquila, in this historical building, in order to celebrate Paolo and his important groundbreaking scientific work. We hope you will enjoy the talks and the activities we prepared for you. And dear Paolo, this is a small tentative to thank you. We know you are not a big fan of such events, and we want to thank you for letting us organize this meeting. We warmly thank the City of L'Aquila for supporting our event and the University of L'Aquila. We thank the administrative and technical colleagues contributing to the success of this event. We thank the speakers for agreeing to contribute, and we are delighted to welcome so many participants from Italy and abroad. We warmly welcome the online participants too. One thing for online participants, please do not hesitate to ask questions, activating your microphone during the conference. Now, some technical details. There is a Wi-Fi network here, and you can see the password. Okay, Marco will show you the password. Lunches are offered by the conference at the canteen of the Abruzzo region, which is 10 minutes walk from here, more or less. Please don't forget your badge and show it to the concierge at the entrance gate of the canteen. Also, if you need a toilet, there is one toilet here in this building, but there is other toilets are in Palazzo Camponeschi, which is the building right in front of this one. Take the first corridor on the left, and at the end you will find the toilets. There is another door, in the second door on the left. You go downstairs, one floor, and there are other toilets. Okay. One more thing, for the online participants too, pay attention because the program was modified a little. So check the web version of the booklet, and not the paper one. Okay, we wish you all a nice meeting. Please enjoy, and Marco Tolotti will be the chairman this afternoon. Marco, the floor is yours.
Okay, thank you, Ida. I would like to say 2 words on behalf of the organizing committee, this wonderful group. So Ida, Francesca, Elena, Marco Formentin, myself, and Pierre-Yves. It has been a very nice journey. So we started more or less 1 year ago to think about the conference. So we said, okay, we must do something for Paolo. I mean, it's definitely necessary. And so, we start chatting and meeting on Zoom, where, who, with whom, and so on and so forth. And then at some point we realized, okay, now we have to tell Paolo that we are organizing these things. Otherwise, I mean, at least to fix the agenda, I don't know. And so we decided to organize a fake scientific Zoom meeting. So Ida invited Paolo Michele invited Paolo for a meeting with Ida to discuss mathematics. Of course, Paolo was really happy and ready to do, complete availability, etc. And then when Paolo entered the Zoom room, there was the 6 of us waiting for him. And since we are very, 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 very perfidious, we made some screenshots of that meeting, okay? Paolo, so are you ready now? Okay, first screenshot. This is the first screenshot. Now you see Paolo, happiness. So Paolo was very happy to meet all of us on Zoom. And then after 2 seconds, he starts thinking, okay, what's going on here? Maybe there is a problem. And so second screenshot. And this is, let's say, perplexity, I don't know, anxiety, okay, so something strange was going on, but then we declared our purpose, and so we moved to complete terror. So really, it was, you can see in his eyes the panic, okay, so, and then eventually, okay, when you realize there is no way, and so, I mean, this was just a joke. I mean, we are used to all this face expression of Paolo, you know, especially on our talks when me or Ellen are presenting. So we are very, very comfortable with Paolo's expressions. Okay, no, we are really grateful for Paolo, our maestro, and so now we can start the scientific part of the meeting. Again, thank you all for coming, all the speakers and all the guests that are here. Thank you. Thank you. Okay. Now if I can... Okay, so we move to the scientific part, and we start by, by Rungaldir, Wolfgang. I think we are sharing the screen. Okay, just to say, I'm very happy to have Wolfgang as the first presenter of this meeting. By the way, I had the honor to write my laureate thesis with Wolfgang, and then to work together with Paolo, also for the papers related to the thesis, and for my PhD thesis, I worked together with Paolo and Wolfgang. So I'm really pleased to start this conference presenting you Wolfgang. I mean, there is no need to present Wolfgang, of course, but Wolfgang, please, you can come and have your presentation and give you the floor. Wolfgang is emeritus professor at Padova, as we all know, and Wolfgang is presenting this work on separation and estimation of and control in portfolio optimization problems under incomplete observation. So please, Wolfgang. Devi usare questo?
Hello, everybody. Hello, everybody. Thanks to the organizers for having given me the privilege to speak here and even be the first speaker. And concerning privileges, I had the privilege also of having Paolo as my thesis student for the Italian laureate thesis, but not only Paolo, but also Francesca. And at that time, I was working on approximations in stochastic filtering and also partly in control. And Paolo's thesis was on approximations in filtering, and Francesca's was related somehow to control. After the laureate thesis, I had not much to suggest to Paolo, except there was a lab from the National Research Council, at that time called LATSEB, Laboratorio Dinamica Sistemi Elettronica Biomedica. There were some good people there, not all really belonging to that lab, but affiliated to that lab. Among them was, for example, Michele Pavon, who is on the list here, and a few others. And they were going more in direction of physics. And I think it was there that Paolo sort of went, I'm not sure, but at least was attracted also by relations to physics or statistical mechanics. There was also a young fellow, Tom Taylor, if I remember correctly, who might have quite an influence on him. And then he moved to Rutgers, and among the couples whom I know, Paolo and Francesca were almost the only ones who were accepted both together in the same place, and if I'm right, also financial support. And of course, one may ask, how come? Of course, he's Paolo and she's Francesca. So, of course, they came together, and that was not so easy, I think. So anyway, I have not really followed much the activity of Paolo during that period. I only want to tell one thing. I once met, during the period that Paolo was at Rutgers, I met Yannis Karatsas. Probably most of you know Karatsas from Bucharest, Schäfer. And he was at Columbia, and he had taken a semester, I guess, off, or he was teaching a course at Rutgers. And he told me that he had this Paolo in the audience, and Paolo was watching at him and looking at him. I had the impression Paolo was checking whether he did everything right. Okay, after the graduation in Rutgers, he came back to Padua, and I was very fortunate that we could work together. We started supervising a thesis. This was an almost monstrous thesis with Lorenzo Meneghini. We had 2 papers out of that thesis. And then later with Marco Tolotti and directly also with Elena Sartori. And the good thing was that he had additional knowledge in statistical mechanics. And one of these first papers that had quite a bit of success, we used this duality between free energy and entropy, and we applied it to get a relationship between stochastic control and stochastic dynamical games. And then at that time, I started working in financial mathematics, and somehow Paolo also moved a little bit into the direction, and working in statistical mechanics was very useful, for example, to study contagion in credit risk. And we had a paper where also Elena participated, Marco Tolotti, of course. And so this interaction was very fruitful, and then, of course, Paolo left for Milan, and the interaction became less, but I'm very grateful for all the things that we could do together. I think I would have some other little anecdotes to tell, but maybe due to the time reason, I better move over to the more specific topic of my talk. So as you have seen, the title of the talk, there are 2 comments to make. First, this is the same title as I had at the conference in Bologna, this third Italian conference in probability statistics, but the contents that I'm going to talk about are not exactly the same. They are related, but they are not exactly the same. And the second thing is I chose this topic because, as you had seen, with Paolo, I was working in stochastic filtering at the beginning, and then also moving to finance. And so this concerns filtering, control, and finance. So this was a topic. It's not completely in line with the main topic of this conference, but roughly we are there. So this is, here let me just make this title a bit more precise. Namely, when we optimize with respect to a given criterion, a stochastic dynamical system of which the evolution depends on an unknown, unobserved quantity, one possibility, this is not the best one, but one possibility is to first estimate the unobserved quantities via filtering or whatever, and then optimize the system with the unobserved quantities simply replaced by their estimates. Now the question here arises, does this lead to full optimality? Many people do that and are not aware that this should not be done. And here I come to this Sebastian Leo, who is, what I'm talking about is related to work in progress with Sebastian Leo. He has various papers with Mark Davis. The last one, unfortunately, he had to do it by himself because Mark, unfortunately, had passed away relatively early. And there was one paper where I think that Mark had not checked that, where they did exactly this to first estimate and then optimize with the unobserved quantities replaced by the estimate. So I told Sébastien that maybe we should investigate this a little bit better. So here is my outline. I would like to start with some... più vicino? Così. With some introductory notions. Then, since I consider portfolio optimization in the context of risk-sensitive portfolio optimization, so I would spend a few words on that, and then move to incomplete observation of the factors that drive the quantities in the model, and then come to the main issue, but that's only short, unfortunately, it's work in progress, to possible separation properties. Now, just to set a little bit the stage, so suppose we have a generic stochastic control problem where one has one or more unobserved factor process X that affect the dynamics in the market. Sorry, here I mix control problem with market. Well, let's say affecting dynamics of the control problem, then it will be applied to the market. And observations, why, for the moment, not more precisely specified. So we speak about incomplete observation problem. Then the usual correct approach, this is our correct approach, you pass to the so-called separated problem, where instead of the unobserved process, one considers its conditional or filter distribution, namely distribution of X, given the filtration generated by the observation process. I use this notation here. This is, I call it the usual approach. There is, well, everybody knows that now big data and deep learning, Q-learning, reinforcement learning are hot topics. So also for stochastic control in partial observation, there's the tendency of deriving data-driven strategies. But this doesn't really invalidate the main problems that lie between relationship between estimation and optimization. The original process that is unobserved may be typically finite dimensional, but the filter being a distribution is generally infinite dimensional. There are some exceptions, like the linear Gaussian models, or Kalman filter model, where the conditional distribution is Gaussian, and so characterized by just mean and conditional variance in the classical Kalman filter, it can be pre-computed deterministically, or when we have finite state Markov process, where the filter is just a vector of the conditional state probabilities. But more generally, the filter distribution may be finitely parameterized or can be approximated by a finitely parameterized one. The classical case is extended Kalman filter, where the filter distribution is approximated by a Gaussian and therefore characterized by mean and variance. So now the question of the separation boils down to the question, can the full filter distribution, that is the main ingredient in the separated problem, be replaced by one or more synthetic values of the conditional distribution, in the extreme case by just the conditional mean? And if this is true, then it is as though one would replace the unobserved process just by the conditional mean. And then we may speak about strict separation, and we shall see that this is generally almost impossible, but we may look at weaker separation properties. Now, what I want to do here is for a stochastic control problem under incomplete information, arising this time, it's related to finance, from risk-sensitive portfolio optimization, and where the filter is finite dimensional or can be approximated by finite dimensional one. First, show the equivalence of what is the separated problem with the original one. As I said, one approach is this deriving the separated problem where the unobserved quantity is replaced by the conditional distribution. But is it so clear that the separated problem is equivalent to the original one? This is generally overlooked and taken for granted. So I would like to speak about that, and that will be maybe the main part of my presentation. And then once we have the separated problem and we are reasonably sure that is equivalent to the original one. So we would like to investigate which parameter or synthetic values of the filter are relevant for the solution of the separated problem and therefore also of the original incomplete information problem. Okay, so let me become more specific. So we start from my usual filter probability space on a finite horizon. In economics and finance, you look at finite horizon. We have a market with a certain number M of risky assets, and the prices, we assume them already discounted. We denote them STI, that would be the price at time t of the ith asset. And we assume a simple dynamics, geometric Brownian motion, so to say, where the drift here depends on this factor process X, vector process that is uncontrolled and possibly unobserved, and satisfies its own dynamics. Here I take for simplicity just a Gaussian diffusion process. And W is a global Wiener process, some components affecting only S, some affecting only X, some affecting both, so there may be some correlation. Now, in what one does in a market, one invests, and one invests according to a strategy, and typically one takes self-financing strategies, and a strategy is given by a vector of the same dimension as the number of risky assets. In fact, HDI denotes the proportion of the wealth invested in the ith asset. And of course, we have to take this adapted to the available information, which may be full information, may be partial information. And then if we look at the self-financing portfolio value process, there's a process, the value of the portfolio that we generate by investing. And the self-financing property means that the return on the process, so that means the increment, infinitesimal increment of the process over the process itself, is a linear combination with weights given by the proportions of wealth that are invested times the return on the individual assets. And if we work that out, remembering that the asset prices had this dynamics, so S, ds over S would be A the T sigma the W, we get these dynamics. Okay. Now, typically what one does is in, say, portfolio optimization, one looks at the expected value of a utility function applied to the terminal value of this wealth process. We look, however, at a risk sensitivity criterion where there's a risk sensitivity parameter, theta different from 0, and here I have split the criterion into two parts because then we will concentrate on this one. The complete risk sensitive criterion is -1 over the risk sensitive parameter, the logarithm of the expectation of the exponential of minus theta logarithm of V. So if there is no randomness, then it's just this theta logarithm and x go away, theta goes away, and the exponential of the logarithm is just Vt. Right? I do not want to spend too much time on that, so if theta is positive, this corresponds to a risk adverse investor. If theta is negative, it corresponds to a risk-prone investor. But one good thing of separating these two things, you see, maximizing or minimizing, this one is equivalent to, just you do the opposite because there's -1 over theta, but depends on the sign of theta also, of course. Maximizing or minimizing this quantity here, so the problem of maximization or minimization is the same here as here. But if you look at this one, this is just like taking the expectation of the terminal value of the portfolio raised to power minus theta. So this is the expectation of a power utility. So viewed in this way, modulo this factor in front and the logarithm, this is related to log utility maximization. There are many comments one could make. If you take this risk-sensitive criterion, it's just like if you take a development, you have the mean and then the variance, so it's sort of a mean variance approach also. And there are various reasons why one looks at such a criterion. And since we have this logarithm of Vt, remembering that the self-financing portfolio value follows these dynamics, by applying Ito formula, we can derive the dynamics of the logarithm of V. So this comes just in, the Ito term comes in here. So now let's then plug this logarithm of Vt in here and see what comes out. So we get this one. So we have this one. And you may notice that what I wrote down here is not exactly this part here. Here you have just minus 1/2 H transpose sigma, sigma transpose H. And here I have minus 1 plus theta over 2. But since there's minus, minus, I add here, I have to subtract it. And there is a reason, you see. If you look at this, if you look at this, you recognize this is a Radon-Nikodym derivative. So if you consider as admissible strategies those for which the expectation of this is equal to 1, so you can pass from the original measure P to a transformed measure, I call it PH, so that you can concentrate the expression of the criterion as the initial value raised to the power minus theta, expectation under the transform measure of the exponential of what stands here, and shorthand notation is just this G. G is just this quantity here. And the pH is the measure that has this Radon-Nikodym derivative, right? And under this new measure, what is a Wiener process is the original one translated with this quantity here. Of course, this changes the dynamics of the other quantities. Now, the purpose here is to see what happens if we have not complete observation, and the object that has not complete, that we suppose is not completely observed, is this factor process. Factors are, I don't know, factors that drive the market, like inflation, occupation, and various things that are not always directly observable. But what we assume to be that can be observed are the log prices. So remembering that under the physical measure P, we had assumed that the prices would satisfy this quantity, this sort of geometric Brownian motion, passing to the logarithm, we get a diffusion process. So the only problem is here we have this ATXT. So this is not supposed to be a generic function of T and XT, provided this equation has a solution. Now, since we, as I said, we have X not observed and we observe Y, we want to estimate or filter X on the basis of Y. So this leads to this filter system. So these unobserved quantities, and these are the observations. And this leads to a filter distribution. So I just denote it by pi tx, assuming that this distribution exists. So if this coefficient would be linear in X, then we have the Kalman filter. And the filter distribution, as I said, just characterized by conditional mean and variance. And we shall require that the investment strategy is adapted, in this case, to the filtration generated by the observation. So we do not have full information also of X, so it has to be adapted to this filtration. Now, what to become workable here? We assume that, okay, we allow this A to be non-linear, but we assume that the corresponding filter problem, namely the one corresponding to this filter model, has a finitely parameterized filter. So the filter distribution is parameterized by this zeta sub t, which is a vector. In the linear case, this would just be the conditional mean and reduced to a scalar. Now we have to make an assumption about the dynamics of this factor process. We assume it to be of this kind. And the reason for this is that in the Kalman filter case, where this would be the conditional mean is just given by a dynamic of this kind. This, in the classical Kalman filter, would be just a deterministic time function. And now just a little bit of terminology. If we have a function that depends on t, on the unobserved x, and the observation y, we want to, I forgot to say, so now x is not observable, but we have, and y is observable, but now we consider as new observable the pair, the zeta, the parameters of the filter, and the observations. The observations are directly observable, and the parameter can be reconstructed from the observations. We can solve the filter problem, or we assume that we can solve it. So we we want to represent quantities that depend on x by quantities that depend just on z, because z we can access, x we cannot access. And then we take the integral of this function with respect to the filter distribution of x, which turns out to depend on t, on y, and on zeta. So this becomes something like that. In the linear case, this is simply the factor at, where we have this here. This is simply the factor a times the conditional mean. Now, what we would like to do is, here we have this at where xt is not observable. It would be nice to have here, instead of this one, this a tilde t of zt, right? So we would like to replace this, so to have a model where everything is accessible. Now we can do that. The only thing is then we have to change here something. We can change here, we have to change here. Now, everybody probably here in this audience knows Girsanov measure transformation. We change the drift and we get a new Wiener process, but under a new measure. But there is something we can stay on the same measure. There is what in filtering is called the innovations lemma, which says that given that we have this original process depending on the unobserved factor and we have this filtered process, there exists a Wiener process under the same measure. We do not have to change measure, but not on the full filtration, but on the subfiltration generated by the observations, such that this equality holds so true. So you see, we can move from this quantity to this quantity, provided we change from this Wiener to this Wiener. But we don't have to change measure. And to convince you that, in fact, it can be on the same measure, this same relation can be written as it's down here. Okay, so you just put this sigma, would have to take the inverse of sigma, but sigma may not be invertible, but full rank, then you can do it this way. And then you have this A is simply dy minus this one. And so you see that you can write it in this way. And what is here on the right, everything is adapted to the subfiltration, to observation filtration FDY. So with this lemma, you see, we can simply then go ahead and replace everywhere we have this expression, we can replace this expression. And so if we go back, okay, so you have what the dynamics that matter now are the dynamics of this process, this pair of processes. So y was a plus ax d dt sigma dw. Now we just replace this a with this a tilde and this w with this d double tilde. We do the same up here, this dw, now we plug in this expression, so just it becomes of this kind here. And now, if we recall that in the full observation case, we were interested in the logarithm of the terminal portfolio value, which had this expression. Maybe you remember, maybe not, but it had this expression. Now the same logarithm of Vt can be expressed by replacing this one with this one, which is accessible for the observations. Provided instead of this Wiener, we have this Wiener, but we are still under the measure P. Now, at this point, we can parallel the complete observation case. In the complete observation case, the criterion was, we have the risk-sensitive criterion, but the second part which matters. So this was the criterion. And now we can just write the logarithm of V. We can just consider this expression. So it's as it was before, under new measure. Now here we made a measure transformation. Remember, we went from the measure P to a measure PH, and now we go from a measure P to a measure PH tilde. And this G tilde is just the same as the original G, but with the ATX replaced by this quantity here. So sorry that I keep this a bit long, but I had to make these preliminaries. Now, this is the criterion for the observation, for the partial observation problem, where we consider now this Z as the process that is accessible. And we work on the filtration. And here is just this measure PH tilde was just the same kind as before, except that instead of from the Wiener W, we start from the The problem, all we need is just a filter mean and a filter variance. And we cannot replace X by the mean and the variance, but we can work with an expression where instead of 80x, we have something like this. But at least we do not need the entire filter. We can do away with just conditional mean and conditional variance. And if we would use the extended Kalman filter to solve the filtering problem, then we obtain conditional mean and variance. And the last situation that we have looked at, if we take this nonlinear function as the exponential of a factor times x, then provided it exists, this A tilde turns out to be the moment-generating function of the filter. Just integrate this with respect to filter distribution, so you get the moment-generating function of the filter. And if we would use the extended Kalman filter, which many people in practice do, now we have the centered Kalman filter, but I mean, extended Kalman filter is still one possibility to do it, then we get conditional mean and variance. And as long as one can accept the approximation by an extended Kalman filter, then for the solution of the separate problem, it suffices to consider just conditional mean and conditional variance. Of course, the problem remains then to solve the control problem. So this is all what I wanted to say. Unfortunately, I have no picture. I was looking hard to have a picture. All I can say, just happy birthday, Paolo. Okay, thank you for your attention.
Okay, thanks, Wolfgang. There are questions for Wolfgang in the audience? Ah, scusa. Tu hai una domanda, Paolo? Ah, bene.
Thank you. Thank you, Wolfgang. Thank you very much for everything, of course. I have a couple of questions concerning this seminar. First is, how can the equivalence of the separated problem fail? So I had the impression that the only way it can fail is that when you pass to the full observation version of the problem, you introduce some non-uniqueness. So is that correct? What I sort of understood. And the second question is also in the last part of your lecture, you had this expansion of the A function, the quadratic expansion, and so this is an approximation. In a sense, you are doing an approximation, and I imagine that in order to obtain an approximate finite-dimensional filter, you can use many other methods. And is there any hope of getting some, concrete and precise estimates on the errors when you do this kind of approximation? Grazie.
Well, the first question, thank you for that. You're quite right. There is a question of uniqueness here, and in fact, also the way we approach it. We base ourselves on the uniqueness of this modified Sakai equation. The intention of Nagai and Peng originally was that they would show that in the linear case, they get an explicit solution of the modified Sakai equation that depends only on the filter mean and variance. But we tried to go a little bit beyond that and see what can be said more in general. But in fact, it is the uniqueness of this modified Sakai equation, and in the end, as you say, it boils down to the uniqueness of the solution of separate problem somehow. We have not really too carefully looked into that, but there is the point, yeah. And the second question you asked, yeah. Of course, I mean, we had worked on approximation and things like that. No, we haven't really done that, right? And since for the filter, you would have to use anyway something where maybe, yeah, to get synthetic values, one way, the easiest way to do approximation extend the Kalman filter, because then you get just two parameters. So it's still work in progress, I must say. But to go beyond that, we have tried. So the issue is always the same. I had been working in approximation, and we did this. There is even a booklet with Lucas Tetner, where we do approximations in partial information stochastic control problems. So you solve the filter in an approximate way, and you solve the control problem in an approximate way. And then you have to show that if you replace the approximate filter in the approximate solution of the control problem, you still get a convergence approximation, right? And this is what one probably has to do here, right? Because you have to show that if the filter converges and you plug it in the control approximation, that doesn't really guarantee that you get this approximation. And in fact, it's not so trivial when you get some Lipschitzianity and things like that. Then if you plug in something, approximate filter, approximate control, then you get it. But we haven't really looked at that in more details. And it's already, it's a topic that many people do not look into very careful, but it's not for granted. I mean, the separation, you may be right. I mean, we just used this approach with the modified Zakkai equation because just to get a feeling that it's okay. But the separation, this is a bigger problem. Okay, thank you.
Thank you, Wolfgang. Other questions from the audience? No? Okay, so we thank Wolfgang again. Lo faccio io. Okay, so we move to the second presenter of this session, who is Gustavo Posta. Gustavo is presenting this work on mixing time and chaos propagation for balls into bins dynamics. So Gustavo, please. I give you the microphone.
Thank you. Okay, thank you everybody. I wish Paolo happy birthday for the future. But, and I want to greet all the organizers for the invitation and for the nice conference. I want to present some results about mixing time and ball into bins dynamics in the interacting particle jargon. I think that we can define this kind of dynamics like interacting particle system with parallel updates and conservation rule. All the results are with works with Nicoletta. And this kind of dynamics naturally appears in the context of algorithms for parallel computings. However, there are natural variation of popular dynamics like zero-range dynamics and so on. So, okay, this is what you find if you search on Wikipedia balls into bins. And it is a problem in computer science. Okay, typically the problem is this: there are n balls or users, and there are computers, which are the bins or the sites. Okay, the goal is to find simple strategies to assign computers to users. in such a way that the maximum load of each computer is reasonable. This is very sloppy, but this is the original problem. The original problem is when n it is equal to L, and it can be shown that, for example, if you independently assign the balls in the bins, you get with high probability log n maximum load. Okay, a variant of this problem is with parallel updates. Okay, this we call the balls, repeated balls into bin process, and there are again n balls and L bins, and at each time we take a ball from each non-empty bin, okay, and then reassign all together the bins. They have the balls, or the bins is almost the same. Again, in the case L equal to n, you can show that with high probability the maximum load is log n. Okay, this is the original context of this model, but we are not really interested in this. And also, we are interested also in models in which the balls are reassigned not independently and randomly, but with some law. Okay? Okay, so let me be more specific. Call with eta x the number of balls in the bin x, okay, and at time t, eta xt. Okay, so the state of the system at time t is t, eta t. Now, the dynamics is this, given that at time t we are in configuration eta, then we at time t plus 1, we made this transition. We remove a ball from each bin where is possible, and then we put some other balls, okay? There are restrictions, but the restriction is always that this is non-negative integers, okay? And also, this is the conservation rule. In this way, the number of balls is conserved, okay? The number of balls we removed, we put in, okay? Furthermore, to have Markovianity, we choose the B to be independent random vectors, okay? Here there is no X, these are vectors, okay? Okay, we call this process generalized repeated ball into bins, GRBB, okay? And some observation, this is a discrete time Markov chain, okay? The number of particles is preserved. In the case in which the update vector is Maxwell Boltzmann, as the Maxwell Boltzmann distribution with the correct number of balls, okay, of particles, then we recover the repeated ball, original repeated ball into bin process, okay? The observation is that with this parallel updating, the reversibility of the model is lost. In fact, for example, this transition in which we have a particle for each site, we move all the particles in the first site is allowed, but the reverse is not. Okay, you have to make L transition to destroy the tower. Okay, So it is not reversible. This typically means that its stationary measure is difficult to compute explicitly. Okay. The fact that the stationary distribution is typically unknown means that if you want to know something in the stationary regime, you need the Monte Carlo Markov chain techniques. Okay. But for the same reason, many of the usual techniques, for example, I don't know, functional inequalities or so on, are not viable in this case because you don't know the stationary distribution. Okay, we have some result on the mixing. So you need a good knowledge of the mixing time of this dynamics if you want to estimate the stationary distribution. Okay, we have some result in this direction. The first one is the Atoi model, the simpler. Okay, this is only to state what I mean with Fermi-Dirac statistics is the uniform distribution on the 0 and 1 such that there are n1, okay? Okay, allora, then in a first theorem with Nicoletta, we proved that if we start with a configuration with n lesser than the number of sites, because otherwise there are locked configurations, okay, then and we take B as the rule as the Fermi-Dirac statistics, then the Rbb process in this case is ergodic, its invariant measure is Fermi-Dirac, and in fact, mixing time can be bounded in this way. Okay, so this mixing time is the correct one asymptotically. Okay, L steps you need. Okay, because the first thing you understand, it is easy to understand that at least the mixing time is at least of order n, because you need n steps to destroy the n towers. And in the regime n of order L, okay, the previous bound is in fact of order of the correct order, and this is easy to prove. This I don't know. I am not going to do this, but the fact is that the first time you empty all the sites is a strong stationary time, not exactly the step after this. No, you remove, when you remove all, you then put all, and it is Fermi-Dirac, and so you reach the equilibrium. Okay, a more challenging example is the original repeat Rbb process, in which you reassign independently the balls. Okay, so you use the Maxwell Boltzmann distribution. Okay, again with Nicoletta, we proved that if we start with order L balls, okay, and you use Maxwell Boltzmann update rules, okay, then again you obtain an ergodic Markov chain with an unknown stationary distribution. It is not Maxwell Boltzmann, and we cannot say what is this, and then we have this bound on the mixing time starting from configuration eta. Okay, the mixing time can be bounded with the maximum load of the starting configuration. Okay. And this again gives us in this regime the correct bound, because it can be shown that you need order L steps to mix. Okay, and in this regime, if you are if you start with order L in this regime, then the mixing time is exactly what you expect, but the inequality is stronger because if you start with a maximum load that is lower, for example, for a flat configuration, then the time to reach the equilibrium is strictly lower than the mixing time. Okay, as I said, is not reversible, a stationary distribution is a no. The proof of this theorem is done using a version of the path coupling. Okay. Okay. I don't know. Okay. I'm not the chronometer, but I think that I am okay. Yes, I have time. Okay, another argument we studied is the propagation of chaos for this model, for these models, and okay, propagation of chaos is a science by itself, and so I don't want to introduce almost nothing. Okay, it has been introduced by Markov. This is what is written on every book of propagation of chaos. Roughly, very, very roughly is this. You have a system with a very large number of particles, but which interact very weakly. And you start by a weakly a weakly correlated initial state, then instead of study the world dynamics, you can look the world dynamics is a product dynamics in which every particle makes a nonlinear dynamic, which with a particular equation. Okay, this is very roughly. Okay. Now let us talk of the original Rbb process. Okay, so I reassign each particle. I remove the particle, one particle per site, and then I put together independently. Okay. And assume that I start from a chaotic configuration, so a configuration in which for L that goes to infinity becomes independent in some sense, okay? And a word of notation, here there is an L that goes to infinity, here there is no L, but this is only for to keep notation simple, okay? In reality, this is a PL, or eta is an eta L, but I don't write this, okay? And remember that this is the dynamics. it is a well-known fact that if in the correct scaling, the Maxwell Boltzmann distribution as L, the number of beans goes to infinity, goes to a product of Poisson distributions. Okay? And with mean, the correct one, okay, and also a product, so B1, BL becomes independent, okay. This suggests that in the limit in which we are interested, if eta 0 is chaotic, then this chaoticity is preserved. If because of the update rule, no? Because if at some time t this satisfies this, and these are almost independent, it seems reasonable that all becomes independent, and also that the evolution should be this, where n is a Poisson random variable with mean the probability of this step before. This is the nonlinearity in the setting of the discrete dynamics. Okay? And with Nicoletta, we proved this. Okay? This kind of results can be made more general and more strong by requiring something more on the dynamics and also on eta 0, on the distribution of this starting point. Okay, so we speak about now about general Rbb process. The update is not necessarily Maxwell Boltzmann. Okay, I need some notation. Two things. One is with calligraphic P, I denote the probability measures on the non-negative integers. Okay, and with pi L, I denote the empirical measure function. Okay, this map. Okay, I recall that the empirical measure is this. If I compute the empirical measure in the number k, I obtain the frequency of the number of sites in which the configuration eta puts k particles. This is the empirical measure function. And obviously, if the distribution of eta is symmetric, which is the standard assumption in chaos propagation, then the empirical measure is the only thing you need to know. Contains all the information to recover the distribution of eta. Okay. Okay. Again. Recall that the dynamics is this. No? For every site, this is what happens. And we made a further assumption that is that the update function B depends on eta only by means of the empirical measure. Okay, this is a homogeneity condition if you want to think to something, and the conservation of the number of particles becomes this, that the sum of Bx equals L times 1, because this is no, the number of particles I removed. I can write this. Okay. Now we want to prove for some of these dynamics a stronger and qualitative also convergence, stronger than weak convergence, stronger than convergence in distribution. And okay, so we need this chaotic condition. I call the key only for this seminar. Okay, no. There is nothing, it is not its real name. I don't know if there is a name. And okay, the first one is obviously that the update rule should be symmetric. The other one say that the distribution of the update rule is chaotic. Okay. And this is the one marginal of the chaotic distribution of B is strong because it is in total variation, and also there is a sup. Okay, and also we ask to the guy in this way. This is quite natural because. I will give you some example for which this happens, but this is a kind of equivalence of ensembles. This is the idea. Okay, a strong equivalence of ensembles. Okay, now that we have all these conditions, we have to say we have a Rbb process such that the condition holds. Okay, the condition especially gives us a mu bar, which is the distribution of the it is this one, no? of the update rule in the limit. Okay, the associated nonlinear process is a process on non-negative integer, such that which work in this way, take a Q, a probability measure, okay, on the integer. Let Q be the distribution of eta bar. Eta bar is the process I am constructing, okay, defining, and take B bar with distribution mu bar, okay. Now assume that at time t you are in the state eta bar, then at time t plus 1 you remove one particle if you can, and you put B bar particle, okay? This is what I will call in the next two slides associated nonlinear process to eta, for which key holds, okay? Okay, the theorem, again with Nicoletta, is this. Take a Rbb process, assume that condition key plus some technical condition holds. Take eta bar the associated nonlinear process, and assume that we start with a distribution for which this happens. Okay. Then this happens in a finite for a finite time. Okay. Again, this is the result we obtained. Okay. Okay. This is the first time you see this kind of things seems very different from the propagation of chaos we said before, but it's the same thing. It's not the same thing. This implies propagation of chaos. You can show that if this happens, effectively there is a convergence, also a weak convergence, weak in the sense of distribution convergence of the original Rbb process to an infinite volume, if you think, process in which every component evolves like the associated nonlinear process, and they evolve simultaneously and independently. Okay. But more, the theorem gives us some explicit bound of this convergence. The theorem needs the strong hypothesis on condition key. Quanto tempo ho ancora? 5 minuti? Ah, va bene, okay. So we see some cases for which the strong condition key holds. The first case is the trivial one, the case of Bernoulli. Okay, if you have Fermi-Dirac measure, Fermi-Dirac statistics, then you can show with L sites n particles, then is a simple computation you can write, okay, that this total variation norm is equal to this expression, so it is smaller than 1 over L. And this means the condition key holds in this case. This implies that if you make this Rbb process with the Fermi-Dirac reassignation rule, then you have a chaos propagation to a product of Bernoulli. But non-linear Bernoulli, in the sense that if you are in a time t in the state theta, then you remove one particle if you can, and you put a Bernoulli measure which mean the probability that at the previous step there was a particle. Okay, so because this is always equal to 0, it is the same thing that always put a Bernoulli measure on the probability that before there was a particle. This is what, but this is a toy model, okay? A more interesting case may be Maxwell Boltzmann, okay? For Maxwell Boltzmann, you can prove this. Okay, if you have Maxwell Boltzmann with n particles and L sites, then you can get this bound using coupling. Almost, I don't know if it is known. We made this computation as. The techniques is similar when you make this for one site, no? Because the Lecam theorem, I think it is called. Okay, the approximation of the binomial with Poisson in total variation. Well, you have to do a coupling to get this. Okay, and this implies again that. You have this key condition, and so in the original Rbb process, then you remove one particle and you put a Poisson random variable with parameter the probability that the day before there was at least one particle, okay. Finally, for Bose-Einstein. Bose-Einstein, for me, it is the uniform distribution on these vectors, okay? And for me, for this seminar, okay? Okay, again, using coupling, you can see coupling with polyaurns. This is quite intricate, but it comes, and you get this bound where these are geometric starting from 0, okay? Geometric distribution, because it is bound to Bose-Einstein, the geometric distribution. And again, what you obtain is that if you use the Bose-Einstein reassignation rule, so you don't put independently the particles in this case, you get this nonlinear process. So locally, if you look at with L large, N large system, locally you see that on one side you remove a particle and you put a geometric random variables with this mean. Okay, I didn't write, thank you for your attention. No, happy birthday, Paolo. When I wrote, I was not so smart. Okay. Okay.
Cosa devo fare? Thanks, Gustavo. Questions from the audience? No. Questions? No. Oh, yes.
Yes.
Question here.
David.
Maybe a naive question. May you have, so you were speaking about Bose-Einstein, may you have some condensation phenomena with dynamics like this? That you have a density of particle above a threshold, then you have
in this case, I think, no, there is no condensation. Because you are in a regime in which, you remove, it is not enough, I don't know, I think, because, let me think, No, I know that there is this problem of condensation for Bose-Einstein statistics, but...
I know it's not simple to answer.
Yes, but the condensation, I think that instead you see a geometric decay instead of a Poisson decay. This is the only difference. Because we don't force more particles. No? In this case, you have L sides, and so you remove L particles, and so the expected number of particles you put on each side is lesser than equal than 1. So I think this is not enough. There is not enough attraction. This is, but I really didn't think very deeply to this. I think this is not enough.
Thanks.
Question in the back.
Just curiosity. So here, if there is a particle, you remove one particle, right?
Yes.
But what happens if you put some probability? I mean, you remove one particle with probability 1 minus epsilon.
Maybe the same thing. Okay. You are talking about propagation of chaos or yes. Mixing time?
No, propagation of chaos, for example.
I don't know. If you remove particles, it is... Now, all these models are, the removing is always the same. You change the way you put.
Yes.
But if you gently remove a particles with probability 1/2, I don't think there is really a difference. But
Okay.
I really don't know.
Okay.
Okay, if you make something more strong with something for which you don't remove or remove all the particles, this change, but with 1/2, but I guess. I really don't know.
It was a curiosity. Thank you.
Thank you. Other questions? Yes. There.
I mean,
It's a little bit the same question as Davide. Did you, I mean, you did not talk about the max in your model. Is the max always of order log n? Or do you have models where the max can be larger, like n to a given power?
you are talking about the maximum in the configuration.
Yes.
No, yes, you can do this. No, but this depends the way you put the particles. If you put the particle with an attractive potential, you.
So do you have this? Did you do this? Did you choose let's say to favor big piles and things like that?
Yes, you can choose to favor. It is this is the particularity of this model are that the updates are parallel. This is the only special things respect to other interacting particle models. Okay, so if you put you make a denial in which you remove the particle and then you randomly choose one site and put all the particles on this site. This is allowed in this class of models, and this gives us you always
discretization that turns out to be a finite state mean-field game where we control Markov chains over a finite state space. The main result is to prove a convergence. The main novelty is to prove a convergence rate and to study the limit in terms of the master equation. We do this in two cases, both in case there is a solution to the classical solution to the master equation, and in case there is no such solution that I will explain. So start with the limiting dynamics. We have a mean-field game. For simplicity, the dynamics is on the one-dimensional torus over a finite horizon. There is in the limit one single particle that controls the drift and the volatility is uncontrolled. And in order to minimize this cost, there is a quadratic part from the control and a running cost and a terminal cost that depend on mu, that is a given flow of measures that represents basically the distribution of all the other players in the game. In the limit, this is deterministic. We have a solution of the mean-field game. Is a couple of strategy and the flow of measures such that the control is optimal given the fixed flow of measure, and plus we have the mean-field condition, like in mean-field models in statistical mechanics, but the law of the optimal process is equal to the mu given it is part of the solution. This notion of optimality corresponds in some sense to the Nash equilibrium for a finite player game. It is optimizing, giving fixed the behavior of the other players. This solution can be captured by a fixed point. So we first fix a flow of measure. We choose the optimal control. It is given by a Hamilton-Jacobi equation. Then we write the equation for the flow, the marginal flow, and we impose it is equal to the mu we started with. Which results in a system of PDEs, one backward Hamilton-Jacobi equation for the optimal value, and one forward Fokker-Planck for the consistency condition. It's forward-backward. the problem with this system is that since it's forward-backward, typically there is existence of solutions, but there's also a nice regularity. But uniqueness fails in general. It is true if the time horizon is small, because the fixed point becomes a contraction, or under this so-called Leslie-Lyon's monotonicity conditions, that says basically that players prefer to spread instead of aggregate. Under this condition, there is a uniqueness of solutions to the limit, to the mean field game. Importantly, this monotonicity implies also stability of the system. Now, the main tool to understand the mean field games is the so-called master equation. It is an equation in the space of measures whose mean field game system represents the system of characteristics, in the sense that we initialize the mean field game system from initial time and distribution, and we define solution of the master equation from this initial time and distribution as the value at the initial time of the backward equation. In other words, it's called a decoupling field in the theory of forward-backward system. This function, capital U, permits to write the backward equation as a forward equation as a function of the forward equation. So U solves an equation in the space of measure. To write the equation, we need a chain rule and a notion of derivatives in the space of measures. There is this notion of flat derivatives. The flat derivative is called delta over m, is a function of measure and an additional variable x. There is a neat formula for these derivatives, so immediately we can derive this master equation. We recognize the backward Hamilton-Jacobi part and the forward part, that is the integral of this is the generator of the optimal process applied to this flat derivative. In general, there is a uniqueness if we have a monotonicity, but uniqueness of the system permits to define a solution. To have a classical solution is called classical if all the derivatives that appear exist and are continuous. There is a general result in the theory. If the coefficients are monotone and smooth enough, then we have a classical solution. Existence of a classical solution implies uniqueness of the mean field game system, but typically this assumption is too strong, so there are other notions of weak solution that can be used. But to define a solution, we always need the uniqueness of the system, so it's required to have a monotonicity of the coefficients. To use these models, as I said, we need some numerical methods. So the first methods are based on finite difference for the system of PDEs. Then there are other methods also based on machine learning. And a method, recent, is a probabilistic method. It is basically the Markov chain approximation of Kushner for a stochastic control. In this work of Adikanlu and Silva, they discretize the problem. Then the advantage is that the discretized problem turns out to be itself a mean field game. And then they prove convergence by probabilistic methods. What we do in this work is to consider a space discretization for which the discretized model is a finite state but in continuous time. And also, we can view from a PDE point of view, the corresponding system is a finite difference scheme for the system, mean field game system of PDE. When we study convergence, the main novelty is that we provide a rate for the convergence. And also we study the convergence in terms of the master equations. So Here is the discretized model. We discretize the space, the torus, we discretize with a step 1 over n. We have a Markov chain in continuous time. Okay, but the peculiarity is that it can jump either right or left, and the player can choose the rate to go right or left. In this way, there is a quantity that will be the drift, and this additional quantity that gives the diffusion in the limit. So the transition rate, right or left, and the cost is the same as before, but is a quadratic part for the two controls, and the same running and terminal cost that depend on mu. Mu is here a fixed flow of measures with values in the simplex as n, because we have a finite state space, so measures are measures on the simplex. This form, finite measure, the solution is still a couple optimal controls and flow of measures, so that alpha is optimal for mu, and mu is the law of the optimal process. We define the usual finite difference of a function on the right and on the left, and the second order finite difference. We obtain the optimal controls by standard Hamilton-Jacobi theories given by this function, the negative part on the right and left first order derivatives. And u is the value function. X is here a point in this finite set. As before, we give the mean-field game system, that is a system for ODEs, a backward Hamilton-Jacobi, and a forward Fokker-Planck, but ODEs because time is continuous, but they are indexed by x. This is a point in this finite set. As before, we have existing a uniqueness under monotonicity assumptions. We can see that heuristically, this system is a finite difference scheme for the system of PDEs we saw before. So formally, if finite difference converges to derivatives, we can see that the UN converges to U and UN to mu solution of the mean-field game system in continuous state space. We can also study convergence in distribution of the optimal trajectories formally by means of the generators. This is the generators, the transition rate, the jumping on the right and jumping on the left. If derivatives, finite derivatives converge to derivatives, and in the limit, this should give the generator of the optimal trajectory, and minus the gradient is the optimal feedback, the optimal control. Formally, we can see the convergence also in terms of the master equation. This is not so important to write this formula. I just want to say, if we have this master equation for the finite state mean-field game, we have the usual derivatives on the simplex. And we can see formally that the derivatives on the simplex are given by this formula. Formally, if u is a function of a discrete measure, the usual derivative in Rn is equal to the flat derivative computed on that point. So the master equation that is given as before as the coupling field by the classical chain rule. Here, this difference converges to the derivative of the flat derivative in the limit. So formally, the limit u, if it exists, solves the limit master equation. So we ask how to make rigorous this argument. We want to study convergence of the master equation of the optimal trajectories. Since the system is forward-backward, we have to study this convergence together the master equation and the optimal trajectories. The main result, first result, assuming that the limit master equation has a classical solution, we can show convergence with a convergence rate of order 1 over n, and also this additional inequality that gives a convergence of the optimal trajectories. This inequality involves the difference that give the optimal control. There is this intermediate result also. And in the optimal trajectories, we study the convergence in the Wasserstein distance, convergence of order of this order, cube root of n. To prove this result, the main steps is first to show that U is almost solves the prelimit master equation with a reminder, and then to prove the convergence using a stability argument for forward-backward system in case that there exists a classical decoupling field. This is an old idea, the so-called four-step schema for forward-backward equations. This method was employed also in this book to prove convergence of the Nash equilibrium of the n-player game. This result strongly requires the non-degeneracy of the dynamics and also the quadraticity of the cost. And to prove the convergence of the optimal trajectory, we need this additional result. It is a diffusion approximation of a Markov chain. We can show with this result convergence in Wasserstein distance of order 1 over n to 1/3. The result, in case there is a smooth solution to the limit, in case there is no classical solution, we can still prove convergence. But in terms of the mean-field game system, it's a solution of the discrete mean-field game system, un and mu-n, we prove this result, but we get still convergence, but with a worse convergence rate, as we see. The proof relies on a variant of the stability of the mean-field game system given by the monotonicity. So to conclude, we show the convergence of a discretized mean-field game in terms of the master equation from discrete to continuous, but with continuous time. And we show a convergence rate both in case there is a classical solution and in case there is no such solution. This, in case without a common noise, we can also show in the paper a convergence of the master equation in case there is a common noise, but just a particular type of common noise introduced by Bertucci. It is a particular common noise that preserves monotonicity. In that case, the proof of convergence is different and relies on a notion of a monotone solution introduced by Bertucci and compactness arguments. So I conclude here, and happy birthday.
Thanks, Alekos. Questions from the audience? Questions? Paolo?
Thank you, Alekos. As you probably expect, my question is what happens if you relax the monotonicity condition? In particular, I have one curiosity, without monotonicity, of course. Is it possible that the discretized system has, for example, a unique solution of a mean-field equation, but the limiting system does not?
This, I don't know, but I don't think I didn't see examples of this because the basic structure is the same. I mean, it's still a forward-backward system. It's this problem that gives the non-uniqueness. But the convergence can still be proved, also in case there is no uniqueness, for sure without a convergence rate. The first result prove, in case there is a classical solution, we don't need the monotonicity to prove the convergence. We don't need the existence of a classical solution to the limit. If there are other conditions, there are examples of other conditions that gives this result, we can still prove the theorem, and we don't need the monotonicity in this case. Without uniqueness in the limit, we can still prove convergence by proving tightness and convergence along subsequence, and this was given in this paper by Adikan, Lu, and Silva. This also implies convergence along some sequence of optimal path and optimal control also. But it's not a master equation because it's not clear how to define a solution in this case if you don't have uniqueness of the characteristics.
Okay. Other questions? No? Do we have questions from online audience, maybe? No, it seems not. Okay, so we can close the first part of this afternoon, and we have a 20 minutes break now, right? 30 minutes, wow, a long break, very good. So we thank Alekos and all the speakers, and we are back in 20 minutes. Thank you. Second session of the conference. Paolo, you can take place. Otherwise, we cannot start if you're not around, of course. Of course. Okay, so Ida asked me to remind you that all the lunches are offered by the organizers. Okay. But so we will move to the Mensa della Regione. Ida knows where the Mensa is, so we can follow Ida and so for the lunch. And also the social dinner is of course is offered by the organization. So you're welcome to join, of course. Okay, now it's time to move to the science. And so the next presenter is Markus Fischer. So Markus presents a work on correlated equilibrium and mean field games. Markus, please. So you can sit down. I think that everything is fine also in the connection.
Yeah, thank you, Marco, and thanks to all the organizers for the opportunity to give this talk here. And thank you to Paolo for the opportunity, not just because at some point you will turn 60, but also more than 10 years ago, you gave me the opportunity to work in Padua when you were still there, to also to be one of your collaborators, to join the probability group, and that was really a wonderful experience. I'm grateful for. Yeah, thank you. Okay, so this talk is on correlated equilibria and mean field games. It's a joint work with Ophelia Bonicini, who's a PhD student in Padua, and Luciano Campi, who's now in Milano at Milano Statale. I'm not sure. Okay, scusa, sì. Okay, yeah. Okay, yeah, we've already seen a talk on mean field games by Alekos, just to recall they arise as limit systems for n-player games, for symmetric n-player games, non-zero sum, non-cooperative, with mean field interaction, like in statistical mechanics. And the limit as n, the number of players, tends to infinity. In fact, the passage to the limit is, at least at a heuristic level, analogous to the Mekin-Blasov limit for weakly interacting particle systems. And here the notion of, well, I should maybe not optimality, but the notion of solution you use in the n-player, so in the pre-limit, in the n-player games, it's usually that of Nash equilibrium. So in a sense, you take limits of n-player Nash equilibrium. So the original motivation, at least for the mathematicians, that was this question by Pierre-Louis Lyons: where do I put my towel on the beach? I hope you can somehow see these are umbrellas and towels. And of course, the answer, and we are in the pre-limit situation, of course, in the end player situation. The answer, the players are, here it's reasonable to assume that they are actually indistinguishable, like in the n particle setting. You see the answer, of course, depends on players' preferences, so on their position. So all players, they like to be on the sand, but it should be dry sand, so they don't like the rocks here, they like the sand, but they don't like the wet sand. These are children, their parents put an umbrella there. So this is, and of course it also depends on what the other people do. So the interaction, and here the preference is to spread out, so to avoid other towels by other people. But of course you can also have a different situation like this. It's a lake close to Berlin, some time ago, where people tend to flock, to concentrate. So they do not want to avoid other people. And from a mathematical point of view, you have an important distinction. In this first case, you can expect to have a unique solution, so a unique mean field game solution when you pass to the limit. While in this second case, you will expect multiple solutions because the population will concentrate, but where they concentrate, that might move. So I know that also Paulo studied this problem. I'm not sure about his original motivation, but the problem of mean field games with multiple solutions. So the connection between these mean field games and the end player games, to make that connection rigorous, you have two directions. You can, the first one already proposed by the engineering group who introduced these mean field games. You can use a solution to the limit model, to the mean field game, to construct approximate Nash equilibria, or you can go the other way around. It's a bit more difficult, where you try to study the convergence of solutions, so of Nash n-player Nash equilibria to solutions of the mean field game. Here you see this work also Alekos mentioned. Here's a work with Alekos and Paulo da Pra, where we look at a very particular toy model, a toy beach where you only have two places where to go, but where you have multiple solutions. So in this work, you have a unique mean field game solution where you have multiple solutions. So the crucial in both directions is this choice of admissible strategies for the definition of n-player Nash equilibria. So you can choose stochastic open loop strategies, so you simply look at time and noise. That's convenient from a mathematical point of view, but maybe not so convincing from a practical point of view. Or you can choose feedback strategies, and then you choose the information you give your players. Little information means they just look at time and their own state, like these restricted or Markov open loop strategies, or they look at the entire current system state, so they have access to the state of the whole system, or you can even include, like progressive closed loop, you include the entire past of the evolution. So here what we want to do is we want to substitute the notion of Nash equilibrium by another notion that's famous in game theory that was introduced by Robert Aumann in the 70s. It's a notion that allows to introduce correlation between player strategies without cooperation. And the idea is that you have a mediator or correlation device. Actually, it's a mechanical thing. That sends before the game starts, this mediator sends a private signal as a recommendation, a recommended strategy to each of the players. And this signal is, this recommendation, this strategy recommendation is sampled from a known joint distribution on strategies. The distribution is known to all players, but the actual recommendations, they are not known. They are private, so each player receives his own recommendation. And it is, the players are free to accept the recommendation or to play something else. And you have a correlated equilibrium when all players will follow the mediator's recommendation. A prototypical example are traffic lights, where you arrive at the traffic lights. Imagine a complicated junction where you do not actually know the green lights of the other roads, but you know the mechanism of the junction, but you do not actually know because it depends on the time you arrive at. But you usually trust the mediator, so the traffic lights. Okay, so there's a huge literature on these correlated equilibria in game theory, mostly on discrete models. There are also some but few works on continuous time diffusion type models. There's in this work, just mentioned, there's a variant of the correlated equilibrium. It's called coarse correlated equilibrium, where players have to decide either they see the recommendation, the mediator's recommendation, then they have to accept this, or otherwise they ignore it and choose their own. And here you have a work where you have like a common signal. That's also an extreme case of a correlated equilibrium. So for mean field games, there's this work with Luciano Campi, and two recent preprints by group. There's also Mathieu Laurier among these people, and also people who work for Google Brain, I think. They look at the look at the discrete setting, as we will do, and they use a notion that turns out to be equivalent to us, but it's more convenient from a computational point of view. So here we will look at a very simple model. So dynamics are in discrete time over a finite horizon, and everything is finite. So the state space is finite, and the set of control actions is finite. Well, not everything, strategies, not necessarily. When we look at restricted strategies, then also the set of these Markov open loop strategies is finite. So we will only look at recommendations in restricted strategies. So the mediator will suggest a strategy that looks only at time and private state. But we will also allow for deviations that have access to the entire information. So we will see an example, a little bit of this beach type, but the second beach type, where people try to block an example with explicit non-trivial solutions and many solutions. I will give you the results for the two-way connection when also the deviator is forced to use restricted strategies, and the construction of approximate correlated equilibria from suitable solutions to the mean field game that are robust against progressive deviations. So in the n-player setup, now the indentation is heavy, a bit heavy, but so we have a time horizon t, and we look at a function psi that describes our dynamics that depends on time, state. And here we have the distributions on our state space. So this will be the empirical measure of the state. So this is where the interaction enters. The control action and the variable that corresponds to the noise. So we give this functional representation of our dynamics, and this gives us a new state. We have these two sets of strategies, restricted strategies that only look at time and state and choose an action, and progressive strategies that look at the entire past of the evolution of the state evolution of the whole system. Then the dynamics just look at this. Can you see this? Yeah, at this part. Here we have the n-player dynamics, so the evolution for the state of the player J, who follows the recommendation. So what we have to look at is now the situation. We model the recommendation by these variables phi n1, phi nn. These are the signals, so the strategies. The mediator suggests, recommends to the individual players. And then the typical situation is that all players but one player follow the mediator's recommendation. So they apply this random signal. It's a strategy, so they apply it in their dynamics. And then there's one player, the ith player here, who can modify the recommendation. So he chooses to deviate. He takes a function u that looks at the deviation, at the recommendation, calculates first this one. This gives a new strategy, a strategy that may depend on everything there is, so on the entire state evolution, and then applies that strategy. Okay. Now you can define corresponding n-player costs. So the cost for the ith player. This is the deviating player. There's, of course, one choice for this function u, one particular choice where you simply choose the identity. This means you accept the recommendation. And you have these running costs and terminal costs. Now you have a definition of correlated, epsilon correlated equilibrium, which is looks similar to the definition of Nash equilibrium. So you say that a correlated profile, so a distribution on strategy profiles. So the joint distribution this is the distribution the mediator uses, is an epsilon correlated equilibrium, either in restricted strategies, so where also deviations are in restricted strategies, or against at least progressive deviations. The recommendations are always these Markov open loop. If no player has an incentive to deviate. So this is like in Nash equilibrium. So if you calculate the costs for accepting the recommendation, all players accept the recommendation against the costs for the ith player, where the ith player chooses to modify the recommendation, then he or she cannot earn or save more than epsilon. Of course, when epsilon is 0, then we have a true correlated equilibrium. So when you, here, a particular case, when gamma, this distribution, is a Dirac distribution, so the recommendations are constant, then you are back with the classical Nash equilibrium in pure strategies. When these recommendations are not constant but independent, then you have a Nash equilibrium in mixed strategies. And what these correlated equilibria can do is they can have these recommendations that are not independent, so they are correlated, and so introduce correlations between strategies. We also have existence. Now we give an analogous definition at the mean field game level, or similar. So now at the mean field game, there's just one representative player, and while the action, the evolution of the other players is modeled by a flow, this mu. This flow corresponds to the limit of the empirical measures. So this mu is the state evolution of the other players. So you have the dynamics for this representative player. You have the state evolution, and you have here the recommendation, phi. Now to specify these dynamics, you have to start from a distribution. Now before we had this distribution on strategy profiles. Here we start from a distribution on the strategies for the one representative player and flows of measures, this row. And so you when you somehow want to implement this, then you take a representation phi and a flow of measures, and the evolution is given by this the recursion. You can define the cost in complete analogy to what you saw before. Here again, we have the cost for the representative player who chooses to modify the recommendation. So he gets his phi, the recommendation, applies his modification u, and applies the resulting strategy to the state and the flow of measures. Okay, then if you do this, the cost function is well defined. And you can give a definition of correlated equilibrium at the mean field game level. Again, the distinction here between restricted correlated solution and correlated solution against progressive deviations is only here in the deviations you allow. So these are functions that take a restricted strategy and give a restricted strategy, and these are functions that take a restricted strategy, so the recommendation, and can use a strategy that depends on everything. You have the optimality condition, and you have the consistency condition, because what you want to do is, in the mean field game business, you want to have this representative player, so it really has to be representative. So it shows the representative player, when playing optimally, should produce exactly the behavior of the population. So you have this consistency condition. But here we need a stronger condition, so we require that the conditional distribution of the representative player's state, given the entire flow of measures until last time, terminal time, gives us the flow of measures at time t. So this condition is stronger than what you might expect. And in the classical mean field game solution is a particular case when rho, this correlated flow, is a Dirac measure. So the recommendation is always the same, and you have a deterministic flow of measures. Now here, this example, again, it's heavy, but the idea is you have a two-state system. You have just, in time, you have initial time t equal to 1, and terminal time cap t equal to 2. You have these two actions, and the two actions, they correspond. Action 0 corresponds to do nothing, and action 1 corresponds to try to stay in the state where you are. So what is, and there's no interaction in the dynamics, only in the costs. So what these dynamics do is this. You have this noise, this will be uniform. So if you do not do anything, then with probability 1/2, you will switch state. And if you decide to do something, then you will stay in the state you are with higher probability, with probability 3/4. Okay. That's all you can do. Now the costs, you have these running costs. You pay for doing something. Yeah, this is this cost here. But you earn if your state is aligned with the mean of the states of the population. So this is M, bold M of M is simply the mean of the two-state distribution at any time. So you want to be where the majority is. This we are minimizing costs. So this gives you less costs. Now consider these strategies. So the phi plus strategy is to do something when you're in state 1 and do nothing when you're in state -1. So the effect is that you want to stay in state 1 when you are there. When you're not there, you cannot do anything. So you can just hope that the noise will switch you. This phi hat plus strategy tells you to do something to stay in state 1 if you are there at time 0, but nothing at time 1. Then you have the symmetric, there's the switch strategies where 1 and -1 change roles. And you have the idle strategy where you fight 0, you do nothing. Okay, so the noise will switch you. Then you have infinitely many solutions. I won't go into that. You can choose some parameters, and then you can construct infinitely many solutions that are also robust against progressive deviations. Just to see how it works for one, to give you one correlated flow, so one explicit solution. You have this distribution. It's on strategies and flows of measures. So the flows of measures are simply these triples. No, the distribution at time 0, distribution at time 1, state distribution at time 2. Here in this picture, we identify a distribution with its mean, and we start from a M0 from a mean 0 distribution. So half of the population is in state 1, half of the population is in state -1. And now you have these flows of measures. You can have this M0, M+1, M+2, so you have a majority in state 1. You can have a majority in state 1, but then you go to half-half, or you can have the same thing with state -1. Now, if you look at these, this correlated flow, what does it mean that if you, from the point of view of the representative player, if the representative player receives the recommendation to play phi+, so to try to stay in state 1, then he can condition and knows that the flow of measures should be this one. So this is the flow of measures the mediator tries to achieve. The same for, no, there's just one, this is flow of measures is just here. The same happens for this flow of measures, where you have the recommendation to stay in state 1 if you are there at time 0 and then do nothing. The interesting recommendation is phi0, because if you receive phi0 to do nothing, then you're actually not sure what the flow of measures will be. So it can come from this flow of measures, or this flow of measures, or this flow of measures, and there's another flow, so four flows of measures. So this means that you actually have a random flow of measures. The costs are made in such a way that people will, so the representative player will accept the recommendation, but you have, so you have this correlated equilibrium. You have no common noise. You have only your representative noise. So still you have a truly random flow of measures. And you can construct infinitely many of these solutions. Then just the results, if you use restricted strategies, I won't bore you with the continuity assumptions. So the convergence result, it somehow has a typical form. So you start from, now you start from epsilon and correlated equilibria. In the restricted strategies, you assume they're symmetric. Of course, you assume that the error goes to 0 as n tends to infinity. You have product form initial distributions, and you assume that they converge. Then if you look at these realizations, so it's enough because of symmetry to look at player 1. You look at the recommendation player 1 receives, and this is the flow of empirical measures. So this is the interaction between these n players. You look at the distribution, joint distribution. Then you have convergence along subsequences of these rho n, and any limit point gives you a solution in restricted strategies of the mean field game. Now you can also do the opposite. So you start from a solution of the mean field game, and you want to construct these correlated profiles. And what you do is you condition on the flow of measures. So this rho 2 would be the marginal distribution of the flow of measures. You condition on the flow of measures, and conditionally on this flow of measures, you give IID recommendations. So then this row 1 would be the conditional distribution of the recommendation given the flow of measures. And this gives you epsilon and correlated equilibria. So in this way, the mediator can induce behavior of the n-player population, and that n-player population will give you a flow that is actually close to the limit flow. Now you can also, last part, you can also construct robust epsilon, robust correlated equilibria, but you need that is robust against deviations that have access to the information on the entire system. But here we needed more stringent hypotheses. So in the first part, this is actually not really needed. We need some continuity on the dynamics, Lipschitz continuity on the costs, and a non-degeneracy assumption on the dynamics, plus this condition. Oops. So suppose you have a solution of the mean field game. You take a realization, so you take variables phi and mu so that the joint distribution is equal to rho. This phi is a recommendation in the mean field game, the signal. So what we need is that the recommendation up to time until time small t that must not reveal too much information on the future, about the future of the flow of measures. This is this conditional independence. So because otherwise in the n-player game, the deviating player could somehow exploit that information. And if this is the case, then you can do the same construction as before. You can construct these correlated profiles that are robust against deviations. Deviations that have access to the entire system history. Okay, so maybe I skip the proof and just say that the idea is to use to reinterpret these strategies as open loop controls, and then to so that you can interpret the n-player game as a perturbed mean field game. And then you have to show that the costs converge. Okay. Thank you for your attention, and 100 anni to Paolo.
Marcus, questions? No questions? Che? Ah, scusa. Scusa Paolo, ci vedo.
Thank you, Marcus. Concerning the example, the two-stage example that you presented, I got a bit lost. So you presented, so in the long formula for all this, that is actually a correlated equilibrium, right?
Yeah.
And as far as I'm not familiar with these notions, but I sort of understood that a Nash equilibrium is a special case of correlated equilibrium, and also a Nash equilibrium in mixed strategy is a. So is this the unique? Correlated?
I mean, no, because here you have these parameters, and you can choose different weights. And as long as these weights satisfy these constraints, then you have a solution.
Okay.
So you have infinitely many solutions.
Okay. So in a sense, in a standard mean field game, you may have a unique or even non-unique Nash equilibrium. So then you may have other Nash equilibrium in mixed strategies, and then you can have other equilibria in correlated equilibria. So that's the point. And so the point of the paper, I'm just trying to see whether I understood that, is that all the convergence results in the two directions are still valid even for this notion of correlated equilibrium. So
yeah. I mean, I should have said, so one advantage of these correlated equilibria, especially when you're in a situation of non-unique solutions, that it gives you an answer of how players find a solution. Because when you have multiple Nash equilibria, it's not clear how players choose the Nash equilibria. If you're just one, okay. But if you have multiple Nash equilibria, it's not so clear. But with correlated equilibria, it's clear because you have the mediator. So the mediator first chooses one of these solutions, then sends a signal, but if it's really a correlated equilibrium, then players will accept.
Okay.
So this is maybe one of the motivations also for studying these correlated equilibria. Also in in computer science, I think they use them for networks. Also, so you can design, you get access rules, for instance. So the individual agents could do something else, but they don't have an incentive.
And is there hope of studying these notions in, say, continuous time?
Yeah, it turned out to be more technical than we thought it would be. So continuous time, finite state, that should be fine. When the state is not is countable or even continuum, the one difficulty is how to model these deviations. So okay. Because now we have, as we do it here, we have functions on these strategies. So they are functions defined on the set of strategies.
Thank you.
Okay, another question, then maybe we move on.
Very quickly, but maybe I missed. So the strategies of the mediator, the function phi, are fixed at the beginning or change? The mediator chooses according to the preferences of the strategies of the players.
Yeah, right. So the mediator chooses so what is known and what is fixed is what is known is his distribution on strategy profiles or the correlated correlated flow. So the distribution is known, and the mediator before the game starts sends a signal, and that signal is a strategy recommendation, and it's sampled from that known distribution.
Okay. Okay. So the mechanism design theory in which there is. Okay, maybe I will postpone the question to you after.
Okay.
Okay.
Yeah.
Okay, thank you. Thank you, Marcus, again. And we move on. Thank you, Marcus. So, dov'è? Here. Ciao. Okay, so we have Luisa now, Andres. So Luisa presents her work about large deviations for coagulation processes and approach via graphs.
Yeah,
okay, so
you.
Luisa, please.
Yes, better. Okay, thank you. Oh, no, wait. Okay, so thank you for the introduction. And I have to confess that I couldn't, I mean, it's my fault. I didn't prepare anything to say at the beginning for Paolo, so I don't want to improvise because I'm not, I can be not so concise. So let's just say that I'm very happy to celebrate your birthday here, also because it's a very nice scientific family that you create around you, so it's going to be very fun, I guess. So, okay, and thank you for organizing this to all of the organizers. Okay, so let's start with what I want to tell you, which is about large deviation for coagulation processes, which is a joint work with some colleagues in Berlin, mainly with Wolfgang König, Heide Langhammer, and Robert Patterson. And so let me start with what we mean by coagulation processes. We mean what you might imagine. So we have a certain number of particles which are provided with their own mass. And the mass, for simplicity, let's say that it's an integer, positive integer. And we have a parameter of the model, which is the total mass of the model. So let's say n, and it's the total mass of the model. And the coagulation works as follows. So you pick a pair of particles with a certain rate that depends on the two masses of the particles. And according to this rate, you merge these two particles into one particle with, that has as a mass the sum of the masses. So exactly what you might imagine for coagulation. And these type of models, they might have a phase transition, which is called gelation. It's a phase transition in time, in a sense that depending on the form of what this function here we call usually the coagulation kernel, depending on the form of this function, then you might have a phase transition in time, meaning that if you let time go enough, in a finite time window, you might still see, you might all of a sudden see a particle, or even more, whose mass is not negligible with respect to the total mass of the system, so basically a giant particle. This is what we call what is usually called gelation. So these type of models, of course, they're very natural, and so they've been introduced a long time ago. And the first one to introduce this was Molokowsky, and he introduced the study of these models from a macroscopic point of view, so studying some deterministic equation modeling average quantities in such systems. So let's imagine that nk of t is the proportion of mass in particles of mass k at time t in our model. Then, of course, we have a full sequence of these quantities, and k, depending on k, and how these quantities evolve. Well, they evolve according to some difference equations, which is then a collection of equations, which is called, usually called the Molokowsky coagulation equation. And this is, you see, it takes into account the fact that you might increase the proportion of particles of mass k if smaller particles merge, so of masses h and k minus h, and then you might decrease the number of particles of mass k if you merge with anyone else. And let me mention that, of course, this is then a system of differential equation, and there is one important initial condition, which is what we usually call the monodisperse initial condition, which means we start with all particles of mass 1. And of course, you can define and study the same model from a stochastic point of view. So this has been introduced a bit later, and it's usually called the Markov-Lucnikov model, and it describes the same model in terms of a continuous time Markov process. So you have the Markov process of the sizes, the masses of your particles, and of course, the masses, the number of these particles will decrease with time because you have these coagulations going on, while the masses, they increase. And okay, then this is a continuous time Markov process, and again, you can describe the same initial condition. So the monodisperse, you start with n. So if n is still our parameter, n particles of mass 1. And if you want to define these two models in a way that somehow they correspond one to the other, so the microscopic correspond to the macroscopic, then you just have to scale properly the coagulation rate. And the proper scaling is 1 over n. So basically, if you want your model, your microscopic model to correspond to the macroscopic Molokowsky coagulation equation, then you have to take the same coagulation rate and scale with 1 over n, and then let n go into infinity. So as I said, you would like to have these two connections between the microscopic and the macroscopic model. And how you do this? Well, you define an empirical measure. This is the empirical measure of the particle masses. And you take into account the path in time of this empirical measure. So this empirical measure will change in time for a fixed n, will change in time with jumps, because the jumps will be the coagulation of particles. And okay, then what it's known, it's that if you start with the monodisperse initial condition, the monodisperse initial condition for any n, it's always the Dirac measure in 1, so it's always the same. If you start with the monodisperse initial condition, well, indeed, what you see is that when you let n to infinity, then the evolution of this measure is indeed deterministic. It follows a deterministic trajectory, which is n, and as well, and this is true also for sequences of converging initial conditions, so not just for the monodisperse. And as you might imagine, well, if there is no gelation, so for non-gelling coagulation kernels, this deterministic trajectory is indeed the solution of the Molokowsky equation that we wrote before. Well, but then you might be a bit worried because I was talking about gelation and I wanted to describe a bit gelation, and this is not, I mean, and then maybe there is some problem. Well, indeed, for some nice gelling kernels, which are usually already a good class of gelling kernels, well, the convergence, so the hydrodynamic limit, is true in the same way. The only thing is that Molokowsky didn't really take into account the role of giant particles. So if you really want your empirical measure to converge to a solution of a deterministic equation, well, you have to slightly modify the Molokowsky coagulation equation. This is known, and it's usually called the Flurry equation. It's basically the same equation with a small additional term that takes into account, if you have a giant particle, this sucks a bit the mass from smaller particles. Yeah. Yes, little n of t is the number of particles. The fact is that this empirical measure, it's not a probability measure. It's not summing up to 1. So you're scaling with the total mass of the system, capital N, but then you're just summing over the particles that you have available at time t. So this is a sub-probability measure, indeed. So that's the only thing that you have here. Yeah. Okay. And no, let me mention also that, I mean, Molokowsky wasn't so wrong, because up to gelling time, Molokowsky equation and Flurry equation, they indeed correspond one with the other. Okay, so let me now go to what we would like to study, which are large deviations. So it's pretty natural, yeah. Yeah. No, there is no. These are just the masses. So these are just integer values, and these are just the masses. So this is an empirical measure on the integer numbers, which is telling you how many particles you have of each mass. Yeah. So, okay, so this is your empirical measure. You know that it has a sort of, it satisfies a sort of law of large numbers. You would like to study large deviations for this. And let me just tell you, we are now in the framework of jump Markov processes, because all the evolutions are given by jumps of our empirical measure, and the noise is vanishing. So let me just describe you in general what it's known about large deviation in this setting. And let's now simplify a bit. So consider a finite space, sigma, let's say with D is a number of elements of our space. Then in general, we can define an empirical measure on this space, and this empirical measure on this space, it will just be a finite vector. It will be a d-dimensional vector. And okay, so I want to describe a Markov dynamic on this with jumps, with a vanishing noise in this sense. So let's take a set of possible jumps, which it's usually called R because this terminology comes from stochastic reaction networks. So R is the set of possible jumps. When a jump occurs, the amplitude of this jump is given by a given vector, let's say gamma of R. But the amplitude of this jump, we actually want to rescale with the size, with a parameter that we want to send to infinity. Sorry for the bad notation now. The parameter that we send to infinity is small v. So we rescale the size of the jump with small v, but then what we have to do is we have to increase the rate of these jumps happening. So let's say that the rate of a jump happening is a function lambda times v. So it scales with v. And if this lambda actually converges to a finite lambda, then we really have this situation in which we have small jumps, smaller and smaller, happening more and more often. And this is known, and this is a nice situation, because this is known that jump Markov processes like this, so described by this generator, they do have a law of large number, exactly as before. So they concentrate on solution of what is usually called the fluid limit, which is, as before, an ODE. So before we had an infinite dimensional ODE, the Molokowsky equation was an infinite dimensional ODE. Here we have a D-dimensional ODE. And why I introduced you that everything in D dimension, this is just because the large deviations which are known, and there is a good framework for this, is for finite dimension. So for finite dimension, it's known that that the evolution of this jump Markov process on any finite time window, this satisfies the large deviation principle. So, and the large deviation principle is on the space of Cadillac trajectories on RD in this case. And it's also, the rate is V, so the rate is really the rate of the scaling of the jumps and of the frequency of the jumps. And also the rate function is known. It's pretty explicit in a sense that it's a time integral of a certain, infimum of something, so a certain variational problem. But this is well known, and it's easy to write down, and the fact is that this falls into the Friedlin-Wenzel theory, and proving this large deviation principle involves usually, normal proofs of this large deviation principle involves tilting. So you do have to tilt a bit your probability measure, and how you tilt? Well, you tilt using your rates. And now I want you to arrive precisely here, because what you do is that you tilt in order to tilt your rates, you have to be sure that either your rates are bounded away from zero, or at least they behave nicely close to zero. And now it comes a problem, because if instead of being in dimension D, we are in infinite dimension, so for example, if our state space sigma is n, as it was for the coagulation process, then you cannot bound away from zero your rates, because they have somehow to be summable at a certain point. So for sure they will approach zero. So this tilting procedure becomes harder, and maybe it doesn't even work. So it's the fact is that then you cannot really apply directly what it's known for jump Markov processes in finite dimension to this case of coagulation processes. Okay, so going back to our Marcus-Lucnikov process, imagine that we have precisely in the same situation, but now our space is the natural numbers, is not anymore a finite space. And okay, but then we can still describe all the jumps. The jumps are really just take away one particle of mass m and one particle of mass n, and plug in one particle of mass m plus n. This is what a single coagulation is doing. Of course, then you codify this for any pair of particles, but you see your rates, they are proportional to the empirical measure, so to the number of particles, to the proportion of particles of mass m and of mass n. And this is clearly not bounded away from zero if your m is some fine, nice measure. Okay, so this is the situation that we have, but we do have problems then. We cannot really apply what is known for the finite dimensional case. And so now we decided, okay, let's focus on one particular coagulation model. So let's pick one coagulation kernel, which is a multiplicative one. And we picked this, because it's the simplest one that is showing a phase transition. So it's already a pretty interesting one. But we also picked this because of a very nice correspondence, because it's known that if you start with the monodisperse initial condition and you look at the finite, at the distribution of your particle sizes at time t, so you fix the time and you just take a screenshot of your particles, the distribution of the masses, in this case, has the same distribution of the connected components, of the size of connected components in one particular Erdogshanigraph random graph, which is the Erdogshanigraph random graph with this precise kernel. Imagine you have n vertices, you have your edges you have a complete graph on n vertices, and you put on all of your edges an exponential clock, independent exponential clocks with rate 1 over n. This is precisely this Erdogshanigraph random graph if you look at the graph at the fixed time t. Okay. Okay, and then you also see that it's pretty natural that the gelation corresponds to the creation of a giant component in the Erdogshanigraph. But this is not the only case, because indeed also, and okay, this is known for the monodisperse initial condition, but you can make the same correspondence also if you start with any initial condition, and the correspondence has to be done with the inhomogeneous graph. So what's the difference between the Erdogshanigraph and the inhomogeneous graph? Well, you just have your vertices, they are provided with a type. And in this case, so let's be fast here. So if your space S is, in our case, the natural numbers, is the type space, every vertex in our graph will be provided with an element of the space, with its type. And its type, we can imagine this as being the initial mass. And then we can construct a graph. And how we construct the graph? Well, exactly as in Erdogshani, you put independently an edge between two vertices with a probability that now depends on the types of the two vertices that this edge is connecting. So this is a pretty general, it's a very natural generalization of the Erdogshani random graph. It was introduced by Söderberg and studied mainly by Bollobás, Jansson, and Riordan. And okay, so and let's try to understand, okay, now we have this graph, and we started with vertices with a given type, and now we look at connected components. A connected component then will be a collection of vertices of different types. So for a connected component C, I can define a type of a component, which is telling me how many vertices I have of type 1, of type 2, etc., etc. And then imagine summing up all these types. So if I want to say, okay, if these were monomers clamped together, if I want to compute the mass of this component, well, then I will just sum how many vertices I have of type 1, then I will sum how many vertices I have of type 2 times 2, because they weight more, and so on and so on. So this is what we call the type of a component. And now you can see that it sounds somehow that you can make a connection with the coagulation process again. Because if you start your Markov-Lucnikov process with a given initial collection of masses at time 0, then if you look at time t, so the distribution of the masses of your particles has exactly the same distribution of the types of components, of the mass of the components of the inhomogeneous graph. And now you just have to be sure that you're putting the precise probability of connection on your edges, such that you're really able to make the connection between the two, but this is completely possible, because now instead of putting an exponential of rate 1 over n, you put an exponential whose rate is the product of the types of the two vertices, again over n, because the time scaling is the same. So this is a well-defined inhomogeneous graph. And so now we can use results on large deviations that we have on the inhomogeneous graph. So for the inhomogeneous graph, we can define again, I don't have much time, so I won't define too much what we mean, but we can define a very nice empirical measure on our graph, which is telling us how many components we have of any given type. And so let me go a bit far. This is a measure. It belongs to a nice space of measures, and we can set everything up in order to get a large deviation. And what we have proved together with Wolfgang König, Heide Langhammer, and Robert Patterson for the inhomogeneous graph is that in general, if your type space is compact, and the function that makes the connection of vertices of two different types is a continuous function, so it's basically it just has to be bounded. Let's say that if this function is bounded, then this empirical measure actually satisfies the large deviation principle. It satisfies the large deviation principle whose rate is really the size of the graph, and the rate function is explicit and is given. Okay, so this is, but you see that this empirical measure is an empirical measure on the size, on the component as an element of the graph. It's not summing the type of a given component. Oh no, so let me first say another thing, so that our result was for compact sets, type set. But then you said, okay, but you just said that your type space, if you want to make the connection with the coagulation, has to be n, and this is not compact. But indeed, everything is so nice that this is still true, that the empirical measure thus satisfies the large deviation principle also in this case. And okay, and then you can also project. So you can also say, okay, now I have my large deviation principle for the graph, but now I want to look at a summarizing quantity, so the total mass of components, because I want to connect with the coagulation process. But this you can do, and so this is something that you can do via contraction principle, and you can prove that the sequence, and since you have your one-to-one correspondence, this is really a large deviation principle for the time marginal of the coagulation process. And you can say that the time marginal of your coagulation process satisfies the large deviation principle. You have your rate function, and everything works. But now you know that you have a Markov process, so you just want to just patch together pieces one after the other, because your result is rather general. It works for any given initial condition. So you can say, okay, now I want you to have a large deviation for at least a finite dimensional distribution of my Markov process, and this you can do. It's just patching together finite things. But then you can also elevate this to the level of paths via projective limit. So you just say, okay, now I have for any discretization of my time interval, I do have a large deviation principle. Okay, then I just have to check that all the conditions are satisfied and everything, such that I can lift this to the level of the path. So to have a large deviation principle for the path of your empirical measure on your finite time interval. And this is true, but the thing is that your rate function is pretty ugly and it's very implicit. It comes in a form of a soup. So it's very different from the one that was known for finite dimensional jump Markov processes, because there it was a very nice time integral of some very nice variational problem. But indeed, you can prove, so your last step is that, okay, now you can try to see if the equality holds. And when there is no gelation, the equality indeed holds. So you can prove that those two large deviation functions, even if they look very different, they are the same. And okay, you just have to write down properly your condition on the Markov process. And indeed, well, here I wrote that when there is gelation, we're still trying to understand this, and this is a joint work, I have to say, is an ongoing joint work with Heidel and Gammer, but indeed we do have also the same. So the fact is that it's not really clear what you have to put here inside your variational problem when you have gelation. Because it's very easy to construct this function when you do have your finite set of jumps, but with your coagulation processes, at any finite time, you don't have the interaction with the giant component, because the giant component is not even well defined for a fixed n. So you just have somehow to understand how you have to write down the missing term here, which is indeed, in the end, pretty natural. And we still have to finish the details, but somehow we are really pretty confident that this equality also holds in that case. And with this, I just give you, okay, then of course I give you some observation and the fact that what we proved is a large deviation principle, but for one particular type of coagulation kernel, which is very special, and you might say, okay, then maybe it works just because you have this nice connection with graphs. But we still hope that at least understanding the graph can give you some information on the coagulation process, also for different kernels, because you might imagine that, okay, on any given time frame, you don't have a one-to-one correspondence with a graph. But if you look at small time frames, maybe this is still true, because on a small time frame, also if you look at your graph, only few edges are put there somehow. So maybe, but this is somehow something that we still want to understand, and still interesting to understand the connection between the two things. And with this I finish. I thank you, and I wish Paolo happy birthday.
Thanks, Luisa. Do you have questions? Oh, sorry.
So in the large deviation for the fluid limit that you write with an infimum, so that one on the left exactly. If I remember well, I think in the paper of Renger, so this is really a contraction principle. So it means that you have a higher level large deviation. So in special, I think in that case you are looking at the current. So. Do you think that there will be an higher level large deviations also on your coagulation process?
Yeah, the fact is that somehow in this type of papers, usually you really look at the flux, so the number of reaction of any given type. And because when you describe your Markov process, you're only describing, you are describing your Markov process via pairwise coagulation. So your fluxes are basically the pair, your reactions are pairs, and then you count how many times pair Mn interacts, so merged. And in our case, if you look at the graph, you do even have a larger, more things going on, because if you look at the connected component of a graph, you don't only, the flux, so the reaction would be an edge. But if you look at the connected component, you're actually looking at a sequence of things that happen together. And so the higher level would really be how a given particle at time t, you have a particle of mass m, the graph is telling you how you create this particle. So you create this particle with first merging two particles of mass 1 and 1, then merging to one particle of mass 5, and then and these are your edges in your connected components. And this maybe gives you a bit more about the history of how you create anything. So I would say that this is somehow a connection, but I'm, yeah, that's the only thing that I can say, more or less.
Okay,
Thanks.
thank you. Thank you.
Thanks. No question anymore.
Yeah, I mean, it means that you're just doing your, you're just studying. It's also a pretty vague sentence, because it means that you're studying your rate function on, so here the path is called mu. Mu of t is the path. So you're studying your rate function, the equivalence of this rate function for those mu that do not have a loss of mass. Because loss of mass is what you codify as gelation. If your mu loses mass, it means that something is gone somewhere else. And so if your mu preserves mass, you don't have gelation. So, but I have to confess that it's a pretty vague sentence. If you lose mass, you have gelation, yeah. So, you can have loss of mass, and this large deviation principle holds for any path mu, even with a loss of mass. Now we are trying to identify with a different form, and we are able to do the steps, the computations, for those mu that doesn't lose mass, that don't lose mass. I mean, now we are kind of sure that we can also do that for mu that loses mass. But since we still have to fix the details, I don't want to say anything that it's not true. But let's say should be also when you lose mass.
Thank you.
Yes.
Okay, so other questions? I have another one. You know? Okay, so I think we can close the session here. So we thank Luisa and all today's speakers for the nice presentations. And now, Ida has an important communication for us.
No, I only want to say that there is the guided tour now, and you can leave your things here. I have the key of the building, then we come back here and you can take your bags and things like that. So if you want to participate to the guided tour.
Yeah, no, the tour is mandatory.
So there is the guide here, which is waiting, who is waiting for us since 10 minutes, so we can go. You have there the, okay.
Devo chiedere a chi è collegato se sente.
No, io la pazienza non ho avuto, se do l'altro gelato, va bene, se do l'altro microfono gelato, no. Okay,
non mi va,
allora
ma...
va bene così.
È proprio debole allora.
Sì, un po'.
Debole? Si dice?
Però funziona, cerchiamo di alzare al massimo.
Sì.
Sì, questa cosa che... No, questo è il canale.
Prova. Funziona ma è molto debole.
Sì, un po' debole. Io lo posso
condividere. Condividi schermo.
No, questo interrompi trasmissione fa.
No, ho fatto via.
Ah, ok, scusami, quando l'ho visto sì, si fa via.
Prova.
Io te lo alzo mentre parlo.
Nicolas Forian. Sì, e Alexandre Gaudière. Sì, e dal CIEM che abbiamo pensato a fare questa. Ok.
Siamo? Prova. Troppo forte questo. Prova.
No, aspetta. Il mio funziona, ma è basso. Mi sentite adesso? Sì, ottimo.
Benissimo.
Sì, ho paura di perderlo. Forse è troppo...
Sai che cos'è il laser? Quello a destra. L'ultimo è il laser.
Sì, ma non ho bisogno di laser.
Ok. Posso iniziare? Sì.
Okay, I think we can start this session this morning. Welcome to you all in this room and also to all of you who are connected remotely. It's a pleasure to introduce Amina Sela, who's going to talk about activated random walks. It's a joint work with Nicolas Furian and Alex Godier.
Okay, so thanks a lot for the invitation and for the organizer for such a technological conference, very demanding. Okay, so I'm very happy to be here and to wish in person a happy birthday to Paolo. We met some 30 years ago, actually, in the fall, in September '92. So it's a long time ago. I was starting my PhD thesis at Rutgers, and he was just finished. I mean, he had defended his a few months ago. And we just exchanged a few words. I think he just said, welcome to Rutgers, and that's going to be great. And I did not know where I was landing in this place, and it was very nice to have a few words. And then 2 years later, Paolo came back for a 1-year stay with his family, even with a babysitter. And since then, I mean, we were always together. We worked for 1 year. And at the end, for our advisor, Joel Leibovitz, we were the same individual. Whenever he was meeting me, he was asking me, where is Paolo? Whenever he was meeting Paolo, he was asking him, where is Amin? So it was a great time. And since then, I mean, I had only good things from Paolo. So it's just amazing that for 30 years, we just stayed very good friends. Okay, so let me now go to the technology and tell you about activated random walks. So it's a recent work with Nicolas Furian, who is a postdoc in Roma 1, and Alexandre Godier, who is at Marseille. I'm not going to, you will see the result is very short, but I cannot really explain too much the proof. I'm going to convey the main steps, some ideas, the model, the conjectures, and so just interrupt me whenever you want. So it's the thing is that it's a family of model. So let me start with the model. You'll see. And so, rather say models. No. So it's really a family, a huge family of models, of interacting diffusions. So particles have two types. They can be either active or frozen or sleepy. Okay? When they're active, when do they are just simple random walk. With one clock, so they have a clock, an exponential clock with a parameter lambda. And when the clock rings, they go to sleep. Okay? So let me just say A, go to sleep with the rate lambda. And then sleep means my particle does not move anymore. So it's on a graph, it's moving on a graph. I'm going to always think of my simple random walk on the graph ZD or on the torus Tn, which is the Z over Nz to the D. Okay, then when you are sleeping, there is nothing to say you're not moving. So if you had just one particle, what it would do, it would run, walk, and then at an average time of order 1 over lambda, so 1 over lambda is expected time of life, it has it has reached the ball, the boundary of a ball of square root of 1 over lambda. There, it stops. It slips, and that's it.
On a walk of rate 1?
Yes. Let's say, yes, you're right, continuous time random walk. That's it. So the problem would finish there if I had just one walk. And the thing is that there is an interaction between the activated and the sleeping one. And the interaction is, let's say, stay still. The interaction is that if you put an active and a sleeping on the same side, immediately you get two active. Okay, so in the sense that if I send another of this walk there and it crosses here, at the time it crosses on the same side, you will have two particles, one sleeping, one awake, and then it wakes the black one, and they go sleeping later in some other place. Okay, that's the simple rule of interaction. Nothing more. And this is, let's say, at an infinite rate, immediately. Okay? So I can call this activated random walk of parameter. The parameter is lambda. So actually, I said it's a huge family because we have to think also about the second parameter, which is how many particles you put in your system. So typically, I'm going to put density mu, call it positive less than 1, of particle on my ZD. So what I will do, usually I will take a product Poisson measure of parameter mu, let me call it P of mu, and this is my initial condition. Okay, so just to be sure the model is completely clear, let me take the example of particle who have the lambda equals 0. Lambda equals 0 just means that it lives for an infinite time. Okay, so it lives an infinite time. So it's a simple random walk. So you would say, okay, the model is just random walk. So if they all activated, that's kind of well known. But imagine that now the initial configuration is slipping. It goes to the eraser immediately. Slipping everywhere. Let's say according to P mu. So I put sleeping particle. Yes. Sometimes many of them. And just one activated at the origin. So the rule, still they interact. So the sleeping do not move unless the activated step on one of them. And then this one is waken up and continues. So it's a model which has been studied, and they gave it the name the frog model. It's also related to this model. So the frog model was studied a lot by the Brazilians, Fabio Machado, Sidoravicius, and also Ramirez, and their friends. So studied a lot. And there is also a model, it looks like a model of propagation of a Rimmer, propagation of Rimmers, studied by, let me write, Kesten and Sidoravicius. Which looks like two types of particle, one diffusing faster than the other one, very few of the fast diffusing in a sea of slow diffusing. Whenever you have an interaction between them, they go to fast diffusing. So it's a propagation of an infection. You can, I mean, they call it many names, and they made some serious work on that. They have shape theorem and things like that. Okay, so you see that if you choose well your initial condition, I mean, you get some other phenomena. So that's why I'm saying it contains a lot of things. Now, let's take lambda equal infinity. This means that right away you slip. Okay, you slip right away. Let me choose a special initial configuration to tell you what's happening. Imagine I have this cluster, this region of slipping particle. All of them are slipping. My origin is here, so they don't move. And I start with one active there. So this one is on top of a slipping. So it wakes it up. So at the origin, if I draw what's happening, I have two particles. They become active right away. As soon as this one jumps to one of its neighbor, the other one immediately becomes slipping because it has an infinite rate of becoming slipping. So as long as my particle is on top of a slipping one, you can think of of the process as just it's diffuse on top of the cluster. And as soon as it goes out of the cluster, then, oh God, then it slips. It slips. So this is internal DLA. This is a famous model called internal DLA for diffusion limited aggregation. So they diffuse at a slow scale, and they aggregate very fast, as soon as there is an empty site. Okay, so activated random walk is like interpolates between independent random walks and internal DLA. But our internal DLA is much simpler than activated random walk, because when they sleep forever. Whereas in my case, the problem is that at whatever time, if I step on a sleeping one, wakes it up, and so you can imagine that there are waves of activated roaming all over. And so that's the problem. So the nice thing with activated random walk is that you expect a phase transition. So now I'm a little bit about trying to convince you that you should study activated random walk, because as you increase the density, imagine that I start as density is increased in your initial measure, P mu, and if you start with all active, you expect that if you look at the long time behavior of the system, if mu is small, there is enough room for particle to slip. Each one is far from the other one, and it makes its life without seeing the other one and slips. This one has small chance to meet the other one and slips. There is enough room, and you expect that the final state is a state where everybody slips. In other words, take the origin of your system, is going to be visited a finite number of times. If mu is large, you will have region, let's say, of high densities where particle one is going to wake up everybody, and region of low density, of course, in the same on your configuration where they slip. But those region of high density, I expect them to diffuse. So how to say it mathematically, the origin is going to be visited infinitely many times. You will always have clouds of diffusing particle. You take a window, finite window, and you will see at all time particle diffusing there. Okay. And so it's easy to see that something is going to be increasing, or there is a boundary, there is a critical model, critical line where below you fixate, this is called fixation, and above you have, I forgot how it's called, activated phase, activation. That's the activated phase. Okay. Nothing is proved. I mean, that's conjecture, this picture. What is known is that you can define mu c, I don't know if I can, it's the largest, let me try to write it, a definition for mu c. The probability that the system eventually fixates is positive, and I want the largest mu, sup of mu. Maybe it's wrong, but it looks like correct. That's the largest number, the largest density. This means my starting initial condition is product Poisson. And there is a 0-1 law. You know that this function is increasing in, so lambda is fixed. Okay, that's, it looks to me.
A question about the normalization.
The what?
Okay, I have a question about the definition of the model. When you give the initial configuration, you have to fix a parameter that rules the density of the particle. But also you have to decide the type of the particle, if they are activated or sleep. So I was wondering if in this definition, I don't know in which way it depends on your choice. All activated. Okay.
All activated.
Thank you.
You start with all activated, but your question is good also because I said Poisson, but why do you choose Poisson? Why don't you choose Bernoulli, product Bernoulli, all activated? Would it be the same thing? The nice thing about activated random walk is that at least there is some universality. All the ergodic translation invariant distribution on ZD will give you the same, exact same parameter mu c of lambda. And this is a work of Leo Rolla, I know Zindi, and someone else, for me, I think, and someone else that I forgot. Fournier, I guess. Okay. And it's believed that activated random walk is universal, contrary to some model introduced by physicists like the abelian sandpile, which is not universal. So that's why recently there's been some effort on the activated random walk, and I would suggest a very nice paper of Lionel Levine and Liang, I think 2000 on the archive. And they also announced a paper of Vittoria Silvestri and Lionel Levine on a lot of conjectures about activated random walk, but it's not yet on the archive. So, but Vittoria is in Roma Unos, and so she's the expert of this activated random walk. And maybe Zindi is the contrary. Okay. So what do I want to say? And the first question which comes to mind is this mu, no, I have to be stable. is mu c less than 1? You see, if you put one particle activated everywhere, you expect that there is, well, no space, so it's going to be activated. It's not obvious, but it has been shown that, let's say it's known that mu c is less or equal to 1. Since a long time, 2010 maybe, the model was introduced in 2009 by actually physicists, but also Vlada Sidoravicius. So he popularized the model in mathematics, Sidoravicius. So this talk can be seen as a tribute to Vladas. And since the model was introduced, you see, this model, even in dimension 1, is not trivial. It's far from trivial. So it was proved in dimension 1 with a lot of tricks that mu c of lambda is strictly less than 1. And I will review a little bit what has been known. Only recently. And it was open, wide open, if you look the notes of Leo in dimension 2. 2 was completely open. So in this talk, we show that, so the result is what I just wrote here. For any positive lambda, mu c is less than 1. That's the result. So what does it mean? It means that if there is some density strictly less than 1, such that you have activation. You have the activated phase. And actually, our proof works in all dimensions, and it gives bounds on how big mu c can be, or upper bounds on mu c. Okay, so let me say that this result with my two friends, Nicolas Forian and Alexandre Gaudière, is that in dimension 2, now I have to look at the precise, if lambda is large, because you see there is two asymptotics, lambda large and lambda small, two heuristics. Okay, if it's large, then mu c of lambda is less, a little bit less, 1 over lambda. Let me put in green so that you don't see too much. There is a log correction, which is just that we have not been able to get rid of this log. And if lambda is small, lambda small, remember, means it's like random walk. And this is less than lambda. Okay, time, again, I will put it in green. I have some log correction to the power u for some u. Okay, and we have bounds in dimension 3 and more, and things like that. So that's it for the result. Questions about the, let's see. All damage. Okay, not much. So it's like you can write it in a, that's it, that's the result. Let me mention other people's work. So I said that in D equal 1, so I have to write carefully. There is Basu, Ganguly, and Hoffman. CMP, it's a long paper, let's say for about 40 pages, very technical, where they show that mu c is less, mu c of lambda is less than 1 for lambda small. And then in the transient case, there is two very, very beautiful papers, one of Stauffer, who is also in Roma, and Lorenzo Taggi, and it's 2018, where they show that for lambda small, mu c lambda is less than 1. And this is dimension 3 and more. So in the transient case, for some reason, it's simpler. And then 1 year later, Lorenzo did something very nice work where he, they introduced a new technique which is called weak stabilization, but for expert, they look at the last time the last particle was going to slip and things like that. And they could show this for any lambda. Okay, and yes, some bound like mu c of lambda less than c square root of lambda. So let me just say that last year in dimension 2, there was two groups independently. A student of Christopher Hoffman at Washington could show that for small lambda, we have the interesting thing. And Nicolas Forian and Alexandre Gaudière show the same thing with a completely different proof. And we actually, in this recent work, they just asked me, can I join them to do the lambda large? I said, of course, I'd be happy. But they had so many tools that I just watched them doing this proof for lambda large. So lambda large is also based. So this paper works with a few new ideas. Works with a few new ideas to control lambda large. Okay, so, and I want to, but first I would like to tell you some heuristics, because in my case, if I don't have good heuristics, I'm completely lost. And understanding the heuristics helps you to find the missing steps in the idea in the first paper of Nicolas and Alexandre. Okay, so how to have an idea of what's the value of mu c lambda? What's mu c lambda? Okay, you see, in this work we are not able to find the function, this function. We just have bounds, but the heuristics are kind of simple. Imagine you have slipping particle. Exactly at density mu c. So what would it mean? If I'm a little bit lower, it means that if I add just one particle, active one, it should slip. It should end up slipping. Okay, imagine I'm just a little bit below, and I add one particle to the sea of slipping particle. So you expect that if on its journey before slipping, he meets some slipping particle, that this number should be on the average 1. So that he doesn't, because you see, whenever he meets one, this one starts and is in turn going to meet others. So it slips here, but maybe it has met this one, so it wakes it up. So it's like a branching random walk. And you want it to be critical because you still are in the sleeping phase. So you don't want this one to make a mess. So you expect that whenever one dies, one should wake up. Or on the other hand, on the range, on the support of this trajectory, they should be on the average 1 particle. So the expected number of visited sites, this is the range or the support, time this density should be 1. This means that the number of particles on the range of a given walk should be 1. So this means one new particle, one activated particle meets, on the average, 1 sleeping. So 1 will wake up and 1 will sleep. So we have a balance. And therefore it's critical. You have a critical branching process. And then, but then we know what's the expected number of visited sites for a random walk. Okay? No, but this is the key heuristics for me. I should get a critical branching process. So maybe I don't want to give you what's the expected number of visited sites. So this is called the range. The expected, so this is the range is the number of sites visited by a random walk and the volume of, so the number. And this is known that if you're in high dimension, this is like n, d bigger or equal to 3. In dimension 2, it's n over log n. And in dimension 1, it's square root of n. Okay? So you have these things. You know also that the expected tau is, this is how much time you have before dying. It's 1 over lambda. So using that, you find some heuristics for the mu critical in the case lambda large. Lambda large, you expect that it's going either to sleep right away or to move 1 step. So, and lambda small, where you really expect this to be large, and then you use the asymptotics. So this is the asymptotics. Okay, so what I mean is that easily you get some function, some guess for mu critical. So if you, I don't want to do all the steps, but easily you get some value for mu c lambda in the 2 cases. Remember, there are 2 cases, case lambda large and the case lambda small. Okay, and our inequality, what's important, our result, up to the log terms which is not in the right position is correct. We catch the correct power of lambda. Okay, so the heuristics. So there is a nice property, maybe I skip it, but let me say that there is a nice property in this model, which is the abelian property. So instead, let me just say a word about that. That is, instead of thinking of my random walk and each one moves independently, I'm going to prepare all the instruction beforehand. On each site, I write which instruction I'm going to use whenever a particle will step on the site. So I have sleep instruction, jump instruction on each site. I have independent piles that I prepare beforehand. It's like my environment. And then I put my particle and follow and look at the instruction one by one and get rid of the used one. What happens is that whatever order of particle you use to move them, the number of instruction, until stabilization, the number of instruction used is going to be the same at each site. You count how many instructions I've used, and this is called the odometer of a site, is independent of the order in which you launch your particle. Okay? So the abelian property is a beautiful thing which says that the number of instruction used in a site is until stabilization, let's say, until stabilization, and you will, stabilization is independent of the order you choose to launch your particles. So, what means until stabilization? That's your question.
No. The question is, thank you. So, and this is working also for the decision whether to sleep or not? It depends on the site?
Yes, on the site you have piles of instruction. One is sleeping, one is jumping right, one is jumping left, etc. This is what is written on each site. There is a pile.
Okay.
And indeed, but independently of which order you choose, it's important that the order is adapted. You don't see the future. Then
sorry, I
you
mean,
get, yes.
Besides the number of instruction, also the final outcome is the same. You mean also the final position of the particles is the same?
Yes.
Okay, sorry.
Yes.
It's not obvious.
It's not obvious.
Okay.
Okay, until stabilization. So here I have in mind that I'm working on a finite graph. Okay, so here really I said ZD, but I have in mind, it works also, and I have in mind the torus, Tn. So there, you know that at the end, eventually, they all slip. It's an absorbing state. You cannot have particle moving all the time. So there is a stabilization of the configuration. Okay. Okay, let me sketch the proof and start with the three old ideas from the paper of Nicolas and Alexandre and introduce three new ideas that we needed to solve the lambda large. So let me, yes.
But in the pile of extraction, if you have sleep and then move to the right, for example,
yeah.
you move to the right or because
no.
The particle sleeps?
No, it sleeps. It sleeps.
Okay, so all the possible.
If no one comes ever to see this site, to visit this site, you will never see those instructions. They are. But if a new particle comes there and wakes it up, the two particles are going to have to look at instructions. So they are indistinguishable. You choose which one you make jump this one, which one you make jump this one, and you cancel the instruction used, and you continue this way. So you will have like a curve which tells you how much instruction you have used after the passage of your wave of moving particle. Okay, the first step is that if you want to study this phase transition, it's enough to study let's say, if you want to show that the system does not stabilize, it's enough that on the torus, its stabilization time be exponential in the size of the torus. So it's a nice way with classical in physics, that enough to see that the time of stabilization, which is well defined on the torus, now I'm on the torus, that if it's less than, this is the size of the torus, less than exponential alpha Tn is atypical, less than exponential minus beta time Tn, something like that. It costs exponentially to stabilize fast. If you have a condition like that, if there exists alpha and beta, positive, such that you have this for any n large enough, then you will know that mu is bigger than mu c, and I have to put a mu here. I start with a system whose time of stabilization is exponential. Then, when you pass to the limit, you know that you are in the activated phase. Okay, so this was, I think, established in many currents, but it's in the paper of Nicolas and Florian. But so let's say this is kind of classical, but the second is for me, it's a crazy idea, which I had never thought about, and I think you do it only when you're completely desperate, is that they studied this probability of having a small stabilization time, conditioning on the place where you slip. They said, okay, this probability of being small is the sum over all the subsets of my torus, such that I'm small and my finite configuration is A. And they said, okay, then, well, and they ended up saying, let's try to find a uniform bound sup of this, called A, the same thing, time the number of A's. So I said A, but you see, I'm starting with a density mu, so you expect A to have volume. Let me say that the volume is about mu times Tn. So you sum over all the A's with a given number of particles. I'm cheating a little bit because it's a Poisson, so it's not fixed exactly the number, but okay, so you expect here something like number of particles over mu Tn. That's the possible sets. So you say, okay, I cannot do anything with such a formula because I don't know the alpha and the beta that I'm expecting for this. I expect this to be less than an exponential minus beta torus. This is also an exponential times some entropy times Tn. So, you know, it's bad. I mean, but then there is one regime where you expect it to maybe work, is that if mu is close to 0 or mu close to 1, then this h mu1 is close to 0. It's, I forgot, maybe I wrote it, minus mu log mu minus 1 minus u log 1 minus mu. So, so then they were working in this regime, and the number of sets with such a number of particles was small now. If they could show that there exists a beta, they could take a mu small enough. That's why the first paper is for mu small enough. And then this decomposition looks completely crazy, but it has a chance to work in this regime, which would solve the conjecture. So I am in this regime now, and I say, okay, let's use again their idea. And why it's a beautiful idea? Because if you know where you are going to slip, imagine you have your torus, and I'm telling you the particles at the end are going to slip on this set. It means that all the slip instructions which happen somewhere else, at some time are going to be overridden. So they are just delaying you because you use the slip instruction there, but you know you're not going to sleep there. So you just wasted time. But if you forget about slip instruction outside the set where you're supposed to slip, you're going to go faster for stabilization. So you have to prove it. So, and they did it. So it's all, again, Nicolas and Alexandre contribution that they say, but it's not so hard, but that if you suppress slip instruction outside A, the place where you are going to slip, yeah, then you go faster, sorry. Which means the stabilization time of the system where you cannot slip outside is always less than the stabilization time of your process. Okay? So this means that since I want to study the probability that you stabilize before some time, knowing where I'm going to slip, and this is a process where you have to fix A, actually, that's less, then this implies that this tau A stab less than T. And tau A slab has no slipping there. I cancel all my slip instruction outside. So now imagine you start there, and imagine you start with activated particle only one activated per site of A. What can they do? So I'm jumping a small step, and I say, imagine eta 0 is 1 on A, and it is active. A is the final step. What can it do? Imagine I launch this active particle. On the other places of A, there are particles. So it just wake them up, but they're already active. But when it goes out of A, no slipping instruction. So he cannot sleep there. He goes there, but it's full already. It's full because I have exactly this number of particles active there. So it continues. It can only make a loop. It comes back, and it's the only place is free for him is his own initial place. All the other ones are either active or no sleep instruction. So actually, yes?
You're just moving that particle, keeping all the other fixed still.
I choose this order to move just one
particle. This is due to the abelian property?
Yeah, I make this choice.
Okay, so it's your
choice. And I say, let's move it until it finds back its hole. That's the only hole left in the, as long as I don't move other ones. So it makes a loop. So now my model is a model where I have loops. I throw loops from my cluster, and it's as if I have a density 1 on a given subset of my torus. And there, I want to show that there is activity forever. And this loop, I mean, when you come back, that's the only place where you can slip. If you come back to your place and you find a slip instruction, you slip. Otherwise, you make another loop. But whenever you make a loop, the good thing is that you can slip all the slipping particles inside your cluster. Okay? So I think I have maybe 10 more minutes or 5, because let's say 5. We started late, actually.
Yeah, okay. 7 minutes.
7 minutes, okay. Okay, so those are, let's say, the old ideas. Now, I want to show that my stabilization, let's say, what are the new ideas? And this is a topic that, that Paolo has worked a lot about, is the reinforcement. You want to show that my time of stabilization is exponential in the size. And I'm going to show that small cluster mix in an exponential time and try to propagate this property. So the new idea is that I want to show that T is larger than some geometric random variable exponential of the size of my torus, because it's the size of A, basically. A is the final set where it depends on n, I forgot the dependence. And in this idea, you see that I need to control the whole distribution of this tau, not just the tail. I want to have a stochastic domination this way. And let me, since I have now 6 minutes, tell you the origin of reinforcement. Because I'm going to do something inductive. imagine I have two clusters, C0, C1, of active particle, and I know that this one has an exponential geometric of this parameter, but with this parameter, C0, this one is larger. So this is the time needed to stabilize this region, C0, TC1, bigger exponential alpha C1. And I want to conclude that to stabilize the union is a product. It's a geometric with a parameter product. And you see, it's kind of very intuitive now. Now, I mean, I have the heuristics, and we could make it correct. I let this one stabilize. This one takes a long time to stabilize. But how does it stabilize? The order is that it makes big loops. Each one, I'm drawing the loops starting from some particle there. And some of the loops, if C1 is not too far, are going to cover C1. So imagine, so all active, so you don't need to wake them up. So you wait until this one stabilizes. What you do at this point, I draw in time this way. You stabilize this one, but this one are all slipping. They have stabilized. Send those ones. And the time is so long, and if the distance is short between them, you expect that some loop are going to wake up all the particle there. But so when this one is stabilized, all slip, you have typically, you wake up, all of those ones are waken up. And this is what we call the ping pong rally. They play ping pong. This one, when it slips, has waken up the other one, and the other one does the same thing, wakes up this one, and you keep on doing that until there is a bad event, which is you stabilize one of the cluster, but not enough loop have been sent to cover the other one. Okay, and then you count how many loops I made. So the loop is, let's say, of C0 union C1. I'm just counting one of them. First, the loop to stabilize at the first time, plus if the ping pong worked, you have a second round, etc., until the ping pong failed. And n is the first index such that the ping pong failed, such that you do not cover the kth stabilization of one or the other failed to cover the other. So I would need some estimate to tell you what's the chance that one loop hit a given site or cover. But those are simple in dimension 2. You see, I don't want to write them down. But that's the idea below the reinforcement. Why? Because I have a sum of geometric random variable. But how many of them? I have a geometric sum of geometric random variable. And this one has parameter q, this one has also parameter, I have to be a little bit careful, but the parameter q, I take cluster of approximately the same size. So exponential alpha C1 is what I call minus C1, minus C1 is what I call the parameter of my geometric. And this gives you a geometric of parameter q times q. I'm cheating a lot. What is q? So it's an exponential minus alpha, the sum of the two, let's say, if they are of the same size. So I cheated in many places, but there is one place where I'm sure some of you see a problem. is that the number of loops you make, imagine you make a lot of loops to stabilize, tell you something about the loops themselves. And will tell you if those loops have covered or not. Imagine I need a lot of loops, maybe it means that my loops went right away, far away. If they stayed in your cluster, you would have needed not so many loops. So there is a dependence between the number of loops you're using and the event of covering or not. So N and L are not independent. This was true. A geometric sum of geometric is geometric only if they are independent, those two variables, N and L. So here, there is a problem in the sense that the number of ping pong rally is not independent of the number of loops needed to stabilize my clusters. And the way we overcome this problem is that since it's easy to cover a cluster not too far away, we have loops of different colors. Okay. Loops which are going to serve only to wake up a given cluster at a given step of my hierarchical construction, because I'm going to merge high density drop over and over, and loops which are going to be used at another scale. So, and in this way, I can get some independence. So even if I know how many loops I've used, I don't know the shape of the blue ones, if I use the yellow ones, and things like that. So we have to introduce, different loops. We throw some loops, different loops, according to the step of my nucleation. It looks like a little bit like nucleation. Metastability is present also. So Alex would have spoken better about those type of ideas. But the only thing I remember is that we have colors. And those colors introduce independence. And there the problem is, the proof is there. Geometric sum of geometric random variable. That's it. Thanks a lot.
Okay, let's thank Amin. Any questions, comments, observation? Okay.
But just two basic questions. First of all, maybe I miss it, but the parameter mu c is monotone in lambda, right?
Yes.
Okay, sometime you can use this property.
Yes.
The second is just a curiosity. The same model on a tree has been studied on trees.
Frog model on trees, yes. Activated random walk, I have to ask the experts. I don't know, I don't think so. I don't think so. But, I'm sure it has been.
Okay, I propose to postpone the questions to the coffee break since we are slightly beyond schedule. Okay, so we can thank again Amin. And let's move to the second speaker.
I forgot to say tanti auguri to Paolo.
Sì, sì, è disattivato. No, non è connetto. Vediamo se va. Can you hear me? Not well. Can you hear me?
Think so. Okay. It's time for the second speaker, Michele Aleandri from Rome. He's going to talk about averaging principle for interacting particle systems and beyond.
Okay, let me thank the organizers for this amazing conference. And today I want to speak about a journey from where I started here in L'Aquila, and in the 2016 when Paolo gave the first a seminar at GSSI, and what I've done during my PhD and what I'm going to do now. So the focus of this talk is the averaging principle. So an interesting phenomenon of many real systems is the presence of two mutually dependent slow and fast motion. And the first example was discovered when scientists studied celestial mechanics and celestial motions. And the tool I want to present is the averaging principle that allows us to state that the slow motion, the right time scaling, can be obtained by averaging its parameter with respect to the motion of the fast variables. And this topic was studied also in deterministic settings, so just some references. First rigorous result of Bogoliubov, Mitropolsky, then other works of Sanders, Mounier, and Hasselmann and Kiefer. And then perturbation in real system also can emerge as a contribution of several factors that are identified with random perturbation. So mathematicians, physicists started studying what happens if you add some randomness. So, and some references in stochastic differential equation setup are the works of Kazminski, Vertennikov, Friedel and Benzer, the famous book, and also Kiefer. But today, this is about more or less stochastic differential equation, but I want to present two works in interacting particle system. So, as I mentioned before, Paolo came here and at GSSI, and at that time I was working on another project, but that lessons remained in my mind. So at the end, I changed it completely. I started working with Paolo, and I started studying the work of Paolo and Daniele, and that is the following model, co-revised model with dissipation. So let's start. We have n spins with state -1 and 1, and then we want to define this following process. Sigma n is the vector of the configurations. So you have a transition from sigma I to minus sigma I with rate 1 minus the hyperbolic tangent of sigma I times lambda nt, who is lambda nt is the process defined by this equation. So you have a dissipative term, and plus the contribution of the magnetization of the system. Well, and as a first result, letting n go into infinity, you can prove that the process Mn lambda n converges in distribution to the solution of this system. And well, okay, yes, and so looking at the stationary solution of this ODE, you can observe that the unique solution is 0, 0, and for any choice of the parameters, and moreover, if beta, beta there is less or equal than half over 2 plus 1, the origin is the global attractor of this dynamic, this deterministic dynamic. But if beta is larger than half over 2 plus 1, the origin loses its stability, and then the system has a unique periodic orbit. And so, when beta is equal to half over 2 plus 1, we have an optimum bifurcation. So, at this point, an interesting, so Daniele and Paolo were interested to study the critical fluctuation around the origin for the parameter of the critical parameter. And so, what was the idea? Well, first of all, you have to rescale time and space to look at the critical fluctuation. And the right scaling is the following. So the time is multiplied by square root of n, and space is multiplied by n to the power 1 over 4. And then change coordinate, because you in the deterministic model, you have a path that rounds around the origin, and then the process approaches the origin. So, in a sense, the right coordinates are the polar coordinates. This is rho square, as you can see. And then, with this changing of coordinates, you can observe that you have this infinitesimal generator for the stopper process, because you know that in the origin, so you have some problem about existence if you don't stop the process. But the important thing is that you can see that the leading term here in the infinitesimal generator is this term, the coefficient of here n to the power 1/2 times a constant. And so this tells you that the angular motion is faster than the radial one. Okay? And then here you see the coefficients of the expansion with respect to k. And so that's why it's important the averaging principle, because the angular is faster than the radial one. And then the result is that under some condition, on the initial condition, the process Kn converges in the sense of weak convergence to the unique solution of this stochastic differential equation. And you can notice here, we have the same coefficient here. But there is no theta, because you have to take the average with respect to theta, these coefficients are obtained taking the integral with respect to the uniform measure with respect to theta. So just the integral with respect to theta, the coefficients. Sorry. And so several steps are needed to prove this theorem, but one main point is the averaging principle that they built ad hoc. And what is the main idea? You have two processes here. Let's suppose that xn converges to some process x bar with some properties. And moreover, you suppose that you can control the increment, expected value of the increment of a second process yn. And then this element here, so take a phi is a function that depends on xn and yn that which increments are not big, plus n to some n to n Xi is a positive number. So here you can see that this process is slow and this process is faster. Then this element converges weakly to this one. So where phi bar is obtained as the integral over the theta of the function phi. Of course, phi must be locally Lipschitz and 2 periodic in the second variable. And so this averaging principle is applied in this case because here you have, this is the yn, and this is the theta is the sum between. So let me write like this. It's something more or less. So you have some coefficient, but the heuristic is the following one. And now here I want to state that the velocity, of the angular coefficient does not depend on the ray. Okay, so for each value of the ray you have this velocity. Then I move on to the second model, the model I studied with Ida. And so now you have two families. Let's suppose we have n individuals, and is even. You divide these two individuals into families, and each. Let's suppose that one family of agents wants to imitate the opinion of the other family. But on the other hand, the second family wants to do the opposite of the first family. And so you have these two processes, sigma 1 and sigma 2n, and the opinion of an agent is 0, 1. And let's suppose to take an agent I of family 1, then I have this pen. So from 0 to 1, agent of family 1 changes with rate that depends on the number of ones divided by n in the first family times this function here, phi1, in which and the argument is the number of ones in the other families. And this phi1 characterizes the family in the following way. If phi is strictly increasing, we say that the family is increasing. The family is conformist and wants to imitate. Of course, if you want the rates of jumps of the other family, you have to change here. You have to put M2, and here M1. Okay. So we have these two families that interact, agents that interact each other. And again, taking n going to infinity, we can have the dynamics of the limit. The dynamic of the limit agent in family 1 is described by this rate of jumps. So you have M1, phi1, 1 over 2, M2 for the first family. And now M1 and M2 are the solution to these equations. And this model is linked to the classical Boder model, in which you don't have phi. Or if phi is a constant, you see that this is 0. And so basically you have this. Okay? No. Okay. But now, let's look at the stationary solution of this system. Well, of course, you can have several stationary solutions depending on the function phi1 and phi2. But if you take phi1 and phi2 strictly increasing, basically you have only this point here. Okay, so 1, 0, no, sorry, 0, 1, 1, 1, 1 half, 1 half. And if both of the family are conformist, I mean, so the derivative of this function is increasing, then you have this, so the stability, these points, this is unstable, and this is there are absorbing states, okay, depending on the starting initial condition. But the interesting phenomena is when one family is conformist and another family is non-conformist, in which here you have that 1 half, 1 half is how to say, stable, and you can observe that there are periodic solutions, and okay, you can find a function h such that the solution of the derivative of the function h along this the solution is 0. So, but the microscopic system basically have a trap. So if all the agents have opinion 1 or 0, so the system does not move. So in the 1 half, 1 half is invisible from the point of view of microscopic system if you take a large time. But so the idea at that time was, okay, so that's now what happens if we rescale the time to look what are the fluctuation of our microscopic system along these periodic solutions. And then here you can pass to the action angle coordinates for the deterministic process, and then you have that h dot is 0, but theta dot depends on h and theta. Okay, so as before, going back to the microscopic process, we rescale the time and change coordinate. So the generator of the stopped process of hn theta n has the following form. As you can notice, is very similar to the previous one, but now here we have this function that depends on theta and h. So we have a dependence on the ray in a sense of so the leading term is this one, so the velocity of the angular variable depends on the value of h. And so we were able to prove a theorem of convergence of this stopped process to a solution of a differential equation where the coefficients are obtained as an average with respect to the invariant measure of the dynamic of theta. And now the tool here was the unaveraging principle, but in which we have to take care of the dependence of the angular velocity with respect to the ray. And now, as before, taking the general averaging principle was taking xn and yn processes. Suppose, as before, you have convergence and you are able to control the increments. Then suppose that the generator has this form when you apply with respect to the projection. Of course, you need some hypothesis on f that is strictly increasing, so you are able to count the time needed to make a circle. Then you need some control on the Martigal increment of the second process yn, and then you can prove this result. So you have the convergence of this element to this, where xi bar is obtained as an average with respect to mi x, that is in the invariant distribution of this dynamics here. So this is what, so the previous example was where I started, then this was the topic of my PhD. And now, let's consider a completely different topic. I mean, suppose that you have this system two differential equation, okay, and the stationary solution is the origin again, and depending on the value of alpha, you have these three. If alpha is less than 0, the origin is the absorbing state. If alpha is larger than 0, you have this limit cycle. Then if alpha is 0, alpha is equal to 0 is the critical value for the off bifurcation. And so, as we noticed in the two previous examples, the idea was, okay, maybe we are able to study the fluctuation around the critical fluctuation. Then what happens if to this deterministic process we add a noise that depends on square root of epsilon, and we want to study the critical fluctuation when epsilon goes to 0 of this system. Well, this is an ongoing project with Paolo and Lorenzo Bertini. And as before, well, take first of all alpha is equal to 0, so we choose the critical parameter. Rescale time and space. Here we have different scaling. The space is multiplied by epsilon to the power minus 1 over 2 and not minus 1 over 4. Change coordinates, the polar coordinates, and then you have this following stochastic differential equation, in which we can observe again that the leading term here is epsilon to 1 over epsilon to minus 1 over 2, and again here we have this leading coefficient that does not depend on rho. I mean, this is a constant, okay? And so the idea is that we pretty sure that we are able to prove the convergence of rho epsilon to the solution to this equation, where here you have f bar obtained as f bar is the integral to pi over 2 f of theta sigma. Okay, as before, and the important, so we look only to the value of the sigma in 0, 0. And now this is the so-called this is normal form of bifurcation. So maybe you can start from a system like this, also in Rn. This is in R2, and then suppose if you have a off bifurcation, so all the how much time? 1 minute. Okay. Okay. So this is NAR2, but you can consider a system in Rn in which n, and this system, the Jacobian in the origin, has n minus 2 eigenvalues with negative real part and 2 eigenvalues with 0 real part, and so complex. And then you have a bifurcation. Then you can change coordinate and go to this normal form. Usually you have something else here. And then our goal is to prove the result in this general setting. So complete the study of critical fluctuation around bifurcation in Rn. And maybe, as a parallel of the second example, extend these studies to the critical fluctuation for a Hamiltonian system, or system in which the velocity of the fast motion depends on the ray, okay, in which you need another kind of averaging principle. And I think that the journey ends here, so we can unfasten our belt and go to the coffee break. Okay, thank you. Happy birthday,
Thanks a lot, Michele, for the talk. Are there questions, comments, remarks?
Thank you, Michele. So when I was working with Daniele Tovazzi on the Curie-Weiss model, we met this problem of separation of timescales. So we were looking for an averaging principle, and we had a lot of difficulties to find a result that fit our model. So in a sense, we proved a very simple result. So that was we just had that. In your PhD thesis, you had to prove a much stronger result, much more general result. In the third part of your talk, it looked like the point of having a constant drift, so the dominant term of the fast variable is constant, is related to the normal form.
Yes.
So in a sense, in the Curie-Weiss model, we were so lucky that without knowing that, we were in the normal form, but you were not. So you think that in general, by choosing appropriately a change of variable, you can always reduce to that case. And so, I mean, the averaging principle that Daniele and I proved would be enough for all these examples?
Thank you, Paolo, for the question. Yes, I think that if we start from, from a model, a general model, not in the normal form, with a change of coordinates, we can use your result to prove the averaging principle you found is enough to prove the theorem. I think it's enough because at least for the off bifurcation. I think that if you have an off bifurcation, things work in this way. So no matter the form of the original system, but maybe if you another type of bifurcation, maybe you need another type of averaging principle.
Okay, if there are no further questions, let's move to the coffee break, and we resume at 11. Okay? Thanks again, Michele. Okay, I think it's time to start with the second part of this morning session. We have Irene Grimaldi from Lucca, who's going to talk about networks of reinforced stochastic processes, a complete description of the first order asymptotics. Okay, the floor is yours.
Okay, good morning, and first of all, I'd like to wish a happy birthday to Paolo and thank the organizer for this kind invitation. Okay, my talk is about a model of a system of interactive stochastic processes whose dynamics is driven by reinforcement mechanism. So the first thing I'd like to do is to explain the term reinforcement. So a stochastic model with reinforcement, I mean self-reinforcement, is a stochastic model in which the probability that a given event occurs has a strictly increasing dependence on the number of times the same event occurred in the past. This kind of mechanism is present in many phenomena, in biology, for example, in economics, and also in social science. For instance, if we think about the evolution of a population, typically a newborn is expected, of a certain species, is expected with a probability proportional to the number of units of the same species. For example, if we think about the problem of the spreading, the question of the spreading of some features, behaviors or opinions among the members of a population, of a system, we can have the so-called popularity context, where the popularity of a particular choice causes the new participants to adopt the same choice, that choice. So we have a class of model for several kind of application, for several kind of contexts. And so the different quantities that appear in this model have different meaning according to the different contexts. In the sequel, I'll refer to a sequence of performed actions. Okay, so for example, if we consider the classical, the most famous, the basic, the oldest model with reinforcement, the standard polyurn, we have a sequence of actions, of performed actions. The set of possible actions is only two elements, 0 and 1. The random variable xt represent the type of the action performed at time step t. So xt equal to 1 means that the action performed at time step t is the action 1. And the predictive mean is the random variable zt, which is the probability that xt plus 1 is equal to 1 given the past until t. This predictive mean in the standard polyurn is equal to this quantity. Okay, this quantity represent the proportion of balls of color 1 in an urn, where the updating of the urn consists. Okay, the initial number of the urn, the initial number of balls of color 0 is A0. The initial number of balls of color 1 is A1. And the updating of the urn is that whenever we draw a ball of color 1, we return the ball in the urn together with alpha balls of the same color. So we have a reinforcement mechanism because the probability of observing action j at time step t plus 1 is a strictly increasing dependence on the number of times we had action 1 in the past. In fact, here we have at the numerator the sum of xn, okay, from n from 1 to t. Okay, if we consider the standard polyurn and we consider the random variable zt, we can write the dynamics of zt in this way. Zt plus 1 is equal to 1 minus rt zt plus RT xt plus 1, where RT is the quantity alpha divided the initial number of balls in the urn plus alpha t. So it is a sequence of numbers that behaves like 1 divided t, okay? Starting from these dynamics that we have in the standard Polya urn, we can give the following definition of reinforced stochastic process. A reinforced stochastic process is a sequence of random variables xt with values in 0, 1, and the predicted mean is zt equal to the probability that xt plus 1 is equal to 1 given the past, and zt satisfies the dynamics zt plus 1 equal to 1 minus rt zt plus rt xt plus 1, where rt is a general sequence of numbers in 0, 1, between 0 and 1, in the interval 0, 1, okay? So starting from the same dynamic that we know for the standard Polya urn, where we have RT exactly defined in the above formula. Here we generalize the definition of standard Polya urn, considering an equivalent dynamics, but where RT can be any sequence between 0 and 1. The interpretation, okay, as before, a long time an agent adopts action 0 or action 1, xt equal to 1 means that at time step t the agent adopted action 1, and at each time step t the random variable zt represents the agent's personal inclination towards action 1. That is the probability, okay, the probability that the agent will adopt action 1 at the time step t plus 1. Okay, so zt represents the inclination of the agents toward action 1. We have the reinforcement mechanism because whenever xt plus 1 is equal to 1, we have zt plus 1 greater than zt. Okay, so if xt plus 1 is equal to 1, zt plus 1 is greater than zt, and so we have a bigger probability, a bigger inclination toward action 1. So again, a strict increasing dependence of the personal inclination towards action 1 on the number of times the agent chose action 1 in the past. We call the sequence RT reinforcement sequence, and this sequence regulates the reinforcement in the dynamics of ZT. And RT, okay, if you look at to the dynamics, okay, RT is the weight that that is given to the new information, okay, the new the action at time t plus 1, so the new information that we have at time t plus 1, while 1 minus RT is the weight that we give to the present status of the process Z. Okay? So RT the weight of the new information, and 1 minus RT the weight of the present status of the process. Justification the reinforcement mechanisms in this framework. So as I said before, we can think to the popularity context where the popularity of a certain action causes the newcomer to be more inclined towards that action. Or, okay, we can also suppose that X1 represents the right choice in the sense that it gives the greater payoff, and 0 represents the wrong one. So as a consequence of the reinforcement mechanism, the larger the number of time steps the agent made the right choice in the past, the higher her of his personal inclination towards a future right choice at time step t plus 1. And this is because, for example, higher payoff can be related to better condition of the individual, and so individuals that are healthier, okay, are less likely to make mistakes in the future choice, and so they are more inclined to, again, to repeat the right choice. Or typically, we have also that if the choice are always related to the same action, an agent that earns higher payoff is not inclined to change the action, of course, and so the reinforcement mechanisms in the choice of the action. Relationship with the previous literature. This the definition that I showed before is not new in the literature, because it is already present in the literature as a time-dependent polyurn. In fact, there is a correspondence between reinforced stochastic processes and time-dependent polyurn. In fact, a time-dependent polyurn is a time-dependent polyurn is a polyurn, okay, where the number of volts we added into the urn is time-dependent. Okay, so we have not the same alpha, but we have an alpha t. Okay? If we consider a time-dependent polyurn, it is a reinforced stochastic process where the sequence RT is given by this quantity, okay, where S0 is the initial number of bolts in the urn and alpha t plus 1 is the number of bolts added to the urn at time step t plus 1. On the other hand, if we consider a reinforced stochastic process, it can be seen as a time-dependent polyurn with S0 initial number of bolts into the urn, arbitrary, and alpha t plus 1, so chosen S0, alpha t plus 1 is equal to S0 RT divided the product of 1 minus Rn, n from 0 to t. And if you remember the meaning that we gave before to RT, RT is the weight of the new information, 1 minus RT is the weight of the present status. So this product, the product that we have at the denominator, can be seen as the weight associated to the whole history of the process until time step t. So the notion of reinforced stochastic process and the notion of time-dependent polyurn are equivalent, but they put the focus, the attention on different quantities. Alpha t for in the framework of time-dependent polyurn, and RT if we look at the definition of reinforced stochastic process. For a single process, we have various results, typically above all by Pemantle and Sidorova. But now we are not interested in the single process, but in a system of interacting processes of this kind. Okay. As you know, the stochastic evolution system composed by units of agents that interact are of interest in many disciplines, economic, social economics, social science, and so on, because agents take decisions under the influence of other agents. And the main goals in this framework are to understand, first to understand whether and when a complete or partial asymptotic synchronization can emerge, okay? Synchronization, asymptotic synchronization, okay, then we will give the mathematical definition, but roughly speaking, it is the problem, propensity of different interacting agents to uniformize their behavior. In the case of synchronization towards a certain random variables, the second goal is to get information about the probability distribution of this limit random variable, and also to construct central limit theorems in order to find confidence intervals for this random limit. The third aim, the third goal, is to analyze the interplay between the structure of the interaction network and the behavior of the system, and construct tools for statistical inference on the interaction matrix based on the observation of the system. And then, okay, they are general goals in any model that it is about processes that interact. Specific goal in this framework is to analyze the role of the reinforcement mechanisms in the behavior of a system of interacting agents. Okay, and all these goals, okay, have been subject of papers in collaboration with different co-authors that you can find here, okay? So Paolo Depra, Pierre-Yves Louis, Ida Minelli, Giacomo Aletti, and Andrea Ghiglietti. Now I focus on results in a recent paper by myself, Giacomo Aletti, and Andrea Ghiglietti. Okay, the model. We have a finite weighted graph, the directed graph. V is the set of vertices, the agents of the system. E, the set of edges. A weighted agency matrix, the interaction matrix. So the term of the matrix AHK means quantify the influence that the agent H has on the agent K. Okay, we suppose that the matrix is normalized. So A transpose to 1 is equal to 1, and XTK represent the action performed by the agent K at time step T, okay? And again, we have action 0 or action 1. The dynamics of the model is the following. So given the past until time step T, agent H makes a choice at time step T plus 1 independently of the other agents' choices at the same time step T plus 1, according to the probability that agent K performs action 1 given the past until time step T is a convex combination of the inclination ZH represents the personal inclination of agent H towards action 1. So the probability that the agent K will perform action 1 is a convex combination of all the inclinations of the agents in the network, okay? Where the weight of this convex combination are the terms of the interaction matrix. And ZH, as I said before, ZH is the personal inclination of agent H toward action 1, and this inclination follows a dynamic of a reinforcement stochastic process. So again, we have a reinforcement mechanism on the inclination. The inclination of action H has an increasing dependence on the number of times agent H performed action 1 in the past. We proved the following theoretical result regarding sufficient and necessary condition on the reinforcement and on the interaction matrix in order to have a complete almost sure asymptotic synchronization of the inclination towards a random variable z. In the case of this complete almost sure asymptotic synchronization, we have analyzed the probability distribution of z, in particular the probability that z takes the extreme value 0 or 1 that are called the probability of asymptotic polarization of the personal inclinations on the extreme value 0 or 1. Okay. And then the behavior of the system when the complete almost sure asymptotic synchronization does not hold, and so in particular condition in order to have a partial almost sure asymptotic synchronization. So not a synchronization of all the system, but a synchronization in a cluster, okay? A cluster of agents that synchronized. Okay, the assumption, okay, the weighted matrix, the interaction matrix A is assumed irreducible, so this means that the graph is strongly connected. We exclude the trivial cases, and so we exclude the case in which the initial inclination are concentrated in 0, 0, 0 or 1, 1, 1. Okay, complete almost sure asymptotic synchronization means that the vector of all the inclinations converges almost surely to the same random variable z. So if we prove that when the transpose, okay, of the matrix, because we have, okay, when the matrix A is a periodic, so with period equal to 1, the complete almost sure synchronization holds if and only if the series of the reinforcement sequence is equal to plus infinity. When the period is different from 1, so the matrix is periodic, the complete almost sure asymptotic synchronization holds if and only if we have that this series is equal to plus infinity. So the series of RT multiplied 1 minus RT is equal to plus infinity. What happens when we are not in these cases, okay? So when the series of RT is finite, all the processes Z, so all the inclination converge almost surely, but there exists three positive probability that the processes do not synchronize. So for each pair of vertices, we have a probability greater than 0 that the difference between the inclination of each. Okay, just a reminder that you have 5 minutes. Sorry. Yes, H1 and H2 doesn't converge to 0. Okay, if the matrix A is periodic and we are in this case, so the series RT is equal to plus infinity, and this series is finite. There exists a strictly positive probability that the process does not converge. So we can have the case that the inclination does not converge, but we have a partial almost sure asymptotic synchronization. We have the synchronization inside the cyclic classes. So when we take H1 and H2 in the same cyclic class, we have that the difference of the two inclinations converges almost surely to 0 if and only if the series of RT is equal to plus infinity. So in this case, we can have that also the probability, and I explain in which sense the process does not converge, but we have always a partial synchronization inside the same cyclic cluster. Okay, I have only 5 minutes, so I can show the idea of the proof. Okay, so I jump the idea of the proof. And I want then, I go back to, I want to explain which kind of dynamics we can have when we are in this condition. Okay, as said before, we have synchronization inside the different cyclic classes. So in the same cyclic class, we have the synchronization. The process, okay, if we look at two, now if we call ZTC the component of the process, means that the process ZTC collects one element for each cyclic class, okay? Because inside the cyclic class we have synchronization, so we can look at a single element for each cyclic class. If we look at the behavior of one element in each cyclic class, we have that this process converges almost surely to zero. This means that the inclination for a large T, the inclinations are in the same cyclic class are all near to 0 or near to 1. Okay? And, okay, I jump this. And the number of cyclic classes that are near to 1, okay, is well represented by the unsure limit of the norm of this vector, the norm to the power 2 of this vector. And this random variable is a random variable that takes value in 0, D. Okay, 0, 1, 2, D. D is the period of the matrix. With the probability that we can also assume the values, the intermediate values, 1, D minus 1, okay? And if we are in the case in which n infinity takes a value between 1 and D minus 1, we have an asymptotic behavior, periodic behavior of the components of ZTC, okay? So, in a sense, if we look at the cyclic class, this cyclic class are near to 1 or near to 0 in a periodic way, okay? Okay, so this is the meaning of this result. So there is a sequence sigma t such that this different converges almost surely to 0, and if we are in this particular case, the clock times sigma t are equal sigma t plus 1 is equal to sigma t plus 1. Okay, and so we have this kind of periodicity. Okay, so I conclude because I think that I have finished the time. So this is a table that describes the behavior of the system in any case. So if the period is equal to 1, okay, we have a series of RT finite, then we have convergence, but we have not almost sure synchronization, non-complete nor partial. If the series of RT is equal to plus infinity, we have almost sure convergence and almost sure synchronization. If the period is greater than 2, RT, the series finite, almost sure converges, but not almost sure synchronization. If we are in this case, the series of RT equal to plus infinity and series of RT 1 minus RT equal to plus infinity, we have convergence, almost sure convergence, and almost sure synchronization. If we are in the other case, so series of RT equal to plus infinity and the other series of RT 1 minus RT finite, we have a strictly positive probability that the system doesn't converge, because we have a periodic behavior, okay, of the across the cyclic classes. We have not almost sure synchronization, but we have almost sure synchronization partial, because almost sure synchronization inside the cyclic classes. Okay, so this table collects all the possible cases that we can have for the behavior, the asymptotic behavior of this kind of system of interacting agents, interacting processes. Okay, so I stop here, and if you want, I go to the last slide where you can find the references. Okay, sorry for taking a lot of time.
Thanks a lot, Irene. Can you hear us, Irene?
Yes, but
okay.
Not so good.
Okay, is it better now? Not really.
Okay.
Okay. Okay. Is there any questions or comment? Okay, Paolo.
Thank you, Irene. I have a very fast question. If I understood correctly, here you are considering a network in which the reinforcement is only self-reinforcement. So you are ruling out the mutual reinforcement, right? So that the ZT plus 1 depends on one component.
Self-reinforcement, because we reinforce the action of the same type.
Right,
okay?
Exactly. So so that is the point. I think that if you include mutual reinforcement, the situation can be
I go
different.
to the definition. Okay.
So by mutual reinforcement, I mean that the ZTH depends also on the ZT case of the other components, ZT minus 1 case, right? That you are not, right?
Yes.
So here is not the case. The ZTH is only influenced by the ZT minus 1H. We don't really see, because there is a problem with the computer.
Okay. Because I can't hear you very well, okay? So here, in this ZTH increases, okay? And so the higher the numbers the agent H performed action 1, the higher is inclination toward action 1, because we have a reinforcement mechanism on the same action as extracted, okay? If you look at to an urn, we reinforce the same color we have extracted, okay?
Yes.
The interaction comes from the fact that now the probability that agent K will choose action 1 depends not only on his inclination, but on a convex combination of all the inclination of the other agents in the network.
Okay, so you can really see that this is also mutual reinforcement. So maybe I was wrong in the interpretation. There is mutual reinforcement here, because the probability of having action 1 is really influenced by all the other Z's. Okay. Now,
yes.
So
yes.
Okay. Okay. I just wanted to understand a little bit better the model. Okay. Thanks, Irene.
Yes. So, yes. You have a self-reinforcement on the inclination, but the probability depends on all the inclinations.
Okay. Okay. Thanks a lot, Irene. Let's give last thanks to Irene. Okay, I think we can move to the next speaker, who is in presence. Okay. Ciao, Irene.
Okay. Ciao.
Okay, we are ready to proceed with Paolo Pigato from Roma Tor Vergata. He's going to talk about short-time properties of non-self-similar rough volatility models. You can go, Paolo.
I'm very happy to be here for this conference in Paolo's honor. So thanks the organizer for inviting me to speak here. So in my PhD with Paolo, I worked on some scaling properties of some stochastic volatility models, and today I will speak about different stochastic volatility models, some kind of scaling property, not exactly. So this is the setting. And today I will talk mostly about the work with Giacomo Giorgio and Barbara Pacchiarotti, who are in Tor Vergata in the math department. But here I say this is based also on work with Christian Bayer and Fabian Harang, because this new work is based in some sense to something that I did before with them. So the setting is the one of rough volatility models. So rough volatility, what does it mean? So it's a stochastic volatility model. So here this is a general form for a stochastic volatility model. So it's like, so imagine Black-Scholes model. We forget about the drift from the beginning because it's easier. And we have a volatility process. So in Black-Scholes, sigma is a constant. Generalization of this is sigma is also a stochastic process. And so this is a general form of a stochastic volatility model. Rough volatility means that this process, the volatility process, is stochastic and is rough. Rough in the sense that it depends on a fractional Brownian motion. So in general, if it depends on a fractional Brownian motion, you would say it is a fractional volatility model. But if H, so then a fractional Brownian motion has a Hertz parameter, H, that is an index that represents several things, but one thing is that it represents the smoothness of the trajectories, because this H is for Hertz, but it's also the Holder regularity of the trajectories. So if H is lower than 1/2, it means that the Holder regularity of the trajectories is less than the Holder regularity of the trajectory of the Brownian motion. That would be 1/2, let's say. So if H is less than 1/2, the volatility process is rougher than a diffusion, and we talk about rough volatility model. And so, okay, so now I say sigma t, this process, is a function of this WHT. So here sigma just represents a function. This is an easy way to introduce the type of dependence. It's not the only one, but is one way, and this is what I will assume today. And this WH here, I said this is the fractional Brownian motion with Hertz parameter H. So this is one option, actually, that I say here. In the setting that I'm considering today, often you don't really take the fractional Brownian motion. You take the so-called Riemann-Liouville process, that is this process here. So it's a Volterra process. This integration of this power law kernel against Brownian motion. And these two processes have very, very similar properties. Because actually, if you can write the fractional Brownian motion as a Volterra process, and you see that the kernel has something like that inside. If you simplify it, you find this guy here. Okay, so and there are also other options, but this is the most common cases. Okay, so for this type of models, yeah. Yeah, so W tilde are Brownian motions, and in general, they are correlated with rho correlation. So actually, I will say something more about that later. But yes, this is a way to, so if you have a classic stochastic volatility model, then here you have another stochastic differential equation driven by, say, W. And W is rho correlated with W tilde. Here, to keep a correlation structure, when you put in the stochastic volatility a fraction of Brownian motion, you keep the correlation between the Brownian motion driving the price and the Brownian motion driving the volatility in this sense, in the sense that the fraction of Brownian motion is written as, is derived from this Brownian motion. Okay, so this is now is a recent, but somehow I would say classical result on rough volatility. So it's exactly the setting that I'm considered, that I just explained. There is a large deviation result due to Ford and Chang in 2017 that says you consider the call price that is here given as, so this is S, so this is the stock price, and I write it like this because this is the log prices, and usually you write it like this, so this X is the X that was here. This is the strike price, so I mean, this is just a way to report everything to the exponential. Call price means that you take the positive part of that and the expectation. So this is very similar as to say, sorry, let's say that for this we have a large deviation result in the sense that if you take K with this dependence in T, so the dependence in T has to depend on H. Notice that if we are in the Brownian case, H is 1/2, so this disappears. It doesn't depend on T anymore. Okay, you have this large deviation result. And here also the speed of the large deviation depends on H. If H is 1/2, the speed is T. So in the case H 1/2, this is just Wenzel-Freidling, okay? Because you have here T, and this doesn't depend on T. But if you are in the fractional case, you need to look at these different scalings in order to see a large deviation behavior. And so, I mean, if you are not used to finance, here you would like to see probability that xt is larger than kt, okay, to say this is a large deviation statement. But this is almost the same because when xt is larger than kt, when you take the positive part, this is not 0. If xt is smaller than kt, that's 0. And so if you take, I mean, here, say probability xt larger than kt would be expectation, indicator function xt is larger than kt. So these are essentially the same thing. Okay? So, say that an exponential is roughly 1. Actually, I mean, it's true. This thing is absolutely true. If you go to higher orders, so if you want to see, I mean, this is a logarithmic equivalence. Okay, so if you want to say, okay, this guy here is exponential times some power of t, then those are different. But this is like this. Okay. So these guys, they prove this for WH as general general process, and then notable examples are the ones that I mentioned. This I said already. And okay, and then after this result, there were many results in large deviations for this fractional setting, and all of them, I mean, always you find that you have to look at this log strike. That would mean you have to look at probability that x is larger than something that goes in T like that in order to see the large deviation behavior. Okay, so to prove this type of result, so notice here, this is asymptotic as T goes to 0, so it's a short time result. To prove this type of result, I would say always, but let's say almost always, so I'm sure that I'm not making a mistake. Well, what you do is you prove a small noise result first using some, for example, some large deviation techniques for Gaussian properties, for Gaussian processes. So, for example, you look at something like that. So this is for the model that I showed before. This is a small noise setting in the sense that you multiply all the noises with some epsilon with the proper scaling, because WH has to be multiplied with 2H. For that, then you have a pathwise large deviation result as epsilon goes to 0, and then through some time rescaling, something like that, from the small noise result, you get the short time result, something like that. And that is more relevant in finance because this gives you an approximate price for an option when T is small. Instead, the small noise is somehow less practically relevant. Okay, so, but you can use the technique in small noise, and then if you have a scaling property, you can report it in short time, and that is also relevant if you are an engineer. Say. Okay, so this is to do something like that, you need self-similarity, and WH is self-similar in the sense that if you, so here you see I wrote an equality in law. Here you have fractional Brownian motion. Here I'm multiplying the time with epsilon, or if you multiply the fractional Brownian motion with epsilon to the h, these are in law the same process. This is true for the Brownian motion with h equal to 1/2. Okay, same thing. And okay, from that property and the self-similarity of Brownian motion, because here in the process you have both WH and W. Okay. From that, you can obtain this type of result for these models. So where you have stochastic volatility model where the volatility is fractional, where WH is fractional Brownian motion or Riemann-Liouville process, or actually in this case, very general Gaussian self-similar process. So what we were interested in this work is what about if the fractional volatility driver is not self-similar? Okay, because there are relevant examples, practically relevant, where the fractional volatility driver is not self-similar. So in this case, maybe you can get the small noise result, but then how do you get to the short time result? Okay, because that's, as I said, this is what you want from the engineering perspective. Okay, so for example, two relevant examples that now I will consider is fractional Steinway-Lembeck process is not self-similar, but is used in fractional volatility models. And this is a more exotic thing, log-modulated fractional Brownian motion. And this is the process that we introduced in the work that I mentioned with Christian Bayer and Fabian Arang. And then, so in this, we introduced it in another way, and now in this work we wanted to find large deviation result for this process. Okay, so fractional Steinway-Lembeck here I say why is used. Just actually, this was the first The first rough volatility model used the fractional unstable volatility, and then there are a bunch of reasons why it has been used, so this slide just to say that, and I skip it. Log modulated is the second one, so I said we introduced it in this work. How? So a Volterra process is something like that, is a integral of a deterministic kernel against Brownian motion. So the Riemann-Liouville process that was in the first slide is just, you take K as a power law, okay? And then that's the Riemann-Liouville process. So is this case here. So this works, so what range can you have for H? I said rough volatility means H is lower than 1/2. In general, H has to be between 0 and 1, excluding 0 and 1. So it has to be strictly positive. But many empirical studies point to H very close to 0. So some people philosophically say, H, I want it to be 0, because there is no reason that in data we find 0.02. That means it's 0. So there is some interest in defining rough volatility for H equal to 0, even if the fractional Brownian motion doesn't exist for H equal to 0. So here what we wanted to do is define a rough volatility model with H equal to 0. So what we said is you can take this power law kernel. So this, why it doesn't work for H equal to 0? Because here you have t to the minus 1/2. When you take square is 1 over t, and that's not integrable. The variance is not integrable. So let's take this kernel and add a little bit, something that doesn't change the power law behavior, but that makes it integrable when you take the square. Okay, so just essentially we make a logarithmic correction to the power law. Okay, so this is defined also for H equal to 0 as a process, not as a distribution or something exotic. You can have a process that has roughness 0. Okay, so this is what is called super rough because it's H equal to 0. And so maybe this is a bit more fun. I mean, so let me say this. Not the only reason, but one reason for rough volatility is that you have implied volatility skew that explode as t to the h minus 1/2, where h is this index. And empirically, you want this to explode as a power law. So if h is less than 1/2, this explodes as a power law. There is some reason to try to have implied volatility skew that explode as t to the minus 1/2. Not only explode, but you want them to explode as t to the minus 1/2. So clearly, this happens if h is 0. And in this way, we were able to obtain this behavior. Okay. So here, our framework in this work is this stochastic volatility where sigma is a function of a process that is a Volterra process. Okay, and then here you have some technical conditions, and what we say we don't want to assume self-similarity, and we assume some notion of asymptotic self-similarity. So we take K, this K here. We do a rescaling with the small parameter epsilon, and so like this, and we call this Kn, and we assume that as n goes to infinity, this Kn defined like this, over another small parameter, converges to something that is non-trivial. And so the second thing is essentially the same, but related to the variance. And this is some kind of uniformity. So if the process and the kernel would be self-similar, these properties, they are not true in the limit. They are just true. But like this, we hope that we can handle something that is, in a sense, asymptotically self-similar. Okay. So under this hypothesis, we prove a large deviation statement in small time. So this is more of a, I mean, here you still have path. So let's look directly at the second. We have this family of random variables, where here you have this epsilon and this gamma. So here you have epsilon, gamma, and here you have epsilon. Remember, epsilon is going to 0. So this satisfies a large deviation principle. And here, clearly, when epsilon goes to 0, this goes to 0. So this is a small time result with the speed also depend on this gamma and a certain rate function. Okay, so this is more or less what we want. And this large deviation we can apply to those two fractional Steinbeck and to that other model that I introduced. And the proof is based on a result.
We have a question.
Yeah.
But what is the relation between gamma n and epsilon n? I mean,
if you find, so you use epsilon n in the definition.
But you don't know the limit of the product. So I mean, it goes to infinity, but there is...
They go to 0, both of them.
No, the product gamma n times epsilon n to the -1/2.
This here.
Yes, it goes to infinity. No, what is a curiosity? It was some relation between them.
Yeah, probably there should be something like that. And let's see then in the example in the computation, I mean, they are related, and probably at least for h less than 1/2, they should go to infinity. Okay, so this is the proof is a modification of a previous result of Pacchiarotti and the master student. Okay, so let's see how this works. How much time do you have?
You have 6 minutes.
Okay, so let's see how this works in this case of this modulation of the power law. So we started trying to have a little bit of a more general framework, but in the end is almost the same. So we have the kernel here is given by a self-similar part. So it satisfies this property, and here you have this h. And then this L is a slowly varying function. Clearly this is, as I said, is inspired by this kernel here that I mentioned before. Okay, so this is the L, and this is the K. What happens in this case? So here I just remind the properties. So what is Kn in this case? Kn is this rescaling with epsilon down to K, and because of the self-similarity of this Greek K, then you can pull out from here the epsilon h minus 1/2, the epsilon to the -1/2 goes away with the square root, and you are just left with epsilon h. Then you have K, and then you have L. So now if you write Kn over something, and you want that to converge to something that doesn't depend on n, so what you can do is you divide by epsilon h, and then you divide by L, and since that's slowly varying, it doesn't matter the t minus s. Okay, so essentially the limit of this doesn't depend on t and s, and it's just kts. Okay, hope it's clear. And kts is just coming from the self-similar part. Okay. So this, applying the theorem before, tell us that for this, if you add to this self-similar kernel this logarithmic modulation, you will get the same rate function as the self-similar process, because in that limit you don't have the modulation, and the speed is given by this. So in the speed you have the modulation, and also, then for sure you don't remember from the theorem, but you have to rescale the x with something, and there you have also L. Probably this maybe answers to your question, because here we have epsilon h minus 1/2, and h is smaller than 1/2, so this goes to infinity. Okay. Okay, so essentially you just apply the theorem, and you have a large deviation result for these models. So here I'm saying the result for put and call strikes. Let's just watch the call prices, because it's essentially the same. So you have a large deviation principle. And what is the difference with respect to the one for the self-similar process by Ford and Chang is that, so the rate function is the same, but the speed has to be corrected with this part coming from the logarithm, and also the strike at which you look to. Okay, so L is here and here. And then, okay, now, so this is a short-time large deviation statement. In the previous work with the Bayer and Haran, we had short-time properties, but not large deviation properties, but they were short-time properties if you look at a Gaussian regime in the short time. So these two results are different, but they are somehow consistent, and they allow you to have this extreme exploding skew with this h equal to 0. Okay, so this is a bit more of a financial part. So maybe, I mean, what I want to say is just that somehow you reach the goal that you had from the beginning, doing all that thing. So instead, let's have a look now at the fractional Ornstein-Uhlenbeck. So fractional Ornstein-Uhlenbeck is this process. So its fraction is Ornstein-Uhlenbeck instead of Brownian motion is driven by fractional Brownian motion. With some tricks, you can express this in this way. So the fraction of Ornstein-Uhlenbeck is the Brownian motion minus this guy here. This also has no problem in defining the integral with respect to the fraction Brownian motion, because the integral here is just the time integral. So in the paper, volatility is rough, that started a little bit all this business of rough volatility, they argue that since the calibrated A is small, V and B are similar, and you can somehow interchange it with each other in some heuristic computation. Here, what you're looking is at small time results where you have this stuff here. So since you have this time integral here, you would expect that the small time results with this volatility and this volatility should be the same, not because A is small, but because T is small. And this is actually true. So, okay, so here just maybe essentially I say just that everything works. And indeed, the short time results that you have with a fractional Ornstein-Uhlenbeck volatility is the same that you have with the fraction Brownian motion volatility. So instead of looking at the formulas, I want to show you that actually, you can implement this stuff. So you can compute the large deviation rate function from the model parameter, so this minimum over blah, blah. You can compute it numerically, and you can compare it to Monte Carlo simulation of the model. Okay, so actually this large deviation principle, they actually give you a way to compute option prices. And here you see, so the red line is the large deviation limit, and you see this is for small time, and I put fraction Brownian motion and 2 fraction Einstein-Uhlenbeck. You see as time increases, they get further from the red line, and maybe a small remark is that the fraction Brownian motion get further from the line, from the large deviation limit faster, because this model, the volatility process, is exponential of fraction Brownian motion. So it's exponential of a Gaussian, and we are looking at increasing time. So we look at T0 is the red line, and then increasing time, you have exponential of a Gaussian with increasing variance. So on average, this is an increasing process. You take expectation of an exponential of a Gaussian, and the Gaussian has increasing variance. The expectation is increasing. So essentially, this explains why the blue line is increasing in T, and fraction Einstein-Uhlenbeck has a mean reversion property, so is increasing less than the fractional Brownian motion, and that's why if you with higher mean reversion, the implied volatility is lower. Okay, so this is the references. And
okay, thanks a lot, Paolo. Sorry for being the bad guy who stands up, but we're slightly beyond schedule. Are there questions, comments, remarks?
So you had some picture that you skipped about, I think, volatility surfaces. Can you comment a bit on that to see, I mean, what are the nice features of these models?
These are not volatility surfaces. These are pictures of this implied volatility skew. So this means you have the implied volatility surface, and you look at the money. You look at the money derivative with respect to log strike. So you see how asymmetric the implied volatility surface is at the money, and this. So empirically, this becomes more and more asymmetric as t goes to 0. So the derivative goes to infinity. And here, what is plotted is the derivative. And then so one section like this is this derivative. Then you do this varying h. So you consider this plot of the derivative for a different model. And this is this plot for maybe the most used rough volatility model for pricing. And so now, actually, to explain this, I have a lot of stuff to say. So they all explode, and they explode faster and faster as h goes to 0. But faster in the sense of the power law. But then in front of that, there is a constant that also depends on h. That constant goes to 0. So there is an interplay between that, and unexpectedly, if you plot that, you would expect it to explode faster and faster, but actually, it goes down. Okay. And with this logarithmic correction, this does not happen. So here is this model with the logarithmic correction. this is this plot. But okay, which of the two is closer to empirical data? I don't know. This is just simulations. Yeah. Okay. Maybe probably on empirical data, you cannot maybe make the difference. I see. Not enough liquidity. Yes. Okay. Thanks a lot, Paolo. And okay. Okay. So I guess we have now the last speaker who's remotely connected. So we should switch.
So welcome everybody to this morning session. It's a pleasure to introduce Giambattista Giacomin, who will give a talk on random matrix products and disordered systems. Please.
Thanks a lot. Now I should say it's a pleasure to be here, but it would have been really a pleasure to be there. Okay. And actually, I'm giving this talk, and yesterday, while doing the rehearsal, the sound that comes back to my. Okay, yesterday, no, I have the sound that comes back to my headphones. Probably there is another machine that is open. Okay, I try again. Now it looks fine. Okay, thanks. So I was saying yesterday while I was rehearsing my talk, I mean, you see on this line in the end, when I write down here, l'Aquila, a journey through complex systems, that was written Paolo's 60th birthday. And it reminded me of when at the age of 40, for my birthday, my daughter had given me a gift, like a drawing, like sort of a three-dimensional structure with lots of windows and drawers. And if you would open a drawer, what inside was written 40, and then open a window, 40, then look for another window, 40. So it was very nice, but okay. So this issue of the age will reappear only on the very last slide. It's not even about Paolo's age. So, okay. May I start on the other end my talk? Let's see here. Okay, perfect. So what should you expect from this talk? Well, we talk about the top Lyapunov exponent for a random matrix product in a very special case in reality. So I will have to give some minimal generalities and then the results. I will go through the argument of proof, because actually the argument of proof is definitely close to Paolo's activity. I won't have much time to explain it, but in reality is a hidden problem of speed of convergence to invariant measure of Markov chains. And then I will attempt to explain why all of this has a lot to do with the statistical mechanics of disordered systems. Let's see if I will make it. So I promise I'll be very concrete, and so here is I will just talk about products of these very simple matrices, 2 by 2, IID, in the sense that you see here you have just two objects that are two parameters, epsilon, which is between -1 and 1. Say small, you should always think of epsilon as smaller. And Zn is just an IID sequence of positive random variables with some minimal integrability requirements. So this is going to form a sequence of IID random matrices. And we'll be interested in the behavior as epsilon goes to 0 of the Lyapunov exponent. The Lyapunov exponent is just capture the exponential growth of a norm, the one that you prefer, or the product of n of these random matrices. And a growth, but yeah, it's going to be a growth. It could be also decreasing, but okay, in this case, it's a growth. Behavior, I should have said, probably. There is a very easy exercise that you can do. Of course, if you put epsilon equal to 0, this matrix is diagonal, and if you make products of these matrices on the entry 1, 1, you will keep 1, and on the entry 2, 2, you will get the products of Zn. So the problem is well known. And is an easy exercise to see that the Lyapunov exponent in that case, so L of 0, is just the expectation of log Z if this quantity is positive. Otherwise, is 1, so 0 when you take the log, that wins. So it's a maximum between 0 and expectation of log Z. So in particular, it's just 0 if the expectation of log Z is negative. But you realize soon that epsilon, immediately that epsilon is pathological. If I tell you that this is a case which is non-irreducible, I'm sure everybody understands. And the reason to take epsilon between -1 and 1 is just because we want to work, to stay away from non-determinant zero cases. So I will talk later of the statistical mechanics. Now, let me say that my motivation has been for a long time and still is this old paper of Bernard Derrida with Henkel Hilhorst, singular behavior of certain infinite products of random 2x2 matrices, a rather mathematical title for physicists. But actually in what I will call just simply the H83 now, because this paper was published in 1983, contains a lot of statistical mechanics examples in which this matrix product and Lyapunov exponents come up, random walking random environments, disorder classical is in chain, disorder quantum is in chain, two-dimensional is in model with columnar disorder, and the list continues. As a matter of fact, if you pick up the book by Crisanti, Palladini, and Vulpiani on products of random matrices in statistical physics in 93, the book is 90% of the books is divided into the matrix you saw and the Anderson matrix, and always 2x2. So they are kind of archetype of general phenomena in disorder systems. So back to mathematics, and you will see more of statistical mechanics later on. So here there is again the definition of the Lyapunov exponent. I remind you what the matrix is. And here, let's say I take away the epsilon equals 0 case, so otherwise I take the risk of saying things that are false. Say the epsilon equals 0 case, at the same time trivial, and it is the old problem, as I'm going to explain. So the existence of the limit I write there is a classical fact. Furstenberg, Kesten, Kingman are the big names in this field. And also other facts, like, for example, you don't need to look at a norm of the random matrix. Anything you take, essentially just look at the semi-norm or look at the 1-1 entry or the 1-2 entry. All the entries grow at exponential level with the same speed. So, okay. This is by now well known. And another elementary fact, that's just a game of conjugation. I will not give a detail, but this Lyapunov exponent is even, so you can really think of epsilon positive, a case of epsilon negative, maps into the case of epsilon negative, positive. There is for us an important result by Ruel in 79, or say rather application of an important result of Ruel that says that the Lyapunov exponent is analytic in epsilon. If you stay away from 0, it's real analytic under some conditions, but rather mild conditions. Here I put strong conditions just not to say something which is completely wrong. But so away from 0, there is no singular behavior, but a priori, the Lyapunov exponent is not even continuous at 0, at epsilon equal to 0, exactly by the lack of irreducibility. I mean, the coordinates don't speak to each other if epsilon is equal to 0. But in our case, it is going to be continuous, but you can find counterexample with other matrices to continuity. So now toward the results. So let's see what the H83 were predicting. about the behavior as epsilon goes to 0 of the Lyapunov exponent. To discuss that, unfortunately, here I have to say to do a slightly technical couple of slides, totally elementary in reality. I just need to study this function, the function that associates to beta, the expectation of z to the beta, or maybe it's better understood if you look at it as the expectation of the exponential of beta log zeta. So in particular, the derivative in 0 of this function is the expectation of log z. Remember, z is a positive random variable. And so if you plot the expectation of, so in particular, you know that this function is convex in beta. So the drawing is like that. To simplify, let's think also that the exponential of z to the beta exists for all beta. In this example, is not the case. I mean, you have a divergence, but okay. And in this drawing, I look at the case of expectation of log z negative and the expectation of z positive. So you see the function is larger than 1 when beta is equal to 1. By the way, expectation is equal to 1 at 0. That's always the case. Expectation of z to the 0 is equal to 0. And but actually, there is another solution that I call alpha, and only another solution to the problem of expectation of z to the beta equal to 1. This quantity alpha is what really interests us. I'm going to talk in terms of alpha if you want. And in general, alpha belongs to R, or it may not even exist if there is lack of integrability. And the other point is that it's very easy to see that the case of alpha strictly positive is equivalent to the case of alpha negative. It's just that because you can factorize Z and you find a matrix which has the same shape in the sense that you have just exchanged the order of the lines and you have exchanged Z in 1 over Z. So, well, that's just, you can write it as a metric conjugation, and the Lyapunov exponent doesn't depend on conjugation. And so except for this Z that is in front, that is a scalar that you compute. The message is simply, we can just stick to alpha positive, which is the case of this drawing. The alpha negative is equivalent. And but of course, in discussing that, I left out the case of alpha equal to 0 because the derivative in 0 could be 0, and there could be only one solution to the equation exponential z to the beta equal to 1. That's what I would call the case alpha equal to 0. And if I tell you that is going to be a critical case, it's kind of evident in many senses. So, okay. So I hope, yeah. Now I define alpha, and now I can tell what Derrida and Lilhorst forecasted in '83. Their work is mostly about the case of alpha between 0 and 1, so also between -1 and up to 0. And they predicted that as epsilon goes to 0, L of epsilon behaves like a constant, which is as explicit as it can get. It's not a number. It depends on invariant measures of certain processes, and times epsilon to the power of 2 alpha. So there is this fractionary behavior because alpha is between 0 and 1. And of course, it's a non-analytic behavior at the origin, in contrast with what Ruel proved for epsilon different from 0. And I will not talk in this seminar about the case of alpha larger or equal to 1. There is a conjecture, there are some results, I will just say a word, but the problem is essentially rather open. And what is, and this also in partly proven, what is expected is that you have a regular expansion in power of epsilon square before getting to the singularity epsilon to the power 2 alpha. But unfortunately, this regular expansion kind of hides the singularity and is more difficult. at least we didn't have a good idea up to now how to study it, and not even the Reed and the Lorst were able really to have a convincing arguments about the singularity in that case. So, and then there is the case of alpha equal to 0, that corresponds to the case of expectation log z equal to 0, and there is there, for example, the work of Neununzen and Luke. These two authors wrote a lot about this case, a little bit after the Reed and the Lorst, and they predict the behavior of L epsilon like going to 0, but much slower, just like 1 over log of 1 over epsilon. So, and of course, all of these are physics claims and without conditions, essentially, on Z. Actually, it's not completely true. Already, Derrida provided a counterexample to the prediction if Z is too bizarre, so to say. And so, in any case, the results I will prove will have always as a condition that Z has a density and more than that. But okay, the issue of generality is definitely there. So here is the first result that dates back by now by 5 years. Most of the results I'm going to talk about are in collaboration with Raphael Greenblatt. This one was also with Giuseppe Genovese. And in that case, we attacked really the original work of the Reed and the Lorst. So alpha between 0 and 1. And the case of the drawing that I showed you before. And the support of, we put the assumption that the support of the law of Z is bounded and bounded away from 0, and that Z has a C1 density. And in this case, we are able to prove the H83 prediction and identify precisely the constant, which is what was predicted by Derrida without surprise. And I just mentioned quickly that a student of mine obtained the result for the alpha larger or equal to 1, but they are not complete and singularity is not really identified, but it's a difficult problem because the singularity is hidden behind this regular expansion. Okay. Then here is a much more recent work with Raphael. Is about the case alpha equal to 0, the critical case. We did this result not only for completely supported random variables bounded away from 0. We just demanded that the expectation to Z to the delta is finite for delta in a neighborhood of 0. We always ask that Z has a density, and actually that the density of the log Z is uniformly order continuous. So we have weakened the C1 assumption, but still some regularity is there. And then in this case, we are able to prove this very strong result, surprisingly strong. I will explain you later why it's really kind of perturbing in its precision, and that the Lyapunov exponent behaves like a certain constant K1 divided by log of 1. What was expected was predicted by physicists, but this result is really much more precise. I will come back to that, and I wanted to stress that this constant K1 and K2 are as explicit as they can get, but they are highly non-trivial. They depend on the details of the distribution of Z. They're not universal. I want also to say that in one of the papers of Neununzen and Luke, assuming a spatial law of Z and doing some exact computations and then some more physical arguments, they get to a result which is equivalent to this one. They write it in a different way, but we are actually, well, it's not that important. their case is not sufficiently regular to be treated with our methods, but that's a technical detail. Let me talk for just a couple of slides about the proof of these results, because this really is in a sense close to a part of the activity of Paolo. So even if a priori looks something really different. If you want to work with the Lyapunov exponents, you really have to deal with the classical Furstenberg representation formula. And this is just given in terms of the invariant probability of a Markov chain. So what do you do? So you start with a point. We are just making products of positive matrices, so we can keep in the first quadrant. If you're not in the first quadrant, you're going to enter the first quadrant. Actually, first or third, but they are equivalent. So let's think of that. We start with an X which has positive entries, and you can apply the random matrix. You apply the random matrix another time, and we are just interested actually in the direction of his. It's going to be clear in a second why of this iterative process. But it's also clear that this is a Markov chain because you are just. I mean, at each step you're just making your previous state, making your new state to be a function of your previous state and of an independent randomness. Which comes from the matrix. So again, this is in drawing. Here is your initial vector. You apply the random matrix. You change the direction of the vector. You change the length, but and then you keep going. And that is a Markov process too. But also, if you simply look at the process of the direction, so which is just in this case a process of angles between 0 and pi over 2. You have a Markov chain. And actually, if you know the invariant measure of this Markov chain, you can apply that's what is needed in the Furstenberg formula, and you have your Lyapunov exponent. So in the end, you just need to find the invariant measure of a Markov chain, and as easy as that. So what is this Markov chain? Actually, the Markov chain, you can write it very explicitly. Look at the action of your matrix on a vector of the form 1x. In any case, x is the tangent of the angle on the two-dimensional plane. So the tangent of the angle is transformed, x, is transformed simply in z times epsilon plus x divided by 1 plus epsilon x. So it's z times a rational function, and then if you're able to find in these new coordinates, if you want, your Lyapunov exponents looks like that, but it's actually it's definitely simpler to work with the random variable x, which is a tangent of theta. And your Markov chain is just given by this transformation, and is a Markov chain on 0 infinity. But I want to do, in a sense, even worse than that, because it's actually even easier and more intuitive to work with the logarithm of x. Again, I'm just playing among spaces. If I take the logarithm of x, x was between 0 and infinity, I'm going to be between minus infinity and infinity. So this is what I'm going to do in the next slides. So again, I say it's possibly more clear if you work with the Markov chain Sn, which is the logarithm of Xn, and I call it Sn thinking of a random walk, because actually if you write that, you do an elementary computation, you see that Sn plus 1 is equal to the logarithm of Zn plus 1 plus Sn plus this thing in green here. And the only thing that you should keep in mind of this thing in green here, that is essentially 0 if the argument is between log epsilon, a very negative number, and log epsilon, a very large number, positive number. And actually, if you plot x plus h epsilon of x, you get that. So this really means that the Markov chain behind this random matrix product is just a random walk in a box Here, this is just the identity function if you don't go too far from the origin. But in a box with a repulsion on the boundaries, if you try to go out, you are really pulled back very quickly. Of course, the increment is log of Zn. And the case of log of Zn negative is different. So the case of alpha positive is different from the case of expectation log Z is equal to 0. Because in the first case, so the case alpha equal to 0, in the first case there is a drift to the left, and but you have a repulsion, you cannot go out of the box, and okay. But it looks like an extremely simple problem, and but actually it's not that easy to find the invariant measure with a precision that it will give you information on the Lyapunov exponent. And what Derrida and Delors came up as an idea was to see this problem as two separated problems. That is, you could, for example, recenter your box around log of epsilon, so very far to the left, and send epsilon to 0. And in that case, you find just a random walk with increments log of Zn, and with a wall on the left, with a wall, a soft wall at 0. A soft, but not that soft. I mean, you really killed exponentially if you try to go out of the region. So you're going to tell me that this walk, this half problem, looked at from here, is certainly positive recurrent because its drift is toward the left, and there is this strong repulsion from the right. You cannot go. So very easy to see there is only one invariant probability. By the way, I forgot to say also in the original problem, in this problem here, there is only one invariant probability because you have whatever you have in the middle. In the middle, you have a Markov chain which is strongly constrained in a finite region, even if very large but finite. So if expectation of log Z is negative, you have only one invariant probability. But if the expectation of log Z is 0, S is going to be null recurrent. Again, that's not too difficult to show. I mean, you have a random walk with mean 0 increments, and well, okay, there is a wall, but doesn't do much damage from the point of view of the recurrence. And we know, therefore, that we have only one up to normalization invariant measure, which is not a probability. Let me say, but you're going to complain, maybe the expectation of log Z is not interest to us because I say that it's the same as expectation of, sorry, if the expectation of log Z is positive, is not interested because it maps to the expectation of log Z in the original problem negative. But I point out that so that case is, of course, if your drift is toward the right, and if you have a repulsion here, and there is not such a term here, you're going to have a transient walk, and but one can show that there is an invariant measure too in that case, and even if this third case is a priori not interesting, if you think a second, it is interesting because. To fully solve this problem, you do not have to solve only the problem on the left. You have to solve also the problem on the right. And the problem on the right is the drift that goes the wrong way if the expectation of log Z is negative. So you have to deal with both cases. And actually, the idea of the H83 is now, if you have these two invariant measures, in some way, put them together, and that will be your invariant measure. So let's be again very concrete, and we just do the drawing in the case of alpha equal to 0. So expectation of log Z equal to 0. You have nobody's surprised now that the invariant measure should look something like that. I mean, you have just a random walk, a center random walk between two, which is constrained to stay essentially constrained to stay in a box, in a large box. So the invariant measure is, let's talk about invariant density, because in any case, under our assumptions, the invariant measure has a density. So the invariant density is just going to be flat, and if there is something fancy, it's just at the boundary. And you see, and actually you can be very precise about this, how to sort of guess what is this invariant measure by using the invariant measure of the two problems that you have solved around log epsilon and around minus log epsilon. And so you take those two problems that you have solved and you match them in a region which is close to the origin. I hope I explained a little bit how you build this Derrida loss guess. Of course, if there is a drift to the left, the measure is not flat. You're going to have a bump toward the left and a decay toward the right. But okay, I decided to present only this one. And it is at this stage that the mathematics sets in, because, and this is actually a general problem in Markov chain. And if somebody gives you something that should be close in some sense to the invariant probability of your problem, this gamma epsilon. And but in a sense, you just know that that this is true, because if you apply the one-step kernel to gamma epsilon, you get something which is sort of similar to gamma epsilon. Can you say that gamma epsilon is close to the invariant measure, the invariant probability that I call nu epsilon? The first reaction is to build a counterexample, and then no. Okay. But actually, here is a way to go that uses really profoundly the structure of this problem. You see, the first step is actually, I have no time to explain. The crucial point is to say which norm we take to measure the distance between measures. But okay, let's say these double vertical lines here denotes a norm, and certainly I can write this by triangular inequality things, which is simply I've just added gamma epsilon, to which I applied the one-step kernel, and I have subtracted it. And here I wrote nu epsilon, to which I applied the one-step kernel. Nu epsilon is invariant, so it is nu epsilon. But if you're able to show that if you found a norm for which that is contractive under the one-step kernel, this is what I'm writing here, and what we could do for alpha between 0 and 1, then from this inequality up here, you immediately derive this inequality, which is a magical inequality in a sense. Because you see, on the left, you have an object on which, of which you know only the existence, which is the invariant probability. But all the rest that is in the formula, in particular, all the right-hand side, just contains the guess that you have that is totally explicit. Okay. And so this is the basic idea that we have used to prove the result. Fortunately or unfortunately, all this took lots of pages to really control this difference here in particular, and in a sufficiently fine way to control the Lyapunov exponent. But okay, it worked out. And here, to make things more complicated, is that this delta, this gap, this delta is positive only if alpha is between 0 and 1. This delta is actually 0 if alpha is equal to 0. And then you have to do actually a final analysis and work in a slightly different way. And okay, and you figure out that this delta, even in the alpha equal to 0, is really not 0. It's something that goes to 0 with epsilon, but you can put something that is still positive. You have still some there is a gap that is shrinking down, and therefore that you have this constant here that is really not infinity also in the case, but it's just exploding. But then if you are very good in controlling the one-step estimate that is here on the right, then you might be still in in business to do your result. And we could do that, and that's I won't say more. And but I've talked with lots of people in Monte Carlo Markov chains. It's this business to discuss of whether because essentially what it looks like what we used is something that is familiar in that context, and it is to a certain extent, but other things are extremely much specialized to the structure of and norms that appear in the product of random matrix. So in the context of products of random matrices, notably the so-called Hilbert matrix, Hilbert metric or Hilbert distance. Okay, I won't say anything more about that. And I really would like to spend the rest of my seminar in talking about the statistical mechanics aspects of the question. About this part, there is a work with Francis and with Raphael Greenwald, and then the rest is about ongoing discussion with Raphael, with Orphe Collen, with Bernard Derrida, with you and you. And so I will just try to explain everything in the context of a very, very easy case that I thought it was completely understood. And I kind of discovered it is not. It's just a one-dimensional easy model. It seems a little bit ridiculous. So just a chain of length n. So you recognize it here with interaction J and with a random magnetic field, external field Hj here. Okay. I assume a minimal familiarity with of people in the audience with the easy model. So the Gibbs measure is exponential minus this energy, and I have to normalize it by the partition function, and much of the information on my system is in the partition function, of course. And here is the point is that is an easy game to show that this partition function can be written as a product of 2 by 2, sorry, as a trace of a product of 2 by 2 matrices. And if you just extract this scalar term here, okay, what is written here is the well-known easy one-dimensional easy matrix, easy transfer matrix. I have just written it in a non-symmetric way by extracting a scalar part. And it's not really me already, or the physicist, the Derrida, Crisanti Vulpiani, all the people always do that. And it becomes in the form of the matrix I have presented to you. You see, there is one here, and if you put epsilon equal to epsilon to the minus 2j, then you have epsilon here. And if you put z equal to exponential minus 2 times the external magnetic field, here you have your z. So this is exactly the matrix we have talked about up to now. And therefore, the free energy, so the limit as n goes to infinity of 1 over n log of zn or of the expectation with respect to the disorder of this quantity. This limit is almost sure in L1, it's self-averaging, there's no problem. So this just becomes J that comes from here. Expectation of H that comes from the law of large number of this quantity here. And then the rest is the logarithm, 1 over n, the logarithm of the trace. Of course, trace or norm, or any entry of the random matrix all behave the same at the exponential level. And so you find the Lyapunov exponent computed at epsilon, which is equal to exponential minus 2j. And therefore, that abstract singularity problem that we have studied as epsilon goes to 0 is actually the problem of one-dimensional, of understanding the free energy of the one-dimensional Ising chain for fixed disorder and strong magnetic, ferromagnetic interaction. So from the next slide, I will just talk about the expectation of H equals 0 case for several reasons. So this term disappears and things becomes even easier. So there will be much to say about expectation of h equal to 0, different to zero, from 0, but let's be serious and say something concrete. So the free energy of that chain is just J plus the Lyapunov exponent, and therefore if we apply our theorem, it is, I just wrote the result that we have proven. And but there is a more fancy way that, to write it that shows how unreasonably precise is the result. Because, of course, since the error is exponentially small, I can develop this term to all orders. So we have the development of the free energy for J that goes to infinity to all orders. We are just lacking the term beyond all orders. And okay, let's just. So this, you would have the reaction, so remarkable. So you know everything about the easy model in this one-dimensional easy model, in this limit as J goes to infinity. And actually, not really, maybe not yet, but no. And so for that, let's look at what the physicists claim. And in this field, there is actually a result, an approach which is called sometimes Madas-Gupta-Fisher renormalization group, or real space renormalization group for disordered system, or infinite disorder fixed point. Okay, in any case, this model enters a large universality class in which there should be a certain precise behavior that I will try to give you a hint that has motivated us enormously. And so we never really fully understood it, but I mean, the motivation gave us motivation to prove certain results, and in other systems, in polymer systems, and notably. So, but so let's see what happens for this. If you have an intuition about what happens for J large for this chain of length n that goes to infinity first, think of J large but finite, and n enormously large, just equal to infinity. So you could think that in this limit, for example, as a first naive strategy, that the spins trying to align to the random fields. If that happens, if all the spins are put with the same sign of the random field, then this will give you a contribution to the energy, which is the sum of the absolute value of the random field. But then the interaction, there will be lots of broken bonds. So with the interaction, sometimes you will gain J's, sometimes you will lose J. So in general, you will have a contribution of J square root of n. And actually, from this strategy, you will find an extensive contribution to the energy, which is proportional to the expectation of the absolute value of the external field. But there is a much more efficient strategy. Just do not flip. Stay equal to +1 with your spins all the times, or -1 all the times is the same. Because in that case, you will gain J times n from the interactions, because they are all satisfied interactions. And well, from the external field, you have bad luck. I mean, you are summing up 8Js and you don't find an extensive quantity. It goes like square root of n, because the H's are centered. But it's in any case much better because J is large, you see, with respect to this previous case. But you can do better, and this is the old Imri-Mas strategy. Which is to say, stay essentially all the times +1 or -1 and switch wisely between, rarely and wisely, between +-1. And actually, what the Imri-Mas strategy tells you, switch on stretches that are of length J square. And it's not difficult to understand why. Because, okay, in this way, since you have not broken many bonds to leading order, you are going to gain in any case Jn. That is in any case there. And then you have broken some bonds, but actually in these long stretches here, the things that are long J square, you are going to gain from the random field because you are going to gain or lose square root of j. Square root of j squared, so j. J times a random quantity that could be positive or negative. So in this sense, I'm saying if you choose wisely these stretches in such a way to pay for what it costs to go to make the switch from one region to the other one, then you might be able to get a contribution which is extensive and more than what you get from the trivial strategy of staying constant all the time. So for Imre and Mats, this was sufficient. But actually, okay, this is a slide that I will show you only if there are questions. You would have to explain how to be wise, how to choose these stretches, and yeah, I have no time to explain all the subtleties and to explain the Dan-Fisher procedure of renormalization. But I wanted just to say that that is actually something that is known in stochastic analysis. This thing was known before the work of Fisher, which is in the 90s. Jacques Neveu and Jim Pittman in 1989 came out with the notion of gamma extremes for Brownian motion. So what are the gamma extremes of Brownian motion? Of course, you cannot talk about. Oh yeah, you could, but you cannot talk about all the maxima and all the minima of a Brownian motion. Kind of a very rich set, and so you want to do a coarse graining. You want to look at the essential one, and you can, and essentially the point of gamma extreme is simply that think of the thing like that. Start from the origin. Here I do not start from the origin, but start from the origin and wait for the first time that your Brownian motion goes down of at least gamma, and then after that, or goes up, is the same, is symmetrical. The thing say goes down, and then after that, look for the minimum after that. The minimum which is before the first time that the Brownian motion goes up of at least gamma again. Okay, sorry for this very synthetic description of a beautiful construction, but in that way you really can make a coarse grain of your Brownian motion into a sequence of alternating gamma maxima and minima, and describe your system in terms of the distance between these extrema and their heights. And the point is that Neveu-Pittman could compute exactly the joint distribution of the distance and their heights, and this is actually a renewal process. I won't say more about that. But what I want to say more is that people had already realized that this limit distribution, no, it is not a limit distribution, sorry. It's the distribution of Neveu-Pittman connected to this renewal process of gamma extrema actually coincides with the limit distribution found in the renovation group procedure of Fisher. And in particular, there is rigorous work by Dimitrios Seliotis in the case of really Brownian motion, and of Alessandra in the case in which the Brownian motion has a drift. So I won't say more about that, but I just want to say that the strategy of that Fisher is going to tell you is for your easing system. Here you're going to say, you're talking about Brownian motion. Well, actually what I plot is not a Brownian motion, is a random walk in reality, if you look carefully. And so if this random walk is just a random walk that you have formed with your increments that is given by the magnetic field, which is centered. So see these Brownian motions just as the sum of the Hj. So it's just a representation of your random field. When you have a descending region, you say that your spin have to stay negative, equal to -1, and you have when you have an ascending region, your spin have to be equal to +1. So this is the smart way of choosing the excursions of connected to the Imre strategy, and Okay. Of course, it was very quick, but it was just to give a guess of this idea of that this in configuration for Fisher and collaborators is totally determined by the environment in a very precise way. And actually, using this idea in particular, they compute the free energy. Actually, they compute the free energy to the first order expansion. And you can recognize that this result is much poorer, even if in agreement with our result, at least if you choose kappa 1, the constant equal to 1/2. And this was very troublesome for me, because kappa 1 is a complex constant. It's really non-trivial. It depends on invariant measures connected to the distribution of J, and Markov chains appearing in the process that I explained you before. And okay, you can make it equal to 1/2, but it's artificial. And there's something that is really not really sounding correct in all of these. And then here is kind of a way out, and that's the last technical thing I'm going to present, is that in this context you can find an exactly solvable model if you scale down the disorder. The scaling down the disorder is what, in particular, Francesco does all the time with these intermediate limits. And maybe we'll do it also in the talk that he's going to give, I'm not sure, but possibly. So you take the variance of Aj, which goes to 0, I call it delta, and it's going to be sent to 0. Scale also the length of the system with delta, so just change the variables like that. Choose also your interaction in such a way that it contains data. You have to scale all the parameters in such a way that your partition function converges to a non-trivial limit. And actually, this non-trivial limit is very simple. Is a Gibbs measure of a continuum easy model. You see, this S of t here were the sigma j before, but it's now just a Poisson process that switches between -1 with a rate exponential of -2j. And this is the integral with respect to a Brownian motion. And of course, the Brownian motion is just our random walk associated to the sum of hj's, the analog at least. And okay, this is done rigorously, even if in a two-dimensional context, but this result can be extracted by the work with Francis and Raphael. And even if it was in a very implicit way, very difficult to read, is already in the McCoy-Vu paper of 69. And there have been lots of contributions after that. And the magical thing of this model is that the free energy, I don't give you the specific formula because I don't want to introduce Bessel functions, but the free energy in this model can be computed exactly. And in particular, its asymptotics is absolutely consistent with the same, you see the same shape of kappa 1 divided by j plus kappa 2, plus an exponential correction. And in particular, the constant kappa 1 here is 1/2. And so I very strongly believe now is more than very strongly because we have partial results, we have files written, and I hope there will be some concrete results soon. I think that for this continuum model, one can really prove that in a precise sense, in a rigorous sense, the Fisher renormalization group claim. And that would open up this thing then to do it really for the original model. And this has not been done. I mean, it's something on the way, let's hope. And here are the final considerations. I wanted to say that the Fisher renormalization group approach makes sense to leading order, but just to leading order. Remember that there is this unreasonable result with the Lyapunov exponent that you get all orders. For a continuum limit version of the easy model. And the results coming from the Lyapunov exponents computations are extremely much more consistent, but extremely much more precise. Really dealing with the discrete system is still a problem because it seems like a secondary problem, but I would like to say that the point is that the fluctuation theory of random walks has not been developed up to now to the point of dealing with gamma extrema. And is a beautiful field, very technical, but very passionate. I'm pretty sure that if one can develop everything, one will refine these two, will find in that context these two constant kappa 1 and kappa 2 that appears in the Lyapunov response. Must be, otherwise, but I don't know. In any case, this is just wishful thinking or science fiction for the moment. And I just want to say that troubles are extremely much more substantial if the expectation of h is different from 0. And I spared you that. I want to say that the physics, not even, now for me it's clear, since I have proven some rigorous results, and since we control the finite energy also in that case extremely precisely, that the physicists don't have a clear idea either of what is going on, and this is remarkable. What can be easier than the one-dimensional easy model? Okay, it's disorder. And then if you're passionate from the random matrix viewpoint, we have worked with, just in the case in which H, which is log Z, has a density and with some more technical conditions, but the results should hold in much greater generality. It should hold, just assuming that the random walk generated by the random field Hj, so the log of Zj, is not lattice. But our techniques do not really work. We don't know how to do that. So we need some regularity. And okay, with this I'm done, except for okay. I was choosing from the, I don't have extremely many pictures with Paolo, but a few I had. But in the end, I decided that maybe this picture of that was already of 12 years ago of Joel's 80th birthday. Joel with 8 of his PhD students. Celia is an intruder, no? But the other ones are really all students. There is Paolo, there is Amin, and there. And I couldn't think of a better omen to a certain extent. Okay, thanks a lot.
So thanks a lot for the very nice talk. Are there questions or comments? Yeah.
Ciao Giambattista, it's Francesco. Just a question. So about the remark you did about doing this theory of gamma extrema for random walk. You mean that, well, in that case, I don't expect that this will be exactly a renewal process. There will be some dependence, perhaps, between the pieces, or you think it's really a renewal process? But anyway, my question was, if it's approximately a renewal process, I mean the steps, the pieces between these maxima are roughly independent. What is the meaning of the two constants, K1 and K2? Can you give them some meaning or some interpretation based on the random walk? What do they represent?
Okay, thank you, Francesco. Yes, this is actually in these last months I was thinking several times that I mean, it would have been very nice to discuss together about these issues that which you worked a lot of time. So okay, there are several ways to answer these questions. I just choose one. So there is not exact independence because of overshoots before the limit. In the limit, I do believe that one recovers the Neveu-Pitman distribution. On the other hand, these constants should come from properties of seeing I don't know, of a random walk constraint to be positive in a certain sense. No, not in a certain sense. It should be really coming from that. Except that the constants appears in the random matrix products in a way that is not that. So there is something that so I don't have any heuristics up to now. I was really hoping to get at least a heuristics. I probably didn't think enough, but once you really do this procedure, do it rigorously, you can gamma extrema, at least in the case in which the increments are continuous, for example. The discrete case is more problematic because there are too many things can be equal, but I do believe that the things can be done, but I don't know how to answer. I still cannot match the constants, but I haven't done it.
Okay.
I don't know if this answered your question.
Yeah, no, okay, I got the idea. Just one quick remark, but so you believe that for the discrete model, the prediction by Fisher is wrong? There should not be a half, but K1 somehow in their expansion. So the expansion they write is really for the continuum model. If you do it really for...
exactly.
Yeah, it will not be a half, the right constant.
That is not that I believe. That I know, because the expansion for the free energy
is exactly it's exactly the Lyapunov exponent. So you already know that it's not one half.
So
okay,
that I know.
Yeah, sorry.
But now if I want to match with the trajectorial behavior, I need to understand the strategy, and I believe that the strategy is I think that Fisher is correct, but one has to redo it for random walks. And the curious thing is that essentially what they do is we substitute a random walk with a Brownian motion, but that step is not completely trivial.
Okay, thank you.
So I hope.
Sorry. Are there other questions? Okay. Then thanks again to Giambattista.
Thank you.
We switch to a talk in presence. Okay, so we can continue. The next speaker is Giovanni Conforti from the École Polytechnique, who will speak about coupling by reflection and propagation of semi-convexity along Hamilton-Jacobi-Bellman equation.
Okay, thank you very much, Alessandra, for the nice introduction. And well, it goes without saying, I'm very, very happy to be here and to talk a little bit about something I've been discussing with Paolo over and over. So how convex are things, how concave are things, how curved are things, so on and so forth. And to motivate what I'm gonna talk about today, just to mention, I would just like to mention a very old but still very interesting result due to Braskamp and Lieb, which is about the ground state of Schrödinger operators. The statement is pretty simple. If your potential V is convex, is omega convex, and then you take the operator, well, Laplacian over 2 minus V, then the ground state, which is the principal eigenvector, is omega to the power 1/2 log concave. Okay, and this is the famous paper where this was proven first. What do you mean by omega convex? Sorry. The second derivative is bounded below by omega, and I really stress that omega has to be positive here. So this is a beautiful result. It has plenty of consequences. And the key tool to prove this, maybe, well, don't know. The key tool, something is frozen. Yeah, maybe. Okay, yeah, got it. The key tool for proving this, at least that's how the original proof goes, It's a well-known functional inequality which is called Prokop-Leindler. And Prokop-Leindler, it's all about the fact that if you take a log concave random vector and then you take its first marginal, then this is still a log concave probability measure. And why this has a lot to do with the ground state? Because you can easily represent the ground state via this kind of Feynman-Katz formula. Essentially, you take the expectation of the exponential of minus the time integral of your potential, computed on a Brownian motion shifted by x. Then you take the log of this. You add a constant that doesn't really matter because when you talk about spatial gradients, this term vanishes immediately. You let capital T to infinity, and this thing should converge, actually is the ground state. So how do you use Prokop-Leindler here? Well, suppose now V is convex. Then you discretize this time integral in time, and then you are computing the expectation of a discrete version of this under a Gaussian measure. This is a very big log concave vector, and you can interpret this x here as a conditional expectation if you wish, and then you just apply this as a black box, and you get the result. Okay, so this is how the original proof goes. Okay. Actually, I will talk in a second about another proof that people in control know very well, and it's much easier than this one. But the question I had for some time is, okay, what happens if V is not convex? Because of course you see that this proof completely breaks down because there is no substitute or surrogate for Prokop-Leindler when the original vector is not log concave. So there is no perturbation of Prokop-Leindler that tells you, okay, you're not really log concave, but almost log concave, then your marginal must be almost log concave. Up to now, this still doesn't exist. So there is one way and here I will not talk about stochastic control, but I just want to introduce a perspective that people in control would have about this problem. So if you take this quantity, which is the one that converges to the ground state up to a linear term in time, well, this quantity, if you call it phi 0 capital T of x, you realize immediately that this is just a solution to a nonlinear PDE, so the Hamilton-Jacobi-Bellman equation, and in particular to this very simple AJB equation. So you have derivative in time plus the Laplacian plus your source term given by the potential, and then you have the nonlinearity is minus 1/2 gradient of phi square. And of course, the link between this and that is just that this formula here is the Hopf-Lachs or Feynman-Katz, if you want, way of representing solutions to this very simple Hamilton-Jacobi-Bellman equation. Well, when you look at these things, if you ask people in control, suppose that V is convex, is it true that phi 0 is convex? They will tell you, yeah, sure, and it's a one-line proof that doesn't require anything like Prokop-Leindler. Just the usual thing, you take the same, you take convex combination of controls, and it's really simple. So this is a bit encouraging because from the control viewpoint, seems to be much simpler. And also you realize that, okay, you want the estimate of you want to estimate the Hessian of this guy. So it is all about estimating uniformly in time, this is the difficult part, the Hessian of solutions of Hamilton-Jacobi-Bellman equations. So that's the only thing one has to do to get, if you want to bound from below the Hessian of the log of minus the log of the ground state, it's all about the Hessian of this object. And then you can say, okay, now there is a huge amount of literature about Hamilton-Jacobi-Bellman equations. I open the books, I take out the estimates, and I'll definitely find one. Actually, and this is where it gets tricky, because for an equation like this, of course, there is a huge literature about semi-concavity of solutions. This is what you usually easily get in control problems by the variational formulation. There's tons of techniques to get semi-concavity estimates. But this is precisely what you don't want here. In fact, you would like estimates that work when V is as widely convex as you want, like exponential to x to the power 2, something like this. And in that case, you know that the value function phi 0 cannot even be semi-concave. So you really have to turn your eyes from semi-concave estimates and look for semi-convexity estimates. And these, of course, people in control know that these ones are harder because parabolic irregularity plays against you instead than in favor of you when you write second order conditions. Of course, you could, if you want to relax the convexity here, you can get away with parabolic regularity, but then you have to impose much more. So you need to ask that the potential is maybe Lipschitz and with globally bounded Hessian from above and below. And of course, this is really what you don't want to see here, because what we hope is that it's only the convexity of V that somehow plays a role in the convexity of phi 0, and nothing more. So one would not like to see that the fact that V is also a bit concave helps this guy to be convex. This is really not what you would like to see. Also, if you impose this, you rule out, so you exclude already the Braskamp-Lieb result is not covered by this by this assumption, because you need to impose more. So, I mean, I've been bothering many people in control, and as far as I know, there is no general condition that is more general than the convexity of V that tells you, okay, solutions to this guy are uniformly semi-convex in time. So if you know a condition, I'll be happy to hear it. But as far as I know, even so, nobody, I mean, I couldn't find it, and all my colleagues with whom I discussed, they couldn't point me at something concrete. Okay, so well, one has to start somewhere. So let's take a simple setting. I just take my V to be the sum of two contributions, V0 and V1. V0 is as nice as I want, so strongly convex, but nothing more. Okay, smooth, this I don't care, but strongly convex. And V1 is Lipschitz, so I take a Lipschitz perturbation of something convex, and the Hessian of V1 is not too bad. So it's bounded below by something negative. So overall, this object is not going to be convex. And the hope that I had was, okay, what I would like to do, I would like to bootstrap bounds on the Hessian of phi 0 by studying the SD, whose drift is the gradient of Hamilton-Jacobi Bellman. So the idea I had, I mean, the hope I had is that if this SD is sufficiently ergodic, then yes, I can obtain some bounds on the Hessian of V. So why this? Well, there is so this SD is obviously connected to the Hamilton-Jacobi-Bellman equation, because in the control interpretation of the problem, this is just the optimally controlled state process. So there is an obvious reason in control to connect this to the Hamilton-Jacobi-Bellman equation. What is not so clear right now is why these being strongly ergodic will imply that the Hessian of V is bounded below. And that's what I hope to be able to explain in the slides that come. But the first question is that, is this really a good idea? Because when you want to study the ergodicity of an SD, well, it's all about some kind of convexity in the potential, and this is what I want to prove in the first place. So I'm not so sure. But there is a way out. There is a way out, because nowadays people know how to obtain some rather precise exponential convergence results for these SDs, assuming that the potential is okay, convex in some sense, but you don't need to know any pointwise lower bound on the Hessian. So even if you don't have a pointwise lower bound, as bad as it could be on the Hessian of phi, but if you have some kind of integrated convexity condition, then you still know that this is exponentially ergodic. And my favorite technique for doing this is coupling by reflection. So it's definitely, so of course it's not me who came up with this. So coupling by reflection works under mild assumptions of phi that I will not detail here. I will come back to this slightly later. I just want to give you the construction. So of course it's a coupling. So the idea is that you will get ergodicity by the fact that the two processes will get closer exponentially fast. Okay? And how does it work? So suppose you want to couple the process starting from x with the process starting from x hat. Okay, the process starting from x, you take your favorite Brownian motion and you solve for the corresponding SDE. There's nothing to do. And the other one, you do something slightly non-standard. So instead of using what you usually do when you have strong convexity on the potential, you just inject the same Brownian motion in both equations, and then it's fine. But in coupling by reflection, the second process has a different Brownian motion, b hat, that you obtain by taking the increments of b, copying the increments of b for the hat process in directions that are orthogonal to the difference between the two SDs, and swapping the sign, flipping around the increments that are parallel to their direction, joining the two processes. So the direction under which x hat sees x, I will denote it by ES. It's a unit vector. And this is the formula. So it's identity minus 2 times the parallel component along the direction. And okay, to be sure that this is a coupling, you have to verify that b hat is really a Brownian motion, but this is straightforward from Levy characterization. This is an orthogonal transformation. So this b hat is a Brownian motion. So in fact, x hat has the law of the diffusion started at x hat. And what I find really, so okay, this is the picture. I wrote B just to say that B is a general drift. So suppose this is x at time t, and I want to discretize my construction in between t and t plus h. So this thing here, the blue arrows are the drifts. Well, there is nothing to couple there. They are deterministic. And this is the Brownian increment related to x, the red one. So I decompose it along the orthogonal and the parallel component. The parallel component, I just move it to the other process, and I keep it as it is. And the parallel component, I flip it around. So I change the sign. That's how it works. And the whole idea is that you use the reflection to overcome the local lack of convexity in your potential. So I think the message is that it's an easy way for probabilists to picture what analysts always say, that when you add the Laplacian to somewhere, everything will get better. And actually here you really see that that's the case. So it's really because you have a Brownian motion that you can overcome the lack of convexity in phi, the local lack of convexity in your potential, and still get exponential convergence of your SDE. So I will not, of course, go into the details, but if you like it, there is this very nice paper where it's explained that under very mild condition on your drift, you have an exponential contraction result in a norm that is actually equivalent to Wasserstein 1. But for us, what it's important is that under mild conditions that I will make precise in 1 second, the difference between the two processes is exponentially small. You pay a multiplicative constant, but fine, I mean, you don't really care, this is super uniform. And the important thing is that this is really a W1 result. So in the sense that it's not in total variation, so you really can bound the difference with the difference of the initial points. And this is crucial if you think that then you want to take derivatives. You would like, in the end, you want to divide by something that looks like this, okay? Okay, I said you need very little to be able to conclude about this. And I don't want to get the details, but I just want to point out that in the problem I am looking at, just by knowing that our potential was the sum of a convex and a Lipschitz contribution, without having to use the fact that I have a uniform lower bound on the Hessian of V, I can decompose my phi into two contributions. One is strongly convex and one is Lipschitz. Still, I know nothing about the global Hessian of phi, but this is enough for me to conclude that I have such an estimate. Okay? So this is the first interesting part. And I mean, transferring from my hypothesis on V, the fact that I can have this decomposition of phi, so one term eta strongly convex and one term strongly Lipschitz, this is easy. it's rather standard in control. It's not difficult to obtain this. So what is easy is transferring convexity, strong convexity and Lipschitzianity from the potential to the value function. This is easy. What is less standard is having the uniform lower bound on the second derivative. Yes.
Sorry, there is a question.
Excuse me, can you say something about lambda?
Lambda is explicit in the paper, but it doesn't have a, so the expression is a bit involved, but it's fully explicit. And in my case, it's some lambda, but it is explicit. I just don't want to write it here. It is explicit. I can. All right. So and now, okay. Now, what are we going to do with this? Now, I want to get the second derivative by this argument. So the idea is that, of course, what I'm going to do, I'm going to study the process, this process. So the difference between the minus the drifts, inner product with the direction under which one process sees the other. Why so? Because, of course, at s equal to 0, this is exactly what I need to estimate if I want to get convexity bound for phi. So this is the process I'm going to study. And if you translate this in control, I'm going to study coupling by reflection on the adjoints, not on the states. It's on the adjoint processes. So okay, then you do Ito, you use your Hamilton-Jacobi, and you easily get the dynamics of the gradient of phi computed in x and in x hat. And the interesting part is that you have a part that contains the gradient of your potential, which is somehow nice because we want to use the properties of our potential when you do estimates. And then here you have a part which involves the Hessian of phi. So you really want to hope that this part doesn't pop up in the estimates you're going to do, because this is what you want to estimate. But for our purposes, the important thing is that this is just a martingale. We don't care about what it is so far. And I think what is really nice is that is the dynamics of the direction of ES. Because what is really striking is that the dynamic of ES, if you do Ito, it doesn't have the DBS term. And if you think a bit about it, this is exactly a special feature of coupling by reflection. If you consider another coupling, this wouldn't be true. So it would be true for coupling, but synchronous couplings cannot be of help in this context. And of course, ES is a stochastic process, but its Ito differential doesn't have the DBT term. And okay, if you want to visualize this has to do a lot with the fact that the reflection happens along the parallel component to the vector to ET. And you see, if you move the points along this direction, well, okay, you change the distance, but you don't really change the direction under which one sees the other. And this is actually this is actually the reason behind this. And this is really crucial for us, because if I had to pick up some dB term, then when you take the Ito differential of this, well, you have a covariance term that will involve the Hessian of phi, and then I'm done, because the Hessian of phi, I don't know anything at the moment. That's exactly what I want to study. So it's okay. Now I guess I'm almost. So I just want to show briefly the calculation that justifies the final estimate. So this is the process I'm interested in, and I compute its Ito differential. And I know, because ES has no DBT part, that I can do it as if they were not stochastic processes, so there is no covariance term. So I know the dynamics of this difference, I know the dynamics of this. So I start writing the terms. I have the difference between the gradient of the potential, scalar, and the direction. This looks good. Then I have a negative term, which also looks good. This is the projection on the direction, on the orthogonal direction to ES of the difference between the drift. I take its norm and I square it. And then I have a martingale. That's all what comes from the Hessian of phi terms. Well, now, so the negative term, I can throw it away. This is okay. And I can use the crude convexity bound that I have on V. So I know that V globally has a bounded Hessian from below. The bound is negative, but I have a bound. So I can do this. And then I take expectation, I kill the martingale, and I'm just left with this. And now the nice thing is that I know that this is small. And so I can use my coupling by reflection, and I know that this, so I know that this difference is exponentially small in time. And that's it, because, and this is, so when I evaluate in 0, let's forget about the derivative, this is the gradient of phi in x minus gradient of phi in x hat times x minus x hat divided by the norm of x minus x hat. So this is exactly what I need if you want one-sided convexity bounds. So that's why it's extremely important of having W1 convergence, because I want x minus x hat here. If I had something else, I would be lost. And I divide, I integrate my estimate. This is, of course, very integrable in time. It's exponential. And then you get the result that, OK, it's exactly what you want. So if V has the nice decomposition that I discussed before, then the Hessian of phi 0 is uniformly in time and space bounded below by a negative constant. It can only be, it cannot be positive, of course. But the bound is uniform in time and space. And in fact, as a corollary, you get that the ground state satisfied log Sobolev. So the probability measure that you associate to the ground state satisfies log Sobolev and also HWI, which is a more involved functional inequality. And the funny thing is that you cannot apply like Bakry-Emery criteria to the ground state simply because it's not log concave. But thanks to this estimate and some other tricks, you can get log Sobolev. And in fact, this calculation carries over to wilder perturbations than Lipschitz, and also to some mean field models. And I guess, this is pretty much what I wanted to say. And maybe I would like to conclude by a couple of slides about what you could do with this and what people have already done in other contexts. So one of the messages that I would like to convey is that coupling techniques are useful to estimate the derivatives of nonlinear PDEs. So of course, couplings are widely used to study convergence to equilibrium of Markov processes. So it's about Fokker-Planck. It's about the long-time behavior of Fokker-Planck. So this is a linear PDE. And this is what we do all the time. But actually here, I used it for once to study Hamilton-Jacobi-Bellman. So couplings are actually nice tools to attack nonlinear PDEs, not just linear PDEs. And in fact, for as long as gradient estimates go, in my case would be Lipschitz estimates on phi, this has been understood in the PDE community. So in the PDE language, there is a technique that is called the doubling of variables techniques that is mostly used, I would say, to prove uniqueness in Hamilton-Jacobi-Bellman equations, but it's actually really equivalent to coupling techniques. And this nice paper, Porretta and Priola actually made really the connection between coupling techniques and the doubling variable method, and they used it to obtain Lipschitz estimates for a large class of nonlinear parabolic equations. So not only Hamilton-Jacobi-Bellman, also you can have these PDEs that come from games. So Isaacs, Hamilton-Jacobi, I don't exactly recall. I mean, there are many PDEs that you can treat with these methods. And actually, there is also this very nice review by Pertam and Fournier, where, in a PDE fashion, they rewrite the coupling method in a PDE fashion. They just say, hey, look, it doesn't only work for Fokker-Planck. But this is as long as gradient estimates go. And this is, so if we go back to the little problem I discussed, this would be when you couple the X processes, the states. And I guess what could be interesting to develop in the future is that if you look at the construction I did, I analyzed coupling between the adjoint, so the gradient of phi. And this is what allows you to estimate the Hessian. If you only work at the X level, first order, you can estimate derivatives. But if you want to estimate the Hessian, you need to work at second order. And now I switch a bit to the control language, then you have to work with the adjoint process in the stochastic maximum principle. And that's what I did in a very, very simple setting, but it works. So with Alessio, we are trying a bit to figure out if there is a general methodology for second-order derivatives. And then the second message I would like to convey is that, yes, okay, semi-concavity is crucial in control. It allows you to do tons of things. But semi-convexity is just as fun, and you can do much with it. So one thing you can do, you can study, you can imagine a bit from what I discussed, you can study the exponential ergodicity of solutions to stochastic control problems. So the idea is that if you have to go from A to B, this is your basic control problem, well, you are going to do so by spending most of the time near some equilibrium state. This is called the turnpike in control language, and you want to show that, yeah, actually you are exponentially close to the turnpike for most of your time. This is a control version of the classical problem of how fast a Markov process converges to equilibrium, and you quickly realize that for that problem is not semi-concavity, it's all about semi-convexity. Then you can also use it to study the exponential convergence of some numerical algorithms that pop up in entropy regularized optimal transport, like for those of you who like these kind of things, like Syncor algorithm and his sisters and brothers. Because there you often have the problem that these algorithms are fine if the marginals are log concave. If they're not concave, what do we do? And you quickly realize that it's all about the fact that you cannot use Prokop-Leibler for non-log concave distributions. And the last thing you can do that I would like to mention, there's a very beautiful theorem by Caffarelli that tells you that if you take a strongly log concave probability measure on RD, then there is a Lipschitz map that maps the Gaussian onto this probability measure. But once again, this only works for strongly log concave probability measures. And recently, there have been some improvements of this. So in Caffarelli's theorem, the map that you use is the Brenier map, is the optimal solution of optimal transport. And people recently realized that, okay, but maybe we don't want this one, we just want a map. So they construct some interpolations where, I guess, they put some Laplacian in there, and they hope they profit from the regularizing property of the Laplacian to construct Lipschitz maps, even between the Gaussian and something which is not log concave. And this is, of course, extremely useful because you can transfer all functional inequalities you have from the Gaussians onto the other probability measure. And even in that context, you realize that at the end of the day, it's all about estimating the Hessian over Hamilton-Jacobi. It's even simpler in that case because, well, I don't want to enter into detail. And these techniques can be of help in generalizing Caffarelli to other settings. And okay, this is as much as I wanted to say. So tanti auguri, Paolo.
Okay, yeah. So thank you. Are there questions? Maybe a fast question? Yeah, of course, Paolo.
Thank you, Giovanni. Very fast and actually a small detail. So when you state your ergodicity estimates for the diffusion, so you decompose the drift into terms, okay?
Yes.
And for the second term, you only need Lipschitzianity.
Yeah.
So no bound on the second derivative.
That's the strength. That's the strength of coupling by reflection.
That's fantastic.
Yeah. Yeah, but that's not me, of course. But that's and you use it to bootstrap the one you want. Yes.
And this is crucial for your.
So actually, I know that. Okay, for the thing I told, yes. In fact, I'm trying to do something more direct, where I don't go through this intermediate decomposition, and I have hopes. But for the moment, yes. But I think at the end of the day, you can do even better than this.
Thank you.
You can actually no. Okay, I don't want to say because it would be long.
There is another question.
Okay.
So there is another question from Giambattista. You can switch on the microphone.
Yes, can you hear me?
Yes.
Yeah, okay, yeah, no, this is a very basic question. I mean, one of the powerful applications of the Prokop-Leibler inequality is the fact that one can get sub-Gaussian estimates on, for example, on marginals of the measure that you brought at the beginning of the concave measures and so on. So I was trying to understand from your talk, do you get also that type of strong estimate in your generalized context?
Yeah, so I don't know if I can be super precise, but in general, I think one of the messages that what you usually do with Braskamp-Lieb that requires low concavity, you can often do without by using this method. So I guess that if there is some estimate that requires Braskamp-Lieb, there is hope to improve it by means of these ideas. This is exactly, for instance, in the applications I mentioned, this is exactly, sorry, this is my timer. This is exactly what we do. So here, typically, and even here, at some point you apply Braskamp-Lieb on a low concave probability measure, and we steer away from that by using these ideas of coupling. So maybe, and I guess this could be used also to say something on the tails of the ground state if you wanted. I didn't think of it, to be honest. But I don't know if this addresses the question. But if there is a specific problem, I can look into it and say if there is something I would be able to say.
No, I was just wondering because I mean there are a series of problems that one can deal with in interacting spin systems when the potential is convex and one gets sub-Gaussian estimates, but even with small perturbations, sometimes it's been done, but the results are poor and so on. So it would have been natural for me. I mean, for me, it's not the first time I'm asking myself this question whether your approach says something about those cases, but.
Yeah. At the philosophical level, it's exactly the same problem. And so there's something that works super well for convex potentials, and you just change them a little bit and you know nothing. And I tried some way out. So I would be kind of hopeful, but then one has to see with what you have to put your hands on if it works.
Thanks a lot.
Thank you for the question.
Okay, thank you, Giovanni. I suggest to postpone the other question to the coffee break. Let us start. The next speaker is Francesco Caravenna from the University of Milano Bicocca. He will speak about renewal theory, disordered systems, and stochastic PDEs.
Okay, thanks a lot, Alessandra. Thanks, the organizer, for this very, very nice invitation. It's a pleasure to be here. The slides and the talks will be in English, but just for 1 minute, let me speak Italian. It's just feel more comfortable. Ho incontrato per la prima volta Paolo nel 2003 e quando ci ho ripensato è stato un aneddoto divertente perché, vabbè, parentesi, sono 20 anni fa. Questa cosa mi provoca un po' di perplessità, soprattutto a pensare che Paolo in quel momento era più giovane di quanto sono io adesso e questa cosa mi sfasa un po' le percezioni soggettive, ma lasciamo stare. È stato divertente perché ho incontrato Paolo nel 2003 perché dovevo incontrare in realtà per la prima volta Giambattista, che era il mio relatore di dottorato. Io ero a Milano, lui era a Belluno, Padova è più o meno a metà, ci siamo trovati a Padova e lui ha chiesto a Paolo se stava all'ufficio, quindi in qualche modo ho incontrato Paolo un po' per caso e sono stato a Padova un po' per caso e in modo anche di un po' inaspettato, qualche anno dopo mi sono effettivamente trasferito a Padova, dove sono stato circa 5 anni e se ci ripenso veramente durante tutti questi anni estremamente belli, ho incontrato, penso, la maggior parte delle persone che sono qua adesso. E fa una certa impressione non solo rivederle, ma pensare che queste persone erano studenti di laurea, studenti di dottorato, postdoc, colleghi junior, senior, e quindi c'è veramente questa dispersione di età molto molto bella e insomma fa una certa emozione ripensarci.
E devo dire che Paolo mi ha veramente introdotto nel mondo dell'università italiana, mi ha come dire, insegnato a insegnare, nel senso che ho fatto veramente i primi corsi fianco a fianco a lui e abbiamo scritto insieme un libro, è stato estremamente generoso a condividere le dispense che aveva scritto, che poi sono diventate un libro, e abbiamo scritto anche un articolo insieme e insomma last but not least mi ha anche aiutato a fare camminate in montagna e tuttora uso con grande piacere il materiale che lui e Francesca mi hanno regalato per il matrimonio, quindi insomma ho ripescato questa fotografia che non è stata scattata ieri ma 11 anni fa, non ci credete ma insomma è così, quindi vabbè è con una certa emozione che dico grazie Paolo e adesso provo a passare all'inglese, sarà un pochettino più facile. Okay, so the plan, this is a relatively short talk, so a bit less than half an hour, and then I decided to talk about a lot of things, because in a sense I will not be able to get into any details, and then I will try to give an overview about 3 seemingly unrelated areas that have been central to my research in the last 10 years. So renewal theorem, disordered systems, and stochastic PDEs. Many of you have heard some of these stories in previous talks. Sorry if you get a bit bored, but hopefully it will be a bit less technical and a bit more comprehensive, so it will be hopefully a bit more fun. And the main references are these 2 papers that I wrote in collaboration with my friends and long-time collaborators, Rongfeng Sun from Singapore and Nikos Zigouras from Warwick. We met, this picture was taken last week when we went together to Oberwolfach and we could meet after nearly 3 years, so in person for the first time, so it was nice. Okay, so let's start. Renewal theory, I have four slides for each point, so I should be a bit relaxed. Okay, what is a renewal process? By the way, just by coincidence, I will talk about renewal theory that was somehow central to Giambattista's talk, and I will mention Feynman-Katz at the end, but this was not made on purpose, so which is a bit connected also to Giovanni's talk. So a renewal process is just a random walk with positive increments, nothing more than that. So you can see I have the increments, I call that xi, they are independent with the same distribution. I take them integer valued, say aperiodic, even though my drawing is periodic, of course, sorry. So you see, I call S1, S2, S3 the position of the walk of the renewal process, and x are the increments. Now, renewal theory focuses on one question. I just take one point n far apart, and I ask what is the probability that my process visits this point, exactly this point. And you know, it's not difficult to write a formula for that, because if you want to visit this point, it will need some number of steps, so you just disintegrate sum over the number of steps k that you need to reach this point. You sum over all k, and you get what is called the renewal function, or Green's function if you prefer, but it's the same thing. Okay, it's the probability that you just visit one point. And the question is, what is the behavior of this as small n goes to infinity? This is a very classical result by Erdős, Feller, and Pollard. It goes back to 1949, and it's not surprising in a sense. The limit of that is just the inverse of the average step length. If you have expectation of x which is equal to 4, which means that on average steps are length 4, so one site out of 4 is visited by there are no walks, so for large point you expect that with 1/4 probability you will visit. It's not difficult. It's not difficult to guess it using the law of large numbers. To get the precise results requires a bit of ability, but it's very, very somehow classical. Now what is interesting, and the direction in which we go, is that this is also true when the expectation is infinite. So the right-hand side is 0, and this is, of course, a very poor result, in the sense that, you see, just says that when the expectation is infinite, the renewal function goes to 0, but you would like to know the speed at which it goes to 0. And for that, you need some stronger assumptions. So let's assume that the probability tail of x decays polynomially with some exponent alpha between 0 and 1, so that the mean is infinite. And okay, you can also add, like in Paolo-Stokes, some slowly varying function, logarithmic correction, but forget if you don't like. And then it's been a classical result again by Garcia-Lamperti 62. Well, you know, the mean is infinite, but if you look until n, the truncated mean, when you just take just the minimum between x and n, this is finite, you can compute, and you see it's n 1 minus alpha. If you have alpha, here you have 1 minus alpha. The heuristics is more or less this. The result is correct with a sharp constant, but you need some assumption when alpha is less than a half. Curiosity, it's not true in generality. This is a local assumption, which is stronger than that. Okay, I missed one constant alpha, I guess. No, but that's okay. And just to mention that recently, together with Rondone, we could give necessary and sufficient condition for any alpha. But this will not be the object of my talk. Okay, so this is the key problem, somehow renewal theory when the mean is infinite. But for today, I will talk about a more extreme case, the case of ultra heavy tails, alpha equals 0. So I would like to take the step distribution of the random walk, which decays as 1 over n. Of course, I cannot do that because 1 over n is not summable, but I can, okay, I could put, like Paolo did, a logarithmic correction to make it summable, but this is not what I want to do. I want to do something more extreme. I introduce a truncation, a time horizon capital N, and I say I want a probability that decays like 1 over n, but only until capital N. And then I renormalize. And then just to be clear, the sum of 1 over n is the harmonic series, so it's just essentially log n. So you should imagine I have a step distribution which is 1 over small n on a time interval capital N. And then you consider the renewal process, which is now a triangular array. So I have a red index capital N, which is the time horizon, where I truncate, and then I have the small index, which is the step. I ask exactly the same question. This is the renewal function. Is the probability that the renewal process visits n, and again, is the sum of the probability that you visit in k steps. I leave some space because, for the sake of generality, but actually for important reason, I consider a slightly more general question. I introduce a possible exponential weight, something to the k. Theta is a real parameter. If you set theta equal to 0, this disappears. It's the renewal function classical. Otherwise, you have a small parameter to play with. Okay, so what is now the result? Well, if you compute the mean of this step distribution, you see n cancels, and you get n over log n. So it's very extreme. The horizon is capital N, and the expectation is n over log n, so almost n. So you expect, by just analogy, that the renewal function is the inverse of the mean, that is log n over n. And our result is that this is the case. In a sharp sense, there is a prefactor which depends on small n and capital N. It's an explicit function, okay, at least if you are not too small. And this function is really explicit in a sense. You see there is gamma function, Euler's constant, and that's it. So this is the first result that I present, and the idea is you can do renewal theory also in this discrete case. The result is not unexpected because it's just the inverse of the mean of the step, but there is this prefactor which is sharp, and you can compute it. And if you are curious, I will not go into details. This comes from the fact that this random walk converges when you rescale it to a Levy process. The Levy process is explicit. You can compute the density even. It's one of the few cases. It's called Dickman subordinator. And then this g theta is the renewal function of the limiting process. So just to give you an idea, so there is like a scaling limit, and then you can compute things. So this is the first result I wanted to present. Now, forget it for a moment. We change completely subject. Yeah. Gamma is Euler's constant. Euler's mascheroni, the same in Giambattista-Stokes, is the asymptotic difference between the harmonic sum and the logarithm, 0.5 something. It's actually a derivative of the gamma function, Euler capital gamma in some point, I don't remember. It's a constant, explicit. Small gamma, you mean? this is Euler's gamma function, and this is the Euler-Mascheroni constant. So, okay, the disordered systems. I will talk about what is called the directed polymer in random environment. This is a disorder model in statistical mechanics that very roughly you can describe it as a random walk which interacts with a random potential, a random medium, in a Gibbs way. This was introduced in the 80s to describe actually not polymers but interfaces in the Ising model by Imre Spencer, and then there was a very influential paper by Erwin Bolthausen. And in the last 25 years, there has been a revival in the interest of that. It has generated a stream of literature because there are many interesting phenomena that appear, localization, super diffusivity, KPZ universality class. This I will not go into detail, but just say that these have been a bit at the center of several areas. So there has been a lot of study, and there is a very nice monograph by Francisco Metz, and it's also an occasion to give a tribute since he sadly passed away this year. So what is the model? I need two ingredients, a simple random walk on ZD. Attention, this has nothing to do with the random walk of before. Simple random walk on ZD. We'll be interested in D equal to. And this is the first ingredient. The second ingredient is the medium, which is just a family of independent Gaussian, called, say, disorder, one for each space-time point. You should imagine that different colors mean different values. So this is a realization, okay? And then I introduce a coupling, a Hamiltonian, that is the simplest you can imagine. Given a random walk trajectory and a realization of the environment, I just make the sum of the omegas along the random walk path. And since we took this Gaussian, this is also Gaussian, and it's a Gaussian with variance n, because we have n steps. Okay, now I will not define the model, I will just define the partition function. What is the partition function? Actually, partition functions, because they depend on the time horizon and on the starting point. It's just the expected value in blue with respect to the simple random walk of the exponential of beta times h. Now, this expected value is really overkill because a simple random walk on a finite time horizon has a finite number of steps. So this is just a sum over all simple random walk paths that start at z, and you take the exponential of beta times this Gaussian random variable. So you see it's a sum of the exponential of Gaussian, sum of log normals that are correlated, however, okay? And actually, it's convenient to normalize and divide by the expectation. So you see that this is a normal, so the expectation of e to the beta Gaussian is e to the half beta squared the variance. So what we do is we divide by exponential to 1 beta squared the variance, just to have expectation 1, nothing deep. And now, my point, the only point I want to make about this model is that there is a deep but hidden link with the renewal function with ultra-heavy tails that we saw before. It's not apparent. Where is alpha equals 0 here? And now, where is the link? So this is the plan. Well, I'm interested in studying these partition functions. What are partition functions? They are random variable. Because we only take expectation with respect to random walk, but the omegas, the Gaussians, are still there. So it's a function of omega. I didn't put it, but so this is a random field in space-time, a family of random variables that depend on omega, and they are actually stationary. Actually, you see that if you just move z, for instance, you are just translating, it's stationary, it doesn't depend on the distribution, so they have the same expectation, and I normalize it to have 1. So to understand how they behave, natural thing is to compute the covariance, because they are not independent. And it turns out that there is an exact formula for the covariance that I now write. I will not prove it. So the covariance, if you take two partition functions for simplicity of the same time duration, but with different starting points, the covariance has this formula. There is beta square. Beta is the coupling constant, you see, this one, beta square. Then you have Q, which is just the random walk transition kernel. The probability that the random walk at time n is in z. So you see, in time 2L, it must be at z minus z prime. So this is the distance between the starting point. And then there is a last term. The last term, which is where the substance is hidden, is an infinite sum. Actually, it's a finite sum of n terms, but when n goes to infinity, it will become infinite. And it's 1 plus the sum of the hit kernel at 0 times beta square, plus a sort of convolution of the hit kernels in time at 0, each by beta square, plus etc., etc. Imagine triple sum, 4-tuple sum, quintuple sum, until the n-tuple sum, which is just one term because you have n ordered points. Okay, I don't prove this, but I just say, the message is you have to expand the exponential suitably. You have random walks, you compute expectations, so it's not surprising that some kind of expression like this can pop out. Now, my message is that this is an analytical expression which looks quite ugly, because even if these are random walk transition kernels, you are summing over time, so they are not probabilities. You see, if you sum over space, they are probabilities, but in time. But the point is that if you fix 2 dimensions, and you look closely at this expression, you realize that the random walk transition kernel in time decays as 1 over time. In 1 dimension is 1 over square root of t, local central limit theorem, and in 2 dimensions is the product of 2 copies. Okay? You know, if you look along the diagonals, a 2-dimensional simple random walk has independent increments, exactly. So, and you see, then you realize that somehow this is exactly the setting of renewal theory. I want to give a probabilistic interpretation to this sum. So I want this to be a probability. I cannot make it a probability on the whole integers, but if I introduce a horizon, capital N, and I rescale beta square as 1 over log n, then when I put the two together, this becomes a probability which depends on n. So remember that I defined the step probability as beta square times q. You see pi simplifies, and you get 1 over L, 1 over log n. That's is exactly what I defined before. And then you have this probabilistic representation of the variance is the probability that the first position of the renewal process is less than n, plus the probability that the second is less than n. That is the sum of my renewal function. So the message is that this renewal function for a very heavy tail, ultra heavy tail renewal process is somehow the key to get a full understanding of second moments properties of this directed polymer in 2 dimensions. There is even more than that. You can really make sharp approximations, but somehow it's a connection that is not so obvious to see. It's a bit unexpected, more analytical than probabilistic. It's just that you have a sum, you don't like sum, you want to think of sums as expected values, and so you just try to transform this into probability kernels. That there is nothing deeper. The point, which is deep, is that this random walk can be studied very sharply. The renewal theorem I stated at the beginning, which the exact prefactor, the exact constant, lies. I mean, this is possible because we have a limiting Rbb process, which is explicit. We know the density, essentially. Okay? And this concludes my second part. And now, stochastic PDEs. Actually, we'll focus on just one. It's the stochastic heat equation. This is formally written as follows. So derivative in time is equal Laplacian in space. So this is the heat equation. Then I have a potential psi times the solution. So it's a multiplicative stochastic heat equation. So for the moment, psi is a function. And I take the simplest non-trivial initial condition, constant 1. Constant 0 is not good because the equation is linear, so the solution would be 0. Okay, so constant 1 is nice. You can do more general. And the point is, it's very interesting to study the case when psi tx is what is called space-time white noise. If you're not familiar with it, is a continuum Gaussian process, which is not a function, actually, is a distribution in the Schwarz sense. In 1 dimension, it will be the derivative of Brownian motion. In 2 dimensions, is an invariant or irregular object. And the point is that this is very irregular, so the product is not classically well posed. Now, what's the point? Is that in 1 dimension, actually, one space dimension, one space, one time, you can make sense of this equation exactly as you make sense of stochastic differential equation. There is an integral form, and the integral makes sense as an Ito integral. This is really an extension of the Ito integral. It's very classical in the PD community, SPD community, because it was developed like by Walsh. There are some Flurry lecture notes of the 80s. So this is understood from a probabilistic viewpoint, and it has been understood in a deeper sense recently in the last 10 years by pathwise theories like regularity structure, in particular this by Heirer and Perdue, or paracontrol distributions by Gubinelli and Perkowski. So essentially one dimension is really understood. And the point is that this breaks into dimension higher. There is no solution theory, so there is no clear meaning of the solution of this equation. Let alone the equation. I mean, formulating an equation is difficult, but what should be the solution? And now, the natural idea in analysis is just we have a very irregular object, let's regularize it. So if we fix again 2 dimensions and we can regularize the noise. There are many ways. A typical way for this equation in the continuum is to consider a mollification in space. That is, you take your noise, you convolve with a mollifier on scale delta, like the heat kernel, for instance. You can do that. But actually, what we do is something different, is a legitimate way as well, is discretize. Now, space-time white noise is the continuum analog of IID random variables. Nothing more, nothing that. So we just replace white noise by a family of Gaussian random variables that live on a rescaled lattice. So essentially, imagine you take the integer in time, the integer in space, you rescale by a capital N, so very, very dense lattice. You rescale diffusively. This is the right way to rescale this equation. And now, you know, this is a differential equation, but once you put yourself on a lattice, if you replace the derivative by a difference, the Laplacian by a lattice Laplacian, this becomes a difference equation. Now, I'm cheating a little bit. There are many ways to discretize the equation, and if you are smart enough to choose a reasonable discretization, then you discover something interesting. You discover that the solution of the discretized stochastic heat equation is, rullo di tamburi, sorry, the directed polymer partition function. So the partition function that I introduced before, you see, before I had an integer time and an integer space. If you rescale space and time diffusively, so now t and x are continuous variables, you get a function of time and space. And this solves exactly the discretization of the heat equation. Again, I'm not proving that, but I'd like to convince you that this is plausible. The first is by analogy. The partition function is really a Feynman-Katz formula, which is analogous also to the one that Giovanni mentioned. So if we just go back quickly, you see it's the exponential of beta T Hamiltonian, and this is like a time integral of the potential evaluated on time and on the random walk that will become a Brownian motion. So you are taking the expectation with respect to the random walk. So this is really a Feynman-Katz formula in the discrete. So it's not surprising. But even more simply, it's quite clear that if you want to study the partition function where the random walk starts at z, and you make just one step in time, at the next time, at time 1, the random walk will be in one of the neighbors of z. So it's clear that there is a simple recursive relation that relates the partition function of length n starting at z with the partition function of length n minus 1 starting at the neighbor of z. If you write this and you just add and subtract term, you get exactly the heat equation. So you see, we are in a good position because we have an equation which is not understood, and we have a very natural candidate for an approximation of the equation. And now the question is, does this approximation converge to a non-trivial limit when n goes to infinity? Because if it does, then we have a candidate for the ill-defined solution of this equation. Of course, this is a rhetorical question. The answer is yes, but. And there are two important but. The first thing is that we cannot expect to have a limit as a function in x. It's too irregular. But this is somehow quite standard in PDE. You just look at this as a distribution in x. Actually, we are quite lucky because Z is positive. So we don't have to just use this abstract theory of distributions, just we can use measures, positive measures. We look at this as a density with respect to Lebesgue measure, and it will converge to a measure that will not admit a density. So it will be a singular measure. So it just means that we don't look, we fix time, this we can do, but we don't look at the convergence for fixed space. We rather average over space with a compactly supported continuous function. The second thing, which is very important, is that in order to hope to have convergence, we need, this is more troublesome in a sense, to rescale the coupling constant and to send it to 0 when n goes to infinity. Remember, n is just a discretization parameter. When n goes to infinity, you go to the continuum, and it's like we are switching off the coupling constant in front of the noise as n goes to infinity. Now, this is not surprising in view of what I told you before, because if you do that, you ensure that this random variable have a mean and a variance which converge to finite limits. You know, we want to have the convergence in distribution of this random variable. This is positive. First thing you say, okay, let's check the mean and the variance if they converge. If you want to have convergence mean, convergence variance, then you need to do that. And it's troublesome because you have an equation where you have a noise term, you have a constant, and you are sending the constant goes to 0. The message is that the equation is so singular that even if you turn the noise to 0 when you remove the discretization, you get an interesting limit, which is random. So randomness is so strong in this equation that it's singular and it poses for a reason. You need to somehow cure this divergence, and then get to the main result is that indeed if you rescale in this critical way the noise strength, then the solution converges to a limiting object. Now, what is this limiting object is what we call the critical two-dimensional stochastic heat flow, because it is, as I tried to argue, a natural candidate for the solution of the stochastic heat equation. From a mathematical viewpoint, okay, it's not perhaps the nicest object, but it's not so bad. It's a stochastic process in time, which is not a function, it's a measure. So it's a family of measures, a stochastic process taking values in measures on R2, okay? So to conclude, the message I tried to convey is that, well, many messages, but first, renewal theory is a very classical and also recent, in a sense, research area. There are interesting problems that are still open, and even though they are elementary, can be a bit technical indeed, but it's incredibly useful in many different contexts. Giambattista showed in his talk another example, and in particular I tried to give an idea about disordered system and stochastic PDEs. Yeah, we constructed this process. It's a stochastic process, and it's a natural candidate for the critical, so the solution of the stochastic heat equation. It's universal. For instance, I took Gaussian disorder, Gaussian, but this is robust. We can take any distribution with finite exponential moments. That works well. We didn't really write, but the proof is robust also to extension of the random walk. You don't have to take simple random walk, for instance. And we expect to be more universal, but the point is many features of this are known because somehow these asymptotics have been studied for a while. For instance, Lorenzo Bertini and Nicoletta Cancrini, back in the late 90s, had computed the limiting variance. Okay, there was no proof that there exists a limiting stochastic process, but now that you exist, you just get all the results that were proved. And more recently, Gu, Castel, and Tsai have proved that formula for all the moments. We have explicit involved formula for all the moments of this object, any integer moments. But the moment grow too fast and the distribution is not determined by its moment. So to conclude, thanks a lot and buon compleanno, Paolo.
Yeah, thank you, Francesco. Are there questions in the audience? Yeah.
So basically, you rescale with square root of n such that h, the variance of h is not going to 0.
What is H?
Sorry. When you define Z, the Miltonian may be H.
Yeah. Ah, okay.
So basically, you rescale with square root of n such that the variance is not going to 0.
Not really. I divide by square root of log n. You know, it's not. I mean, it's not too difficult to see. I mean, the variance formula that I wrote for the directed polymer here. Okay, sorry.
Later.
Here. Yeah.
No.
Okay, I wrote a formula for the covariance. You see, there is a sum and there is a V, and from this you can prove that when you rescale beta in that way, this converges to 0. In a sense, the reason why you need to scale beta square as 1 over log n, you already see from the first term. The first term, you have this that is 1 over L. You are summing until small n, and then eventually small n is proportional to capital N. So the sum over L of that gives log n, and then you need beta square to be 1 over log n to have this first term of finite variance. Then it's not trivial that all terms have finite variance and the series converge to something finite, but it's true, you can do it. But this was somehow already done with different techniques by Lorenzo Nicoletta. But yeah, this is where you see that somehow this is a natural way to scale the strength.
Other questions? Okay, if this is not the case, let's thanks again.
Thank you.
Thank you. Just 1 minute to move to the next speaker.
Non lo so, prova, funziona, fantastico. Ok, va bene. Devo parlare, devo... Va bene. Ok. Sì, poi lo regolo. Ok. Questo. Ok.
Sì, prova a dire prova così.
Prova, 1, 2, 3, psa. I musicisti fanno così. Ok, va bene.
Okay, so let us continue. The next speaker is Benedetto Scoppola from the University of Roma Tor Vergata. He will speak about the Bloom-Emery-Griffiths model at the FAT interface and about the unicity of the Gibbs method.
Okay, thank you very much. This is a plan of my talk, and the point 0 that is usually very short, it will be slightly longer, sorry, because this is a unique experience in my life. I had the possibility to give talks in Congress in which some very eminent colleagues were celebrated, but in this case, it's different for me because the eminent colleague is not only one of my best co-authors, but he's also one of my best friends. So this is not, is the first time that a very good friend has a Congress for his 60th birthday. And I have to say that I learned a lot of things by Paolo. Let me mention, for instance, the relation between the Deviation condition and the property of the correlations in high temperature spin systems. And let me also mention the fact that the morning coffee is much better without sugar. I learned this in Rutgers in 1990 when I was hosted by Paolo and Francesca, and it changed my life, of course. And I mean, I hope you can understand that it's really an emotional thing to talk in this Congress. And of course, I want to thank deeply all the organizers. They had to be patient with me. I'm sorry it was not possible for me to come yesterday for reasons and for health reasons. And anyway, thank you very much for this Congress. And one of the reasons why they had to be patient is that I changed the subject of my talk. But I did this simply because I'm obsessed by this problem, and it seems that due also to the interaction with Lorenzo recently, we have solved one point, and I wanted to tell to Paolo this fact. Well, the Bloom memory Griffiths model is a very ancient model. It was proposed by Bloom memory Griffiths, of course, in 71. And I studied a bit the physics of the model, and I think it was proposed in a period in which the idea of universality classes were very popular. The paper by Wilson on the normalization group was 3 years later. So clearly the idea was to discuss the property of the mixture of helium-3 and helium-4 with a different simpler model, hoping that it was in the same universality class of the Landau theory of superfluids. And then it has been used with this attitude for many other problems in physics. And the formal Hamiltonian has something to share with the Hamiltonian of the easy model. You see there is, I have a, no, well, anyway, you see there is a ferromagnetic term of the form of the easy model, then you have a quadrupolar term, and this quadrupolar term is not trivial as it would be in the easy model, simply because the spins are -1, +1, and 0. And then you have a last term, which is in some sense the chemical potential for the let me call them particles, the particles with 1 or -1 spin. And well, you can study it varying the value of the constant. And there are actually three regions. Let me pass directly to the picture. You have 3 regions. You can understand the features of the ground states of the system in the various regions. Typically, for instance, the ferromagnetic phase is a phase in which you have a very high, to understand, a very high chemical potential. So you have a lot of particles. If the quadrupolar term is positive, you see that when you have a lot of particles, it does not count much, and because typically the states, the ground states, are with all the points in the lattice occupied by particles, and then it becomes an easy model, and you can discuss the other regions, and you find the fact that at the Fad interface in that point and on the dA line, the problem has an interesting feature. The ground states is incredibly degenerated, and then you want to understand something about this part of the phase space, and so we started studying the ferromagnetic antiquadrupolar disorder point, in which the Hamiltonian is this. And if you want to study the zero temperature problem, you see that the energy is not negative, and is zero always, except in the case that the two nearest neighbors have different sign. So typically, the ground state is a set of the old configuration in which you never have a plus and a minus in nearest neighbor position. You always have to have a zero between them. But clearly, the number of states of this kind is exponential in the volume. So if you want to understand something, well, you have to work. And for instance, an open question was to understand if the Gibbs measure is unique in the thermodynamic limit in boundary condition. I mean, you put a different boundary condition and then send the volume to infinity. You obtain a single measure, or you obtain different measure, as in low temperature is in model with the plus and minus boundary condition. So we started computing the thermodynamic limit of the spontaneous magnetization. And the standard procedure is define the back model in a finite square, then choose, for instance, +1 boundary condition, and compute the expected value of the magnetization in the center, and see if the thermodynamic limit of this object exists and what kind of result you find. Well, to our knowledge, there are no rigorous results about this, and it seems that the problem has been studied by mathematical physicists only a few years after the Bloom-Emery-Griffiths paper. For instance, Joel Lebowitz and Moore, I don't know who is, but anyway, Joel published a paper on the fact that the FKG inequality were valid when the value of the constant in front of the quadrupolar term was enough, was small enough. And it means I think that they were interested to this problem of the magnetization of the spontaneous magnetization. But as far as we know, there are no rigorous results about this. There are a lot of numerical results, and the spoiler is that the presence or not of the spontaneous magnetization depends on the dimensions. In 2 dimensions, there is no spontaneous magnetization. In 3 dimensions, there is spontaneous magnetization. And this implies that there is not an abstract reason why you cannot expect a dependence or independence on boundary condition. You have to understand something that should depend on dimensions. Our argument is related to the first result. We prove that there is no spontaneous magnetization in 2 dimensions, and then also we prove that the measure is unique, using, if you want, FKG or different techniques in 2 dimensions. And then in the last slide, I will tell you something about the open question about this problem, and of course the 3 dimensions are one of those. Our argument uses a dynamical approach, and we defined a sampler, which is the first thing that you can imagine. You choose at random a point, and then in that point you put with uniform distribution a possible value for the spin. It means that if the nearest neighbors are all 0, you put 1, -1, and 0 with probability 1/3. If you have 0 and +1 or 0 and -1, you put one of the two values with probability 1/2. If you have both plus and minus, you are not yet standing. Okay. If you have plus and minus in the neighborhood, you are forced to put 0 there. So this is a trivial, if you want, sampler. Well, yes, this is what I told you. It is very easy to show that it's ergodic, and since the probability transition are symmetric, the invariant measure is uniform as you want, because the energy of the ground states are always 0, so your Gibbs distribution is unique on feasible configuration. And also it is not difficult to show that since the states are partially ordered, you can define the updating functions in such a way that you can define a coupling between different ordered configuration in such a way that the order is preserved by the dynamics. And this is what I wrote here, but maybe I don't know to go very in detail. Of course, what you do is, in order to define the coupling, is if you have two ordered configurations, you update the same point, and then you use the same uniform variable in 0, 1 in order to update the value of the spin in that point in such a way that always, for all the possible values of U, the new spins are ordered. This is quite standard, and I did 2 examples, but it's not. This gives you the possibility to define a perfect sampling. And it is not, well, this is the part on which I am less efficient. A young student, Riccardo Mariani, I forgot to tell you it was written. This work is in collaboration with Aldo Procacci, Paolo Lima, and Riccardo Mariani. And Riccardo Mariani worked a lot in order to realize a perfect sampling. And it is quite good the fact that if you do a sampling that is of the order, say, of the square of the volume, then the probability to have something that you have to restart with a coupling from the past is quite small. So it is not difficult to realize a coupling from the past for this sampling. It is not too slow. And we computed empirically the magnetization with this sampling, and you see this tells you that the magnetization goes to 0 slightly more than exponentially. Slightly more may be the fact that the volume is very small, but anyway, say exponentially, and we have a proof, in fact, of this. This is. I asked to Riccardo to send me the updated figure, but I had not updated this figure in time. He arrives up to 31. This is for very small volumes, but anyway, it is clear that the spontaneous magnetization in D equal to 3 is not 0, is something like something more than 0.4. And then this sampler gave us the idea that is necessary to prove this first result. This theorem then is a basic result in order to prove the unicity of the Gibbs measure. And the theorem tells you that the Beck model at the far interface with plus boundary condition, the spontaneous magnetization with plus boundary condition, I told you, is 0. And I don't want to give you details, but the idea of the proof in the end is quite simple. I'm saying in the end because we tried a lot of combinatorial ways to prove that the spontaneous magnetization is 0, and they failed. It really was an hard problem to solve until we had the idea to make a coupling with the percolation. Since the probability to put +1 in our model is always less than 1/2, it is possible to define a coupling with an easy microchain that has as stationary measure the measure of percolation. Since in 2 dimensions 1/2 is undercritical for site percolation, you have that the set of plus that you obtain in the bag model has to be smaller than the set of plus that you obtain in percolation, and you know that typically the set of plus in percolation is finite because and you know more. You know that the correlations decay exponentially and so on and so forth. So you can use all the results in percolation in order to give estimates of the probability to have clusters of plus. And actually the clusters of plus, this is the first lemma, is all you need in order to compute the magnetization, the spontaneous magnetization, simply because when you have a finite cluster and the cluster does not touch the boundary, the contribution to the spontaneous magnetization when the value of the cluster is plus is exactly cancelled by the contribution with all the rest equal and the cluster minus. So all you need is to compute the sum of the configuration in which the cluster containing 0 touches the boundary. And so in the end, the proof is really quite simple. From a technical point of view, it's quite simple. I don't, in some sense, I already told you the proof of the 2 lemmas. And the proof of the main theorem is what I told you. Simply, you cannot touch the boundary, so the train in the limit of the volume that tends to infinity, the spontaneous magnetization goes to 0, and you can also say that it goes to 0 exponentially, at least exponentially, because the probability to touch the boundary goes to 0 exponentially in percolation. And then after a while, we spent sometimes in an unuseful way, but in the end, talking to Lorenzo and reading both Liggett and Lebowitz, it is not difficult to prove that the measure is unique. Actually, for instance, I like the proof of the book by Liggett. You have to prove that the marginal in each site is equal. It does not depend on boundary condition. And this is not difficult using the coupling with the percolation. And then you simply have to prove that the monotonicity for all increasing functions, the average of the increasing function, if the boundary conditions are ordered, the average are ordered too. And so clearly you find the unicity of the Gibbs measure for this very particular problem. I would like to say that the reason why I choose this seminar is because I think that this problem of the bag model is really very interesting. There are a lot of open questions, and some may be not too difficult. For instance, it would be nice to provide a theoretical proof for the non-vanishing of the spontaneous magnetization in 3 dimensions. or to prove something about the back model, for instance, also at the FAD interface, but when the temperature is not zero. And this is also a problem which is not trivial, I think. All I know about the possibility to study the Gibbs measure when the temperature is very small is related to the fact that the ground states are 1 or 2, say, and then you can do some expansion in terms of contours or something like this. Here the situation is completely different because once you switch some positive but very small temperature, you add that all the possible 3 to the lambda states have non-zero probability. But the zero probability state is a mess. So the typical cluster expansions or stuff like this do not work in this case. So it could be interesting to understand how to define low temperature expansions when the ground state is very, very degenerate as in this case. I think it's an interesting problem. And also very interesting, but I think very hard, is to prove that the fast mixing of our sampler that is quite evident from an experimental point of view, but since in some sense this is a coloring with few colors, to prove the fast mixing of a sampler like this could be very, very hard. Anyway, this is what I wanted to say about this problem. I'm sorry I do not have pictures of Paolo when he told me that the coffee was better without sugar, but it was quite a lot of years ago, and I had the cell phone at the time, so it was not possible. Paolo, tanti auguri, the best is yet to come, surely. Come tempi sono andato bene. Okay.
Thank you for the talk. At least for people that is connected is important. Okay, so thank you. There is one question first.
So just a little more comment of what you said. Maybe once you have exponential convergence of the dynamic, it's not impossible to set up a perturbation argument at the dynamical level, which should much easier than looking at the static.
Yes.
Is that what you said? I mean, doing like cluster expansion, whatever, infinite degenerate, this is a mess. But doing a perturbation argument around beta infinity to the dynamics, once you have that beta infinity exponential convergence, maybe this is feasible.
Yes.
Other questions? Or do you want to comment back?
No. Thank you very much. But the idea that the coupling and the dynamical approach is crucial in this model is clear. So surely we will try to do something like what you say. Thank you to Lorenzo for everything. Okay.
So if there are no other questions, since we are always a little in late, we thanks again Benedetto.
Thank you.
The next speaker is online, so just a few minutes to prepare the connection.
Yes, can you hear me? Yeah. Can you hear me? Okay. Beautiful, beautiful.
Thank you very much for your patience. Now I just give the floor to the chairman. Bye.
Thank you very much.
Yeah, so thank you. Now the next speaker, the last speaker of this morning session is Hans Dessin from the University of Bielefeld, who will speak about on-cluster dynamics of infinite Newtonian dynamics. Please.
Thank you very much. Dear Paolo, I enjoy very much to contribute to your birthday at a distance, and I wish you all the best. The topic of my talk is I consider classical systems in Euclidean space, Rd, under the action of the infinite Newtonian dynamics. This is an old classical topic, and I am interested in the idea of the decomposition of this system into cluster dynamics. And the first idea formulated by Bogolyubov in 1946 is the following. In the gaseous phase, where the interaction between particles is short-ranged, the particle system can be decomposed into finite clusters so that during some random interval of time, each cluster moves independently of other clusters as a finite dimensional dynamical system. After such a random time, the clusters collide and the system can be decomposed again into other dynamically independent clusters and so on. In 1974, around Sinai made these ideas rigorous, but the notion of cluster dynamics remained implicit. And what I want to do in this talk is to give a rigorous construction of the cluster dynamics of the infinitely extended Newtonian dynamics in Euclidean space, which I call E. And my talk has three parts. The first is I present the so-called evolution theorem of Kornfeld, Fomin, Sinai, of these three authors on ergodic theory. The second part is so-called Muirmann's theorem, which is unfortunately not well known. I will present it because we use it. And this part is based on joint work with Suren Pogosyan. And then I present two main results. So consider the initial configuration. My phase space is the S, the product of Rd with itself. And I have looked at this psi here. This means it is the configuration, infinite configuration, but locally finite of the positions. The positions are Q prime. And to each Q prime, you have P of Q prime, which is the velocity, associated velocity. And this I call a particle. And this tuple I consider as a measure, as a Dirac measure. And I sum up these Dirac measures, and I get I get a configuration which I call mu. It is an initial configuration of particles. And this is surrounding a given particle which I call A. A is situated in Q, has velocity v. So this is the initial situation. Pardon. And the first problem is to solve the Newtonian dynamics. And what is it? What does it mean? We are given stable and one moment, something. We are given a stable potential of finite range R, and the particle A, given the environment mu, it develops under the action of the Newtonian dynamics. And it is here, this equation. So given the initial data A, mu, and the position at time t, what is it for the Newtonian dynamics? First of all, this first sum here, this is the so-called free dynamics. So it is q plus velocity times t, but there is another contribution here, which I want to explain now. It is a double integration. Look at the inner integration about over S. There, the integrand is f of q of r prime minus q of r. And what this f means, it is minus the gradient of the given potential of the distance between q prime and q, and it represents the force with which the particle in q prime acts on the given particle in q. So this is the forces, they are summed up here. So mu d a prime is the sum over all particles of the environment, of these forces. And this is integrated on, with respect to R. R is here, you see. So the position of the particle at time t is the free position plus something, a disturbance. In the evolution theorem of Kornfeld, Fomin, and Sinai, it has several ingredients. The first, very important, is there exists a subset M prime of M, which is so large that it supports all Gibbs processes P for this given potential, and a reference measure rho on the phase space, which is of the following form. First of all, it is Lebesgue. So in the position space, Lebesgue times some Z, some activity. And the second is the Maxwell distribution. Second ingredient, for every initial configuration mu in M prime and every particle A, there exists a curve delta T mu in M, but not, unfortunately, not in M prime. M prime is this set here, this subset of M, which has the property that the Q, the position at time t for the initial data A mu, solves the Newtonian dynamics. So this is second ingredient, existence of solutions. Third ingredient is that this series here, remember, this is the sum, this mu d A prime is the sum over all forces, over all configurations. This sum is finite. This is the third ingredient, the finite sum, and it is differentiable with respect to t. It's not at all trivial. All these things are not at all trivial. So we can take the derivative on the right-hand side of the Newtonian equation, and we obtain then the usual form, well-known usual form, Q 2 times differentiated is given by this integral here. And these are the initial distributions. At time 0, the position is Q, and the velocity is V. Next point is every Gibbs process P remains invariant under this theta T. And finally, this theta T is a flow on M prime P for every Gibbs process P for phi and rho. And this flow here is the dynamical system corresponding to the Newtonian dynamics. So this was the evolution theorem of Kornfeld form in Sinai. Now I come to the second part. It is Muirmann's theorem. And I want to present some isomorphism first. The parameter R, it is the range of the potential. So once more, we have assumptions on this small phi. Pair potential is stability and finite range R and some smoothness conditions so that we can formulate correctly the Newtonian dynamics. So this parameter R enables the notion of a finite cluster. So this is very important, this notion. A finite configuration of particles, chi, is called an R cluster if the graph with vertices chi, so the particles, which is obtained by joining interacting particles, this graph is connected. So all particles of chi are vertices, and if I join interacting particles, they are all connected. Or to say it in another word, each two particles of chi interact at least indirectly. So let us call C prime the collection of such clusters, and M subcritical, this SBC means subcritical. This denotes a set of all mu, configurations mu, which decompose into R clusters chi, which have the property that chi does not interact with the rest of the configuration. And now I consider following mapping, which then will be the isomorphism. It is defined in these subcritical configurations. And the idea of chi is very simple. A configuration of particles, we associate the kappa. This is a configuration of all clusters. So if you look at this Dirac measure here, it is Dirac in chi. Chi is an element, is a cluster. I integrate over clusters, and I take all. This here means summation over all clusters of mu. Do not try to understand this formula. It is only a formal, rigorous definition of what I said before. So to mu, I associate the configuration of clusters. And it is clear that this configuration, I can go back. If I have here a cluster configuration, I dissolute the clusters into its particles and come back to this space. So I wrote it here. This dalet, this symbol dalet, is a bijection between this set of configurations and the set of kappa, this cluster configuration, and the inverse I call Gmail. This is defined, as I said, by dissolving the clusters of kappa into its particles. And moreover, the relation, so take some P process supported by this set here of subcritical configurations, the image of P under dalet I call Q. This induces a one-to-one correspondence between subcritical processes. This means processes supported by this set here, M subcritical, and processes in the space C prime of clusters. So this is the isomorphism. Now the theorem, this important theorem of Mühlmann. It describes the images of Gibbs processes which are subcritical under the action of dalet as Gibbs processes in C prime. So let me be more precise. If Q is the image of P under this isomorphism, if this is the cluster process of some subcritical P, once more, consider Q the image of P, and I assume that P is subcritical. Then we have the following equivalence. P is Gibbs for phi and rho, if and only if this image is also Gibbs, but a Gibbs process in the space of clusters, yeah, for which interaction and for which measure. So this interaction here, this is very simple. It is a pure hardcore pair potential in the clusters. So it is a pair potential in the cluster space and pure hardcore. So it's a non-negative pure hardcore potential. The structure of this interaction is much simpler than this original phi, but it is a pair potential on the cluster space. It is not Euclidean space. And what is M here? M is defined as follows. So we have this rho, this measure rho here, and this I lift to the collection of all finite configuration as usual. This is restriction to the cluster space. So this measure here, it is supported by finite configurations. They are restricted here to clusters. They should be clusters. And I multiply with the e to the minus the energy of this given pair potential small phi. This is what we call the Mühlmann measure. Yeah. Let me go back once more. So this equivalence is really very, very interesting. It is an old result of Mühlmann from 75. Why it is interesting? So if we want these objects here, these classical Gibbs processes in Euclidean space, they are very difficult to analyze. And you can get informations for them in studying such pure hardcore processes in the space of clusters. This is the message of Memann's theorem. Here are some comments. This measure, M, can only be a reference measure for Gibbs processes in this space C prime if it is locally finite. So it should be locally finite. And this is the case one can show if Z is bounded from above by some explicit known constant. I do not give the constant here. So such assertion is, the proof is given by so-called method of cluster expansions. For such Z bounded by Z0, one can even show existence of Gibbs processes Q, of these Gibbs processes Q, which are called by Memann Poisson exclusion processes. So these are Poisson processes, but with hardcore, so Poisson exclusion processes. So one can prove existence of them, and thereby also, by Memann's theorem, existence of subcritical Gibbs processes in space. So P in Gibbs for phi and rho. In this case, we write in the subcritical here to the space of Gibbs processes. One moment. So this is only some formulation, what I said already. We have some Z0 such that if Z is smaller than or equal, then this set here of Gibbs processes which are subcritical is non-empty. And moreover, if we are under the assumptions of the evolution theorem of Sinai, then these processes are supported not only by the subcritical configurations in Euclidean space, but even in the subspace intersection with M prime. And we write subcritical N prime here. So, and the first main result now, it is also a summary. If we combine Memann's theorem with the evolution theorem, then we get a theorem of Sinai from 74. For all subcritical Gibbs processes for phi and rho, this triple here. So it is M prime intersection with subcritical configurations, then the actions of the Newtonian dynamics, and P, the given Gibbs process. This triple is, for Z small enough, the flow which describes the dynamical system corresponding to the Newtonian dynamics. So this is a flow in the sense of ergodic theory. And this is a mathematical formulation of one part of Bogolyubov's assertion at the beginning. So this is P is invariant under theta t. So if we start at the beginning in some mu of M prime, which also decomposes into clusters completely, then this remains so for later times, all later times t. So this is this picture that the Newtonian dynamics decomposes always in two clusters. Now I come to the notion of the cluster dynamics for the Newtonian dynamics. So let Z be small enough. P is a subcritical Gibbs concentrated on n prime, so that we are in the situation of the evolution theorem. We consider the image Q under the isomorphism. Then this theorem, which I just formulated from Sinai, it enables us to define Q almost surely the cluster dynamics as a curve kappa T in the space of configurations, of cluster configurations, as in the following way. We start with some kappa, a cluster configuration. It is here, kappa. Then we take Gmail. It is the inverse of the isomorphism. This means we dissolute the clusters into the particles. We get the configurations in Euclidean space. Then we apply Newtonian dynamics, theta T. This we can only if this Gmail kappa is in M prime. And this is only the case almost surely, P almost surely. So then we can do this, P almost surely, we get the time-evolved configurations, and then we go back to the cluster space by the configuration, by the isomorphism. Also, this is only not always possible, but almost surely. So, this is a precise formulation of the cluster dynamics. One can show that Q remains invariant under the cluster dynamics. This is very simple. So let me summarize this theorem. If Z is small enough, let Z be small enough, and the P subcritical Gibbs process for these data, phi, and our rho, which is explicitly, I repeat here again what it means, rho, and Q the corresponding cluster process under the isomorphism. Then I obtain the flow which describes the Newtonian cluster dynamics. It is the following. It is the space of cluster configurations together with this action here, kappa T, and the given Q, which is a Poisson exclusion process belonging to P. So this is, before I go to the literature, these theorems, for these two theorems, I used the evolution theorem of Kornfeld, Fomin, Sinai, but to apply Neumann's theorem, I need only stability of the given pair potential and finite range. So I can replace, this allows us to replace Sinai's evolution theorem by others. There are several others. Unfortunately, there does not exist a final evolution theorem. This is very complicated to solve the Newtonian equations, but one can replace for these theorems here the evolution theorem of Sinai by a theorem of Landford, Oscar Landford, who was one of the pioneers in this topic, or of Alexander, Bodrigini, Dobrushin, Sukhov, or Dobrushin and Fritz. So this indicates that I can replace the evolution theorem, indicates the generality of these theorems, which I presented here. So thank you very much for your attention.
Thanks a lot for the nice presentation. Are there questions in the audience or online? Yeah.
Hello, Hans. This is Paolo speaking. So first of all, let me thank you for, even if you could not come here, that you accepted to contribute to this event. I'm really deeply grateful for that. And I just have the curiosity. So the original theorem, the Mühlmann theorem that you mentioned about the isomorphism between the particle dynamics and the cluster dynamics had something. So what was the original purpose of that result? What was the original motivation of that result? So you applied here, and can you say a little bit more, tell us a bit more about the history of this not very well-known result?
Thank you. You mean the Mühlmann theorem, or
the Mühlmann theorem, yes.
Or the evolution theorem?
Mühlmann.
The Mühlmann theorem, Hans.
Yes. Yes, for Mühlmann, the motivation was to deduce this theorem to solve problems of existence, of uniqueness, of classical Gibbs processes. So he was concerned in the 70s with these problems without being able to solve, for instance, the problem of uniqueness. This was his motivation. And my idea here was to use it in the context of the cluster dynamics of the Newtonian equations.
Thank you. Yes, thank you. Thank you. Other questions? Okay, it seems not the case. Then we thank again Hans Erdogshanigraph.
Thank you very much. Thank you.
Thanks a lot. And I think that now we have the lunch break, and we resume at 2:30 in the afternoon.
Welcome back. First, some announcement. That the meeting point for the visit this evening is at 7 p.m. Is at Piazza Duomo. And now it's our pleasure to welcome Elisabetta Scoppola, and you will present us some results about quasi-stationary distribution of non-absorbing Markov chains. The floor is yours.
Thank you very much. So thank you for the invitation to this very special workshop in honor of a very special person and very special friend. So ok, auguri, quasi auguri, quasi stationary, quasi auguri. Okay, I will speak about quasi-stationary distribution of non-absorbing Markov chain. This is a work, actually a work in progress with Roberto Fernandez, Francesco Manzo, and Matteo Quattrobani. Okay, so. Doesn't work? Non funziona? Ecco, andata. Ok, The talk is organized as follows. First, I introduce some notation hypothesis, and I recall what happens in the absorbing case. What is the quasi-stationary distribution and what one knows. And also, I want to relate the quasi-stationary distribution to the problem of first heating and metastability, because this is the context in which this has been applied. Then I will... no, questo non funziona? Sì, okay, thank you. I will make a small detour on first heating and conditionally strong quasi-stationary times, remaining in the context of the absorbing case. And then I will give the problem in the non-absorbing case and the main results of our work. I will discuss a sort of very simple example in order to explain the results. Okay, so notation and hypothesis. So I'm not interested in making the more general case, but I will start with very particular, very simple hypothesis. I have a discrete time Markov chain on a finite state space, and P is irreducible and aperiodic. I suppose that there is a unique stationary distribution, okay, that I call pi. I also assume reversibility. This is not necessary for every result that I will present, but I start with the particular case in some sense, with the maximum of hypothesis. And I assume that the non-trivial eigenvalue of P are all positive. So one can reduce one can have this condition just considering a lazy version of the reversible chain. Okay, I call alpha the starting distribution considered, and so I denote my mu the evolution, the mu alpha, the t, the evolution starting from alpha at time t. Okay, so this is I will use the separation distance to control the convergence to stationarity, and so this is a standard definition. And I will also use the notion of optimal strong stationary time that I will denote by tau alpha pi. That is a randomized stopping time such that the probability to be at a certain point, starting from alpha, to be at a certain point, and the tau pi is less or equal to pi is equal to pi x and the probability. So these two events are independent. And okay, and also I assume optimality, so that the probability that tau pi larger than t is equal to the separation distance. Okay, so this is a quite standard notation. So in the case of absorbing metrics, I mean that there is an absorbing state. So a state from which the probability to remain in the state is equal to 1. One can consider the set of all the other states of inessential states of the chain, and I call this I. And I denote by tau xs the absorption time, so the time in which the process hits the absorption state. Okay, so in this context, the quasi-stationary distribution on I is well known. I mean, by definition, the quasi-stationary distribution means that if I start from mu star is a quasi-stationary distribution, is starting from mu star and looking at the process conditioned not to be absorbed up to time t, then this is equal to mu star. So it's stationary for the process conditioned to remain in the set I of inessential states. Okay, this is a possible definition. This is the definition, actually. But there is also another quantity which actually is the same, that is the limit, is the Yaglom limit. So the limit of the process for t tending to infinity of the distribution of the process conditioned by not to be absorbed. So of course, if this limit exists, this is a quasi-stationary distribution. Okay. So this was the starting point of the theory. I mean, yeah, I don't want to make a complete review. So I just mentioned the main paper. The existence of the Yaglom limit in some particular case is a famous paper by Yaglom, and then Dialog Seneta, and then Seneta in his book describe in great detail this quasi-stationary distribution. And there is also a nice paper in 95 by Ferrari, Kest, and Martinez Pico. Okay, I don't give a complete. Okay, this is the definition in the absorbing case. And there is, of course, a simple algebraic characterization of the quasi-stationary distribution, in the sense that if I denote by P with the XS the substochastic matrix obtained by P, erasing the row and the column corresponding to XS, okay, then if this, and I suppose that this is a primitive matrix, so erasing this row and this column, I don't break the ergodicity, the ergodic property. So by Perron-Frobenius theorem, we know that there exists a principal eigenvalue less than 1 because the matrix is substochastic. And there is a unique non-negative left eigenvector, and this eigenvector is exactly the quasi-stationary measure. So it's very clear, the definition also from an algebraic point of view. And of course, if I start from mu star and I look at the probability that not to be absorbed up to time t, this is equal to lambda to the power t. Of course, this is an immediate computation. And also that this is a quasi-stationary matrix in the sense that I start from mu star and I look at the conditional process to be in x at time t, this is mu star, of course. So this is all simple, all is very clear, very simple. Moreover, the quasi-stationary measures satisfy, of course, that the limit for t tending to infinity, so the Yaglom limit is mu star. Okay, this is very, very simple, all is very, very clear. Why this is related to the first heating problem and metastability? Because, of course, if one is considering first heating to a state, I have, again, a Markov chain with the godicity property and all what I assumed in the first slide. And I'm interested in the first heating to a given state, G, say a goal. One can consider the chain with where G is absorbing and up to the first heating to G, the process is exactly the same. And so, sorry, and so the, che ho fatto? Okay. And so the exponential distribution of the first heating time is strictly related to the quasi-stationary distribution because starting from the quasi-stationary distribution, I have exactly an exponential distribution. Okay, exponential law of eating time has been studied by a lot of people. Again, I recall the very nice book by Kilson, and also a lot of papers of Aldous and Brown, and etc. Okay, there are two different regimes for the first eating. The first regime is the regime, say, of metastability, in which there is a state which is frequently visited before the eating to the state excess, to the goal, so to the absorbing state. And so the path up to absorbing consists of a geometric number of excursion from M to M. So this is the reason of the exponential distribution. The second regime, completely different, is that the distribution of type T is near to the stationary distribution. If the chain is rapidly mixing, even when one considers the conditioning not to be eat the state excess, then Aldous show that the distribution starting from pi of the first eating to excess larger than tau is approximated by an exponential, where this delta is small if the goal, I mean the excess, is a rare event. So if the expectation of the eating time to excess is much larger than the relaxation time of the chain. Okay, so these two regime at the beginning was considered as in a sense complementary. The first, as I said, is typical of metastability, and so the process is trapped for a long time in a part of space and with a lot of recursion to a metastable state, say XM. And this has been initially introduced by the paper by Cassandra, Galvez, Olivieri, Vares, and then by Schonman. I mean, here there is a lot of, I mean, metastability has been studied by a lot of people. And also there have been more recent extension of the method to other regimes. So when there is not a recurrence to a single state, and so there are papers by Bianchi, Godillere, Fernandez, Manzo, Francesca Nardi, and myself, and I mean there are a lot of results. The second scenario, the scenario studied by Aldous, Aldous showed that rapid mixing implied that the stationary and the quasi-stationary measure are closer to each other. This is the idea. And this paper is really very nice because starting from this idea with the sequence of smart elementary steps, he deduced his estimate on the exponential distribution of the first eating to XS. Okay, in both regime, metastability and eating to a rare state, all is played by on the fact that there are two completely different time scale. The eating to the goal is the mean of the eating to the goal is much larger than the time of a local equilibrium. So it occurs to XM in the first case, and occurs to pi in the second case. Okay, so it's clear that these two regimes can be understood in the same way by replacing recurrence to a point with the recurrence to a measure. Okay, so and this has been done in the study of metastability. Okay, so starting from this consideration, one can. Dove siamo? Okay. Starting from this consideration, one can extend the theory of strong stationary time to quasi-stationarity. And so one can introduce the idea of conditionally strong quasi-stationary time. And with this notion, one can prove exact formula for the distribution of the first hinting time. Starting from an arbitrary distribution. This is important. I mean, one can, in the previous result, one was starting from pi or from xm, or from the metastable state. Here, we are trying, this is a paper in collaboration with Francesco Manzo. We want to have exact result for the distribution and also the dependence on the initial starting distribution. Okay, what is the conditionally strong quasi-stationary time? Our definition is, is essentially the analog of the strong stationary time. So a randomized stopping time is a conditionally strong quasi-stationary time if for any y different from xs, which is the absorbing state, say, one has that starting from alpha, the probability to be an x and tau star equal to t equal mu star and the probability that is equal to t less than not to be before the absorption or equivalent. This is the case. Okay, so we prove that for any alpha there exists a conditionally strong quasi-stationary time. And we have this expression. This is not an estimate. It is a completely defined expression. Precise evaluation of the distribution of tau xs of the. Okay, one just to comment this, I don't want to enter, of course, in the detail of the proof, but we know that we can prove that this term and this term that now I explain what is are exponentially decreasing in t, and here the dependence of alpha, which is here and here, also in this term. Is given, using the right eigenvector of the reduced matrix. This is known that the right eigenvector gives information about the dependence of the initial distribution. Indeed, it's well known that if one look at the limit of the distribution of tau larger than t, starting from y and starting from z, the ratio is given by the ratio of the two of the value of gamma in these 2 points, and also that this limit, the dependence of y, is given exactly by the right eigenvector. Okay, so so introducing this right eigenvector is also useful to define, in a sense, a Dubter's form. I mean, we want to, in a sense, renormalize the reduced chain that obtained by erasing the row and the column corresponding to x with this ratio and dividing by lambda. And so one can obtain, in this way, a stochastic matrix with an invariant measure which is related to mu star and the right eigenvector. And this can be simply checked by controlling that if I consider a new, if I define nu in this way, and ma dove sono andata? Che è successo? Sono andata alla fine? Che disastro, che impedita. Ok, ok. If I substitute here this definition and in the definition, it's immediate to check that this is exactly the... Okay. Then one can define a new given alpha, a distribution alpha, one can deduce the corresponding initial distribution for the Duptas form. So, and one can look at the convergence to equilibrium of this Duptas form. So this is the quantity. This is the quantity. Ma che succede? Non capisco. Okay. This was the quantity that was involved here in the still the alpha and all that, and gamma. So this is to clarify the. Okay. What one has to say on this result is first of all, the hypotheses necessary for this result are much more general than what I asked at the beginning. I don't need reversibility. The state space can be countable. The target can be a set of states. Okay, so it's more general. Okay, and one can obtain an exponential decay only if the time given by the minimum between the tau star, so the conditional stationary time, and the absorbing time is smaller than the relation time 1 over 1 minus lambda. Okay, so this is okay. So, however, it's clear that it's difficult to use such a result because one has to control the right eigenvector, the decay of the Duptas form, and all that. So this is okay. Now we come at the main argument of the talk. So, of the case in which there is not an absorbing state. Okay, so I have a reversible Markov chain, a finite reversible Markov chain. I have a stationary distribution pi, and I look at the conditional distribution obtained by conditioning that tau pi is larger than t. Okay, this is the analogous. I replace the not to be absorbed with this condition, not to be at equilibrium in a sense. Okay, so for this conditional distribution, one can see with a series of very simple steps, but I don't give the detail because it was too long. That one can see at the evolution of the conditional distribution. There is a relation of this kind. And the main theorem that we have is that if the transition matrix is reversible, irreducible, aperiodic, with positive eigenvalue, then for every starting distribution, of course different from pi, there exists the limit of this conditioned distribution. Okay, so there is the Yaglom limit. Okay, and of course, if there exists this, I already said that this corresponds to substitute in the absorbing case what was the absorbing time now with the optimal stationary time. And And the distribution phi alpha, that is the Yaglom limit, of course, is a quasi-stationary distribution for the process conditioned to not to be at equilibrium up to time t. Okay. And of course, if starting from this phi star alpha, the heating to pi is exactly exponential. Okay. Okay. So as a corollary, we obtain that I give this corollary in order to clarify that this existent theorem that we have done for the Yaglom limit in the non-absorbing case is in a sense constructive. So is a constructive proof. So one can deduce by this theorem that if the limit distribution exists, then for every alpha there exists a couple V alpha lambda alpha, such that V alpha and lambda alpha are eigenvector, left eigenvector and eigenvalues of the matrix P. The distribution is in the span of V alpha and pi, and this is, and the distribution, the quasi-stationary distribution. And the quasi-stationary distribution satisfies this equation, so the evolution after a time t is given by lambda alpha to the power t phi star alpha, and this term. And the separation distance starting at alpha decay exponentially with rate, asymptotically, exponentially with rate lambda alpha. And it exists a state where the quasi-stationary distribution is 0. Okay, this is the point that one can prove with this theorem. This is not really the idea of the proof, but I try to explain in which sense the proof is constructive. So if I call the left eigenvector with the bra pi and nu I with I from 1 to n, if n is the size of the number of states, and the right eigenvector with f is not. Sorry, the right eigenvector of pi is 1, of course, and the ket corresponding to the nu I call fi, and lambda 1 is 1, and lambda 2, etc., all the eigenvalue of the matrix order in the decreasing order. Okay, then one, using reversibility, one can rewrite the transition matrix in its spectral decomposition, okay? And so, and one can write also alpha in this basis of pi and nu, okay? And so, since alpha is a probability distribution, alpha scalar product with the vector given by all 1 is 1, okay? And so this first coefficient C1 is 1. And so alpha can be written as pi plus this sum, okay? And so when one put this alpha here and one look at the evolution of this, it's possible to see that I mean, I'm not giving the proof, but if these are our eigenvalues, and lambda alpha is the maximum value, is maximum lambda, such that Ci is different from 0, so the... ma perché fa così? Io non capisco. Ok. such that chi was the maximum lambda, such that alpha has a non-zero component on the corresponding eigenvector. Okay, and E alpha is the set of the index in which lambda I is equal to lambda alpha, because there can be, of course, degeneracy in this spectrum. Then, if there exists this limit, then one see immediately that the Yaglom limit can be written in this form. So as V alpha is this part, and pi is pi. Okay. Where lambda alpha is this, and is related, can be written in terms of nu I and pi in this way. Okay, this is an immediate consequence. Okay, so some remark. As I said, the proof is constructive, so one can, in a simple example, one can calculate the quasi-stationary measure. But the construction needs the spectral contour of pi, so this is not very simple to apply. And there is another point to note, that the quasi-stationary measure it depends on alpha. And this is really a difference with respect to the absorbing case, where the quasi-stationary distribution was simply the second eigenvalue, left eigenvalue of the matrix, independently of the starting distribution. In the non-absorbed case, the quasi-stationary measure depends on the eigenvalue corresponding to the eigenfunction in which there is a component of alpha. This, in a sense, is a little, at the first can be strange, in the sense that if an absorbing case can be obtained with a suitable limit of some parameter in the transition matrix, this dependence on the starting distribution alpha can be surprising. But especially what can be surprising is that if I change also with a very small change in the initial distribution, I can produce a completely different quasi-stationary distribution corresponding. So I want to use some very simple example in which all calculation is very simple, in order to explain why one can apply this theorem, and why how one can discuss this dependence on alpha. Okay, is it clear almost? Okay, so the first case, very simple, is this homogeneous triangle. So of course the invariant measure for this chain is 1/3, 1/3, 1/3. This is the uniform distribution. And the eigenvalue also is immediate to see that there is 1, and then 1/2, 1/2, 1/4, 1/4. And one can also very simply compute the orthogonal spanning, eigenvector spanning. So one obtains very simply nu2 and nu3. Okay. Note that, of course, nu2 and nu3 have some 0, because they have to be orthogonal to the right eigenvector 1. I mean, so and these are also orthogonal from 1 from chart. And given the distribution alpha, so I call alpha 1, alpha 2, alpha 3, one can write this alpha in this basis of pi, which is uniform, and nu2 and nu3. Okay. So if one look at the system, it's very simple. This is a system of two equations in two incogniti, come si dice, vabbè, C2 and C3. And so one can solve this. And of course, assuming that alpha is different from pi, we necessarily have 1/4 as lambda alpha. No? So lambda alpha is clearly 1/4 because there is a degeneration in the second, the third eigenvalue are equal. And so one can compute explicitly this quantity. Since the sum of this was alpha minus pi, this is clearly, one compute immediately this. And one conclude that the quasi-stationary measure in this case is 1 over lambda alpha this plus pi. This was a formula. And so one compute that this is the quasi-stationary measure in this case. Of course, that depends on alpha. If alpha change, this change. Of course, there is one of this entry which is equal to 0 because one of alpha 1, alpha 2, alpha 3 is the minimum. And so one can immediately obtain. Actually, this is not very surprising because alpha can be written as alpha min, alpha min, alpha min, plus alpha 1 minus alpha min, alpha 2 minus, of course. And so this can be written exactly in this way. And but looking at our chain, actually our chain can be written as a sum of two possible steps. With probability 3/4, I have a chain that immediately go to equilibrium in one step. And with probability 1/4, I stay where I am. And so it's clear that the quasi-stationary measure must be the component of alpha, which is not already in pi. Okay, so this is clear that this is the conditionally stationary measure. Okay. Okay. One can, in a sense, generalize this to a little more complicated Markov chain in which we have 2n states divided in two classes, x1, x2, of the same size, and assuming that the transition matrix Q is 1 minus epsilon over n if x and y belong to the same class, and epsilon over n otherwise. And so for some epsilon in 0, 1 alpha. In other words, if I call J the n by n matrix having all entry 1 over n, then I can write A 1 minus epsilon j and B epsilon j and write the transition matrix in this way. To avoid the existence of zero eigenvalue, one can consider a lazy version of this, and this is very simple. And then one can, due to the symmetry of the model, one can compute the eigenvalue. There is 1, of course, and then lambda 2 is 1 minus gamma multiplied by 1 minus 2 epsilon plus gamma. And then there is a lambda 3 equal gamma with as a multiplicity 2n minus 2. So there is all this multiplicity. And also one can compute the eigenvector, associated to lambda 2 and to lambda 3. Okay, this is a computation which is, is very simple using the symmetry of the model. We point out that the W vector and also the Z are not orthogonal but are linearly independent, and then there are a lot of orthogonal conditions in this set of eigenvectors. And what one can prove is that, so knowing all the spectrum, all the eigenvectors, one can apply our theory, so one can compute everything. So if alpha, the starting measure, gives more mass to x1 with respect to x2, then phi star, the quasi-stationary distribution, is all concentrated in x1, as uniform in x1. If alpha gives a larger mass to 2, then the opposite, phi star is completely concentrated, uniform and completely concentrated on x2. And in the case in which they are equal, then one can compute and one can have in an explicit description. Just some remark. It's clear that case 1 and 2 are very easy to interpret. So the conditional, the quasi-stationary measure concentrates where the initial mass were maximal, and there it was uniform because of the symmetry of the model. In the degenerate cases, so in the third case, the Yaglom limit preserves the proportional between the two blocks, but since one has to have state in which the quasi-stationary measure is 0, phi star is 0, then this state coincides with the minimizers of alpha. Okay, but this maybe is, you have some, yes, some time to, probably the easier but interesting example in order to discuss the dependence of alpha. This is, I want to describe a metastable state, okay, a metastable chain. So I consider 3 states always because I have to make explicit computation. So, and I consider, in a sense, a random walk between these 3 states, in which the probability to each transition is exponentially small in a large parameter beta. And the quantities, in a sense, is the I that one has to, this is state 1, 2, and 3, the I that one has to overcome, the energy barrier, say, one has to overcome in order to make the transition, okay? So these are all the possibilities. This is a case in which A, the first transition, is larger than all the other, B, C, and D. And actually, I am supposing that D I suppose that D is the minimum, so there is a very large barrier to go back from D to from 3 to 2. Okay, so if beta is very large, the invariant measure is concentrated in 3. Okay, so first one can consider 3 as an absorbing state. So this is a very simple case, as one can use Friedin-Welzer theory. I mean, it's very simple. One can do explicitly all the computation. So if the state 3 is absorbing, so I am putting D equal to 0, then the reduced matrix is this one, and one can compute explicitly its spectrum, and also the corresponding eigenvalue. Okay, so one can compute everything. And if one looks, for instance, at the third case, the case in which the parameter C was A was this transition, B was this transition, C was the transition from 2 to 3. Is larger than the other one, so the barrier is smaller. So one has to put this condition in the, but every C, A, and B are exponentially small, so one can also make the approximation. So, and one can see that the eigenvalue goes like 1 minus alpha, okay? This corresponds to what one knows by the Frey-Wenzel theory, that the 1 minus sorry, not alpha. So the deeper well of potential in this case is a well in which the bottom is 1, so is given by the parameter A. So it e to the minus beta gamma, usually call it the maximal depth in the Frey-Wenzel theory. Okay, so and one has also the ratio of the quasi-stationary distribution, which is alpha over C, and A over C, sorry. So mu star is given by 1 minus, I mean, considering the normalization, one has this. So the mu star is exponentially concentrated on 1, on the deepest well. Also, if the Gibbs measure, also, no, ma perché va indietro invece che andare avanti? Dunque, no, ma perché non capisco? Sì, ma non capisco perché io sto spingendo la freccina di sinistra. Ecco, also if, in this case, 2 was as a larger Gibbs measure with respect to 1. But the 1 is the deepest well, so this is what is important for the quasi-stationary measure. So, okay, so the quasi-stationary distribution does not correspond to the Gibbs measure in 1, 2, restricted to 1, 2. Okay. Okay, now go to the same example, but now without considering the absorption in 3. So D is smaller than all the other, okay? Sorry, it's not smaller than all the other. B is smaller than A. B is this barrier, I mean, it's the exponent of this barrier. Is less A equal D, so these two I are E are equal. Less than C. I choose this because with this choice, the computation are very simple. So this is the interest of this example. And so one can explicitly compute the eigenvalue, and one has eigenvalue 1 minus alpha, 1 minus A, and 1 minus A plus B plus C. And left eigenvector pi, S is the sum A plus B plus C, nu2 and nu3. Okay, so one can apply our theory, and so one can consider first the starting distribution, which is all concentrated in the site 2. Okay, and so applying our computation, one obtains that since 0, 1, 0 can be written as pi plus a constant multiplied by nu3, then it's clear that there is no component along nu2. So C2 is equal to 0. And so this one can immediately check that alpha 2, so the distribution concentrated on the second point, on the second state, is a fixed point of the evolution of the conditioned process. Okay, And so this means that alpha 2 is a quasi-stationary measure. Okay. This is the computation, but probably I have not much time to discuss that. Okay, this was the check that alpha 2 is a fixed point for the evolution in one step of the conditioned process. Okay. And now, if one considers the general alpha, one can apply the general theory and then find the G2 and G3 in terms of the component alpha 1, alpha 2, alpha I sufficient 2 because we have only just 2. Okay, so C2 is equal to 0 if and only if there is a particular condition among the component of the initial distribution in 1 and 2. Okay. This is verified for the distribution 0, 1, 0, as we discussed in the previous slides, but also, for instance, by this initial distribution. Okay. And actually, one can find what happens in general. So if C2, for a general alpha, if C2 is larger than 0, then one has that the Yaglom limit is this one. So it's 0 in 3, and C plus B, so this is exponential concentrated in 1, and exponentially small as A in B. As A over C, say C is the larger. And if C2 is equal to 0, but C3 is larger than 0, one has the 0, 1, 0, so the quasi-stationary distribution that we discussed before. And otherwise, one has, if C2 is equal to 0, but C3 is less than 0, one has this case, so the 0 is in the state 2. And if C2 is smaller than 0, then one has this as a quasi-stationary distribution. So, I mean, the point that with a small variation of alpha, one can obtain a completely different quasi-stationary distribution is really is true, but one has really to have very particular choice for alpha in order to have C2 equal to 0, for instance. Okay, so it's very, it's true that the quasi-stationary distribution depends on alpha, but this dependence is very, very not robust. I mean, it's sufficient to change a little the initial distribution for remain in the case in which C2 is different from 0. So it's a second eigenvalue as in the absorbing case that determine the. I stop here because time is over. Thank you very much.
Thank you very much. So are there any questions? Paolo?
Very general and naive. So is this notion of quasi-stationary distribution for the non-absorbing, so with a strong stationary time, really the good notion for metastability, for studying metastability phenomena in general?
No, in the sense that usually metastability is in the limit beta to infinity. So I mean, so is an asymptotic regime, and so the absorbing case is usual frame in which one discusses metastability, okay? But we think that the more obvious generalization of the quasi-stationary distribution to the non-absorbed case is to replace the absorbing time with the time to reach pi, so to the strong stationary time. So this was the, we obtained this, dependence of alpha, which is a little strange, but I think that it can be. Lorenzo Ride. No.
So do you have an example in which the strong stationary time can be, sorry, do we have an example where the for some alpha, the strong stationary time can give some pathwise expression? Not as a eating time of something, of course, but some.
Yes, yes. One can construct. This is Phil and other people. One can construct another chain in which one describe tau pi. I mean, the strong stationary time as the eating time to a certain set of states. In this new chain, one has to enlarge the state space, and yes, one has to see. We have not done this. I mean, it's I repeat, it's a work in progress, and I was very interested in your comments. This is clearly a direction in which one has to investigate and to say something, of course.
Okay, thank you. Are there other questions? No, if not, thank you, Elisabetta, again. So we have the pleasure to welcome Michele Pavon. So, Michele, the floor is yours.
Thank you. Sorry for all these difficulties. The purpose of, first of all, thanks the organizer for giving me a chance to participate and to celebrate this very young scientist. So at least Wolfgang and I can say so. And so I wanted to talk about a paper that Paolo wrote in 1991, so he was pretty young, and which is a bit outside of the topics of this conference, but which has had and is having more and more impact. So could you, it's a long story that starts with Gaspar Monge in 1981. We can skip a few of the slides. You can go ahead. Go ahead, please. Go ahead. Okay, let's go to the mathematical formulation of Monge's problem. It is the optimal mass transport problem. You have two probability measures, and you want to find a measurable map T that pushes the first measure onto the second, okay, and minimizes a cost of that form, okay? And this is actually a pretty hard problem. It may be unfeasible. For instance, if the first measure is concentrated at one point. Let's go ahead. Okay, the other turning point, I'm skipping a lot, of course, in this historical overview. The other major step comes with Kantorovich in 1939. Okay, you can go to the next slide. So this is a fundamental contribution. He is the founder of linear programming and of duality theory. Go ahead, please. And he gives a relaxed version of Monge's problem. He's not aware of Monge's work. And his relaxed version is the following. You want to minimize this cost over joint probability distribution on the cross space, on the product space. This joint probability distribution need to have nu0 and nu1 as marginals, okay? And first of all, this problem is always feasible, okay? And under very reasonable assumptions, this problem has a solution, okay? And what you see at the bottom is the first duality theorem in history in an abstract setting, because he had actually a functional analytic background. And what happened is that a few years after he started working on this problem, he attended a historical talk, because it was 200 years since Monge's birth. And then suddenly he realized that his potentials, as he called them, his dual variable, we would call them, phi and psi, could be related to these surfaces, these manifolds that Monge had already the intuition that they should be, that the optimal trajectory should be orthogonal to certain manifolds. So there is the connection. Okay, you can go ahead. Okay, the original Monge problem has caused the distance, and that's pretty hard here and in many other problems. For instance, uniqueness is not guaranteed. But if we take the square of the distance, then in 1991, we have another turning point, a very, very important theorem by Brenier, okay, French mathematical physicist, who says if the first measure has a density, okay, then there exists a unique optimal transport plan, namely this joint distribution in the sense of Kantorovich, and actually it is induced by a Monge map. Okay, not only that, but the Monge map is the gradient of a convex function. Okay, this is of paramount importance in many proofs in functional analysis, in many applications, and the problem, since then has witnessed an incredible number of applications in just about any field of science. Let's continue. Okay. This field has impacted many fields of mathematics. Of course, analysis, probability, of course, mathematical physics. Think of the application that Alessio Figali did, okay? And geometry, because it turns out that in spite of the abundance of distances that we had before on probability measures, okay, the one induced by this optimization problem is a bona fide distance, first of all. Second, it's a natural one. It metrizes with convergence, okay, with some extra condition. And therefore, we have a beautiful separable complete metric space, the Wasserstein space, okay? You can continue. Okay, why is this distance between probability distribution so important? Let me try to give you some intuition on this, in case probably many of you already know it, but if you don't know it, it's good to have it. Suppose you have two masses on the plane, okay, which you see depicted at t equals 0 and t equals 1. If you do the affine interpolation, namely the convex combination, okay, this is what you're going to see at the intermediate times, right? Okay. This, which may look natural to some of you, is a disaster. And to understand why this is a disaster, think of those masses as made of pebbles, okay? The pebbles jump with infinite velocity from one bunch to the other. Infinite velocity. So this is not physical, it's not natural, and it causes disasters in application. If you use this, for instance, in image processing, you will get this fade-in, fade-out effects, okay? Or if you like, the push-pop effect. But if you use the Wasserstein metric, see what happens. The mass, the bunch moves correctly, smoothly from the first location to the second. And of course, a lot of people have understood that this was the metric to be used in many applications, computer graphic and so on. In fact, computer scientists, of course, jumped into it. They call it the Earth mover's distance. And so I think we have a fantastic theoretical development, parallel by an incredible number of new applications where this distance has proven to be the right one. Okay, we can continue. Okay, another turning point happens in the year 2000. Benamou and Brenier again, okay, give a fluid dynamic formulation of the problem. So from the static, we have now a somewhat dynamic formulation, which was somewhat hinted by Mons himself. And of course, you start looking at this and if you are from control theory, you will start thinking that maybe there's some control problem around, okay? The stochasticity here only comes from the marginals for the time being, okay? Nevertheless, you start thinking, if you are degenerate enough having spent your life in control theory, you will start thinking in that direction. Let's go to the next slide. Okay, the interpolation is very, very interesting. The one that occurs with the Wasserstein distance, okay, it has been named displacement interpolation, and it has been recognized as a somewhat a constant speed geodesics. Otto is the one that pushed this viewpoint because it satisfies that relation, and therefore we have a formal Riemannian structure on an infinite dimensional space, which can be made precise in some special situation, okay? Here, I'm mentioning things, most of my presentation I'm gonna mention, besides Paolo's work, things that I have been involved with, because I know them better, okay? For instance, that geometry allows you to study some variational problems on the space and gives new insight in fields like stochastic mechanics, various versions of stochastic mechanics, the Bohmian, the Nelsonian, and so on. Let's continue. Okay, finally we come to Schrödinger bridges. So Schrödinger is 1931. Schrödinger is desperate the way quantum mechanics has been established. In very few years, from 1924 to 1930, quantum mechanics has taken the shape that it has today. Okay, and of course he's quite unhappy, and as Einstein is, and so on. So he's trying to find a more classical version of quantum mechanics, and he writes two papers, 31, 32. So here is the situation, the Gedanken experiment, okay, which he's thinking about. He says, I have a very large number of independent Brownian particles, and I have two distribution, the empirical distribution are approximately equal to rho 0, rho 1, okay, the densities. And however, the two densities are not compatible with the transition mechanism of the Brownian motion. So something exotic has occurred, right? Because n is very large. Think of Avogadro's number, okay? So something very unlikely. And yet, of the many unlikely ways in which the Brownian particle might have been transported, they have not been transported as Brownians. They have been transported in some other way. And he clearly states the problem, which one is the most likely of these exotic way in which they might have been transported. So this is the second large deviation problem in history after Boltzmann 1877. And it's interesting that both are to this day ignored by Wikipedia, who thinks that large deviation starts with Hara-Cramér in the 1940s. Okay, let's continue. Now, notice that Schrödinger is attacking a very abstract problem, okay, at a moment when we do not have any theory of continuous parameter stochastic processes, and yet he's using the tools that Boltzmann used, coarse graining, Stirling approximation, and so on. And he basically almost solves the problem. He reduces the problem to the Schrödinger system, to this couple of linear equations, which, however, have a non-linear coupling at the endpoint, okay? And he noticed this remarkable analogy with quantum mechanics, because you have reversibility. If you swap the two marginals, rho 0, rho 1, the solution is simply the time reversal of the previous one. Okay, and you notice the factorization, which you also have in quantum mechanics, two adjoint equations, so there are impressive analogies. Let's continue. So what is the bottleneck? The bottleneck is to show existence for the Schrödinger system, okay? Uniqueness is uniqueness in a projected geometric sense, is the uniqueness of the ray, but that's easy. It is the existence which is really tough. Okay, there's a contribution by Bernstein, or Bernstein, I should say, who claims that he has solved something, but he does not. In fact, Robert Fauteuil, who writes the fundamental paper in 1940, he has some irony on Bernstein, who anyway gives an important contribution because he introduces the concept of reciprocal processes. Now, Fauteuil is ignored to this day. Fauteuil solves the problem. Not only does he prove existence, but it is a constructive proof. He has an iterative scheme. Okay, once you have the system, of course, the iterative scheme, how to design the iterative scheme might seem simple, but it is not, because you are on an unbounded domain. After each iteration, you lose the property of being bounded away from zero. So he has a very complex scheme with three sequences of functions, and yet he proves existence. Okay, let's continue. Okay, then of course there is the maximum entropy formulation. Okay, as it had already been noticed by Boltzmann. Okay, we have a maximum entropy formulation, minimizing relative entropy over measures that are equivalent to stationary Wiener measure and with the correct marginals. And in 1988, see how much later, Fermat goes back to the problem and states very clearly. In the meantime, large deviation, of course, had been developed, and he says, look, this is a problem of large deviation of the empirical distribution, and the connection between the maximum entropy and the large deviation is, of course, the bottom line, which, of course, all of you know much better than me, and Paolo in particular. Let's go ahead. And here we come to the, here we come. You see, this field, which has impacted so many areas, has also been developed in many areas of science that were not communicating much between them. Okay, so we have analysis probability, we have control theory, actually the mathematical side and even the engineering side, we shall see, statistics, classical statistics on contingency table, all of these fields had very poor communication for decades. So what is the situation when Paolo is going to write this paper? The situation is the following. Jamison, who has already contributed a lot to reciprocal processes, realizes that the solution to the Schrödinger bridge problem is an H-path process in the sense of Doob. This is what it was called. H is a space-time harmonic function for the prior, the original process, okay? Which in Schrödinger case was Brownian motion, but of course you can extend to any Markov process. And then there is a sequence of papers by first-class people in stochastic control, starting with Wendell Fleming, you see, starting in 78, in the 80s and so on, Karjasas, I mean, very, very good people who are not aware of the connection with the Schrödinger bridges. They notice that if you do a logarithmic transformation of a parabolic equation, you get a dynamic programming equation. Okay, you get a Hamilton-Jacobi-Bellman equation, and therefore there is a stochastic control problem, and so on, so on. But they had not made the connection to the Schrödinger bridges. And then here comes Paolo, who is back from his doctorate. Of course, you know, he had learned stochastic control, I think, in Italy already, and then, of course, in at Rutgers and in New York with Varadhan. He had learned, all that could be learned on large deviation. So he writes this paper, a stochastic control approach to reciprocal diffusion processes, where I'm going to show you it is finally made very clear and precise that you can think of the Schrödinger bridge problem as an atypical stochastic control problem because you have also a final constraint on the state, okay? Of course, there is other work, but could we go to the next slide? But the point, you see, here is the abstract, okay? Problem forcing non-degenerate diffusion to a given final configuration is considered using the logarithmic transformation approach developed by Fleming. It's shown that the perturbation of the drift suggested by Jamison solves an optimal stochastic control problem. Such perturbation happens to have minimal energy between all controls that bring the diffusion to the desired final distribution. And then he also proves invariance of the most probable path. Now, look at the bottom of the definition, problem P. Find an admissible control U star such that the initial condition is distributed according to mu0, the final is distributed according to mu t, and between all admissible controls, okay, satisfying one, U star minimizes the cost function. So the formulation is very clear. And in a sense, I would like to say, as it happens sometimes in life in many other situations, this contribution is at the right moment, at the right place. Because it represents a bridge. We're talking about bridges, right? Schrödinger bridges, okay, between fields that had not communicated, okay? And of course, it was in the air. There were things, Kolbinger had tried the variation representation, but it was more in the spirit of stochastic calculus of variation, saying this is a stochastic control problem, had a major impact. And if you give me, now, of course, I'm going over time, but if you give me a few more minutes, I could at least try to give you an idea. When should I stop? I don't want to take too much of your time.
Now you can take 5 minutes if you want.
5 minutes. Okay. Let me try. Okay, let's go to the next slide. Thank you. So now we have this Schrödinger bridge problem as a stochastic control problem, etc., etc. Notice that the Schrödinger bridge problem, if you ask people in optimal mass transport, they will tell you it's regularized optimal mass transport. That's all they can see. And it is. We will see that, okay? However, the Schrödinger bridge has two other important interpretations. First of all, Schrödinger's original statistical mechanical motivation. And second, this has generated an enormous amount of literature as inference method, okay? You see some of the names of the people that have, contributed the most to that. Okay, and then you have all the applications and some are also modern. In the discrete setting, you have work that started with Synchron in the 60s, okay? A lot of people only know Synchron, they don't know, and some don't want to know the connection with the Schrödinger bridges, okay? But there are very strong groups in France who have contributed a lot, okay? Let's continue. Okay, now, instead of the stochastic control problem, okay, but it is immediate once you know the stochastic control problem. What could actually look at this in the fluid dynamic form of Benhamou-Brenier, okay, like a steering problem for probability densities. Once you get this idea is incredibly fruitful. So it is like a relaxation of a most central problem in optimal control, the steering problem. You want to move a spacecraft or a robotic arm from an initial state to a final state with minimum energy. All right? What is a natural relaxation? Okay, those hard constraints, initial and final constraint, you replace with a probability distribution, like a Gaussian center, at those points. And this has led to an enormous amount of application. There are two versions of the fluid dynamic. Okay, let's continue. Okay, and finally, what is finally the connection with optimal mass transport? You see, it came actually not so long ago, 2004. Mikami, a student of Wendell Fleming, proves that as the noise tends to zero, the solution of the Schrödinger bridge, gamma converges to the solution of the optimal mass transport. Now you say, okay, that's a beautiful mathematical result, who cares? You should care a lot, because optimal mass transport is a beautiful theory, fantastic theory, but it has one weakness. It is very hard computationally, whereas the Schrödinger bridge has that iterative scheme that Forte started, and then it's called also synchronous and many other names. So you have effective algorithms. So you just add a little noise, and you can do an entropic interpolation, for instance between images. Okay. Now, of course, there were many other sides to it. What probabilists had done in the 90s and so on, they thought that the field was closed. Vakorbingen writes a survey in 1992, but they were studying a very special problem, which, by the way, excluded most engineering applications. So there was a lot to be done. Totally independent, you see this covariance control, these are engineers, control engineers that were studying a problem on the infinite horizon, which is also interesting, okay? And of course, in the Gaussian case, you can say much more. Actually, Paolo has this scalar Gaussian case in his paper, and so on. I think, I don't know what comes after this. Maybe you can go ahead. Okay, we can stop here. We have been working on many different aspects. There are many interesting problems, but the message I want to get through is that this paper really opened a new avenue, and then with the fact that you can view the Schrödinger bridge as a regularized version of optimal mass transport, it has led to a number of interesting applications. If you go to the very end of my slides, you see there are examples of, go fast forward. Okay, there are examples, of interpolation with using the Schrödinger bridge. Go ahead. When you reduce the noise, and then also image interpolation, so entropic interpolation, there are many things here. Okay, this we don't have time to read, but I recommend that you read the Schrödinger paper has been translated literally, and it is stunning even to this day what it says. Okay, sorry for going over time.
Thank you very much, Michele. A very short question maybe for Paolo, or a short remark?
Very, very short. Thank you, Michele. Really deeply grateful to you for this reconstruction, historic reconstruction. By the way, the 1940 paper by Attal, I think is the name, I was not aware of, so I admit that I...
Okay, thank you. Yeah.
Yeah, I'm, should I? Yes. Am I audible? Can you hear me?
Yes, yes, yes. Thank you.
Okay. All right. So thank you so much. Thank you to the organizers for inviting me to this. I wish I could be there in person, but well, at least I can be there virtually. So I'm going to talk about interacting urns with multiple drawings. This is joint work with my PhD student Yogesh. And before I start, I must mention that this is an area which Paolo introduced me to. So it's only apt that I talk about it in this workshop. So I'm going to start with some very basic classical urn models to set the context. So I apologize to people who already know all this stuff. All right. So urn models essentially fall under this large class of problems known as random processes with reinforcement. And over the years, urn models have found applications in various areas. I mean, there have been very recent applications to model to understanding how ants walk on a graph, let's say, or random growth models and so on. And indeed, in 1957, Polya himself said that any problem of probability appears comparable to a suitable problem about bags containing balls, and any random mass phenomenon appears as similar in certain essential respects to successive drawings of balls from a system of suitably combined balls. Thought it's a nice quote for someone who is working in the area. It's a nice motivational quote to think that a lot of problems can actually be reduced in terms of, by thinking in terms of urns and balls. All right, so in 1923, Polya gave the definition of the Polya urn process, which is the classical urn model. So the process is as follows. You have an urn which contains finite number of balls of different colors. So I'm going to stick to balls of two colors throughout this talk. So on models with balls of two colors. And at any discrete time step, a ball is drawn from the urn uniformly at random, and it is replaced in the urn along with a constant number of balls of same color. So various extensions, variations of this process have been studied over the years. For example, the most popular one is the Friedman urn, where a ball is drawn uniformly at random, and then a certain number of balls of the same color and a certain number of balls of the opposite color are reinforced in the urn. The most celebrated result of Polya is that if we are looking at the fraction of white balls in the urn at time t, that converges almost surely to a random variable, which is distributed as it has the limiting distribution is beta distribution with appropriate parameters. So this is the celebrated result, the most well-known result in the area. And so what happens when you change the process a little bit? Let's say if you go to Friedman urns, the asymptotic behavior changes radically, and in that case, the fraction of balls of white color converges to 1/2 almost surely. Okay, so over the years, like I said, people have studied various extensions of these kind of processes. I'm going to talk about two directions in which work has happened recently. So the first one is urns with multiple drawings. So in this case, at each time step, instead of drawing one ball, you draw a fixed number of balls, let's say S number of balls. And then depending on what you see in the drawn sample, you reinforce the urn. So again, this was studied by Chen, Wei, Kuba, Mahmood, and all these people recently. I mean, these are papers in 2005 and 2013. And they classified this as, the reinforcement was classified as Polya type and Friedman type, depending on which color reinforces which color. So if in your sample you have R white balls, then you add a constant multiplier here is significantly different from the classical Polya process, because at every step you are adding balls of both color. And indeed, the limiting distribution in general is not known in most these cases. I mean, in these papers, they do talk about asymptotic behavior of fraction of white balls. They compute certain moments of fraction of white balls or fraction of black balls, let's say. But a general description of the limiting distribution is not known. Okay, so this is one direction, and the other direction is interacting urns. So by interacting urns, I mean that you have more than one urn. So let's say you have n urns, and the reinforcement in each urn now depends on either all the urns in the system or a non-trivial subset of the given set of urns. So more precisely, if I have to write this mathematically, you have n urns with WTI and BTI being the number of white balls and number of black balls in ith urn at time t. And if this difference WTI BTI minus WT minus 1i, BT minus 1i, this is the reinforcement. So this is the number of white balls and black balls that you are adding to the urn at time t. Right? So we are going to assume that the reinforcement is non-negative in the sense that you are always adding balls, you are not taking out balls. That kind of models have also been studied, and it's finite. And further, that this reinforcement, this is conditionally independent given the past. All right, so by interacting urns, I mean that the evolution of ith urn depends on the urns indexed by I1, I2, IKI, let's say. Right? So in other words, the distribution of this reinforcement is determined by number of white balls in these KI urns. Right? So this I1 IKI can be called as the dependency set of the ith urn. And so in particular, if you are looking at, let's say, urns on a finite graph, a natural choice of a dependency set is the neighborhood of urns. All right, so this sort of interacting urns have also been studied extensively, and I have put some of the papers by Paolo here. So the first two are specific to interacting polia urns. The last one is not exactly about urns, but it can be interpreted as urn processes as well. It is about interacting reinforced random walks on graphs. And like I said, the first two are specific to interacting polia urns. So the reinforcement in each urn depends on what you draw from the urn, and it also depends on the entire set of the urns. So in some sense, a complete graph. So you look at all the urns, and you also look at that specific urn, and based on that, based on what you draw, you reinforce the urn, and all urns are reinforced simultaneously. All right. So what I'm going to, the work that I'm going to talk about essentially combines these two. So it's about urns with multiple drawings and graph-based interactions. Okay. So we have a finite graph with n vertices, and at each vertex, I have an urn with non-zero number of balls of two colors, so white and black, let's say. And I'm going to assume, so I'm going to talk about, I think I didn't mention it anywhere, but I'm going to only talk about undirected graphs. You can do the same thing on directed graphs, it becomes a little more complicated. And the results are different, but I'm going to stick to undirected graphs. And I'm going to assume that the graph is connected, because if you have a disconnected node, then there is no interaction happening there in that urn. Okay. So like I said, the urn process is two-phase. First you sample and then you reinforce. So let me describe how you sample here, and I'll then tell you how to reinforce. So since it's a multiple drawing urn, so from each urn you draw S number of balls uniformly at random with replacement with probability P. And with probability 1 minus P, you look at one of the uniformly at random, you choose a neighbor of that urn in the graph. And then you look at the sample drawn from that neighbor. Right? So you are drawing from the urn and also from a randomly chosen neighbor. With probability P from the urn and with probability 1 minus P from the randomly chosen neighbor. And now the reinforcement can also happen in multiple ways. You can choose to reinforce based on what you draw from each urn. You can choose to reinforce a certain subset of the urns. And of course, what we said earlier, it could be Polya type or Friedman type. So in that sense, the first thing that I said, the first level where you decide which urns you reinforce. So you can have self-reinforcing. So each urn there, looking at the sample that has been drawn, reinforces itself, or it reinforces all its neighbors, or it reinforces itself as well as the neighbors. And then the color reinforcement essentially classifies whether it is Polya type or Friedman type. So based on the sample that you see, whether you reinforce the same color, so if you have R white, do you reinforce C times R white, or do you reinforce C times S minus R white? So there are 3 parts here, 2 parts here. So we'll end up getting 6 types of reinforcements in total. So I call Friedman type self-reinforcement, Friedman type neighbor reinforcement, Friedman type self and neighbor reinforcement, and so on, right? And similarly for Polya type. Now, those of you who are familiar will see that some of these models will eventually be similar, especially for extreme values of P. So quick observation that Friedman type self-reinforcement with P equal to 0, what is happening is you are always sampling from a randomly chosen neighbor and the urn is being reinforced. And for FTNR with P equal to 1, balls are sampled from the urn and neighbors are being reinforced. So you are essentially doing the same thing and therefore they exhibit the same asymptotic behavior. Similarly for PTSR with P equal to 0 and PTNR with P equal to 1. Okay. So, I mean, once you write this mathematically, it's very clear that they are similar, but one can also just look at what is happening in the process and see that this is indeed the case. Okay, so again, the main question going back to what Polya asked is the same. What happens to the fraction of balls of white color? Okay. So now instead of having ZT, I have a vector ZT, which is a fraction of balls of white color across urns. So I want to understand how this ZT behaves. All right, so for that, let me just introduce some notation. So the first observation is since we are adding the same number of balls in every urn. Okay, this is not same across urns because it depends on the degree. But if you fix an urn, the number of balls that you are adding in that urn at every time step is same. So each urn is being reinforced using a balanced scheme. This is what a balanced scheme is called. Yeah, this is what we mean by a balanced replacement matrix or a reinforcement matrix. So the total number of balls at time t plus 1 is just total number of balls at time t plus whatever you are adding, which I said does not change with time. So it's total number of balls are growing linearly in time. Now, what about how the number of white balls are growing? Because eventually we want to understand how the fraction of white balls is growing. So let yt plus 1i be the number of white balls sampled from the urn I at time t. So in general, I can write a recursion for Polya type and Friedman type. So number of white balls at time t plus 1 is number of white balls at time t plus what you add. And what you add depends on which type of reinforcement, which type of color reinforcement you are doing and which type of urn reinforcement you are doing. So I can just combine all of these by taking my suitable values of eta and kappa will give me, so all the 6 models are essentially there in front of you. Okay, but I still have to tell you what this yt plus 1, how it behaves. So I can write the conditional distribution of yt plus 1. So yt plus 1 is, just to recall, is the number of white balls sampled from urn I at time t. So it is k if out of S balls drawn, you have chosen k white balls, and that happens with probability p you are drawing from the same urn. So that happens with probability equal to the fraction of white balls in that urn times 1 minus the fraction of white balls to the power the number of black balls that you have drawn. Plus 1 minus p times, now you want to choose a random neighbor, which happens with 1 over dj, which is the degree of the node where your urn j is. And then you sum over this probability in the neighborhood. So this is what the distribution of y looks like. And then, of course, I'm going to combine everything in one. So I wrote down Polya type and Friedman type differently, but now I can just introduce this chi-t, which is ytj for Polya type and s minus ytj for Friedman type. So I can just combine all the recursion into one, and I can here I can divide by total number of balls to write a recursion for zt I. So this is my main recursion for, and all the models that I have talked about are captured here. And then because I know the conditional distribution of yt, I can say, I know the conditional distribution of yt, and I've written conditional expectation here because it has a neater expression and it is more useful when I analyze it and analyze the model. All right, so what can we say about these models now? So the first result is on Friedman type color reinforcement system. So in most cases, the Friedman type goes to 1/2, which is expected. The two cases where it does not go to 1/2 is when there is self-reinforcement, P is equal to 0, and the graph is bipartite. And similarly for FTNR, I've already said that FTSR for P equal to 0 and FTNR for P equal to 1 behave similarly. So it's not surprising that you get the similar results. So what this theorem leaves out is what happens when your underlying graph is bipartite. Okay. So the main idea behind proving this is to just write the stochastic approximation scheme for ZT. So just to quickly go over what a stochastic approximation scheme is. So you have this sort of recursion for a vector in Rd. So your xt is in Rd. So xt plus 1 is xt plus this quantity, where your mt is martingale difference sequence. Your gamma t are called step sizes, and so the sum of gamma t is infinite, but sum of gamma t square is finite. So they are going to infinity, but not too fast, let's say. And the function h is Lipschitz. So under these conditions, the stochastic approximation theory says that the iterates of this recursion converge to the stable limit point of the solution of the ODE given by this. So x dot t equals hx. So what I can do is I can write a stochastic, so I can write my recursion for zt in this form, and then just look at the ODE and then see where, if the unique stable limit point is indeed half. So you can actually do that. You can write the recursion for zt in the form of the stochastic approximation scheme. And then you get this h, which is, well, it's a linear function of zt. So it's Lipschitz. And these are the various forms of h that you get in all the 6 cases. So now what remains is to analyze these h functions. And so the first thing is quite immediate. You just look at the Jacobian of h and you see that the real part of each eigenvalue is non-positive. So if you have a unique solution, it is indeed stable. And to say that there is a unique solution, you have to prove that these matrices that are associated with the in the h function are invertible, which requires some work, especially in case of self and neighbor reinforcement. So I'm not getting into this, but this is the main idea. So, sorry, is there a question? I could hear some noise. Can I continue? Okay. So, like I said, what I left out was how these the FTSR model on bipartite graph. So let me go to that now. So again, we use the same idea. We use the stochastic approximation method, but for a more specific case. So this is sort of a another way of looking at stochastic approximation method. But in this case, your h is actually, sorry, this should not be minus of grad f, it is grad f. So when your h is actually gradient of a function f, one can look at the zeros of gradient of f and say that your xt actually converges to this x star, which satisfies grad f x star 0 with probability 1 on this set. Well, for us, this set is fine because we are looking at fraction of balls of a certain color under certain conditions. So, so let me just quickly go to the conditions. So the step size condition is still similar. There are 2 other conditions. So the first one, I'll maybe, sorry, the second one I'll explain a bit, and third one I will try to skip because I don't have that much time. So the second one is essentially saying that, so these gamma i's are partial sums of your step sizes. And beta is the process which will be the martingale difference process when we write down our. So this this partial sum from n to k is essentially almost surely finite. That's what it is, right? As n goes to infinity. Okay, so how do we, I mean, once we have this, we have a description of how the system behaves, how xt behaves as t goes to infinity. Okay, so so we write down the recursion of zt in this case, and now I'm going to restrict myself to the case of regular graphs, and I'll tell you in a bit why. Because so once I have a regular graph, I can rewrite my recursion, and it becomes slightly simpler. And why I need regular graph is because I want to write my h function as a gradient of some function f. So if I have regularity, that f comes out to be a nice function like this. So your x is a matrix. So here my x is a matrix which is dependent on the adjacency matrix, and x and y are both symmetric because I have an undirected graph. And it turns out that this f indeed works. So if I look at the gradient of f, I will get back my h function from the original recursion that I wrote for zt. So using this, I can have a similar recursion like this, and then I have to check that it indeed satisfies these three conditions. Like I said, I'm not getting into the details of all the conditions. The first one is quite trivial. It is satisfied because the step size is still 1 by t, like you can see here. So at is 1 over something linear in t. Okay. So let me talk about the second condition a bit. So remember I said that the beta I process that remains is actually your martingale difference process. So I take r equal to 2 in that assumption. And what I get, if I define st to be like this, I can show that st is also a martingale. And since I know that my at is like 1 by t, remember my gamma is the partial sums of at's. So it's like the kth harmonic number. I know that this is finite. So hn to the 4 divided by n square is finite. And I'm looking at hn to the 4 because of this. So I want to show that conditional expectation of the difference of these martingales, this si plus 1 minus si, this is finite. So here I'll get gamma I to the 4, which will give me hn to the 4. Right? And alpha I square, sorry, this is not alpha, this is ai. So ai square will give me 1 over n square. And that whole thing turns out to be finite. And therefore, I can show that this sequence st is almost surely Cauchy. That gives you the second condition, essentially, this one. So this was just a way to show that you can actually indeed verify these three conditions for an appropriately written recursion for zt. And therefore, using the...
Sorry to interrupt you. If you could finish in 3 minutes, 3-4 minutes, please. Thank you.
Okay, I'll try. Sorry. Yeah, sure. So I'm done with this part, and I'll just show you the results then. Right. So the result now is that the bipartite part was left. So on a bipartite regular graph, you see that on one partition everything goes to the same limit, and on the other partition everything goes to the 1 minus of that limit. But the limit is indeed random in this case. So similarly, you can do the same thing for Polya type because I wrote down this general recursion. This is for Polya type and Friedman type. You can get this f. So a similar result for Polya type is also true. So maybe I'll just mention a couple of things more. So like I said, the proof is simple. The convergence is already guaranteed if you have verified the three conditions. To classify the zeros, you have to again go back and look at how the grad f looks and do some rank analysis of the matrices to say that the rank is indeed n minus 1 in cases when you are getting, in this last case, for example, when you're getting that on one set you have some limit and on the other set you have some other limit. Right? So the last thing that I want to mention is that this regularity condition, I would still want to get rid of that regularity condition on the graph, which you can do by assuming something else, which is more general. So we assume that the adjacency matrix times the D inverse, which is the degree matrix, the diagonal matrix of degrees. If this is diagonalizable and if the initial number of balls across runs is same, I can still prove the same result, which we did using stochastic approximation, but with regularity condition. So I can get away with this condition of non-regular graphs. And so very quickly, there what you need to do is on each partition, you look at the weighted mean of the fraction of balls of each color. You show that the overall vector attains an almost sure limit, and you show that on each partition, ZTI minus this average mean, this difference is going to 0 in L2 and almost surely. Well, you only need almost surely here, but you can also show it that it goes to 0 in L2. And then again use stochastic approximation to show that this sum of the mean is going to 1. So that will give you that on one partition, if the limit is C or Z, then on the other partition, it is 1 minus Z. Right? So that last part clinches that Z1 minus Z, which is not true in Polya case. You don't have this kind of behavior in Polya case, but only in Friedman case. Yeah, I think I'll stop here just to mention. So in addition to this, one immediate offshoot of using stochastic approximation is that you can also get CLT sort of results. But I put them here, but I'm not going to explain them. Yeah, so thank you.
Thank you very much, Nirja. Maybe a short question, very short or not? No, okay. So thank you again, Nirja. Thank you also for your patience because we postponed you a little bit. Thank you. And we can have a short break now. And we will start again at 5. Welcome back. So this is our last session or sessions part. And so maybe you can connect us. So it's a meeting with lots of surprises for both Paolo and the organizers. So we have a special guest from Berlin. So Alexander, maybe. Okay.
Ciao,
so
Paolo.
I'm giving you the floor.
I mean,
if you want to talk.
Okay, so I just wanted to say hi from Berlin to Paolo and to wish you a happy birthday conference. That's it.
Ciao Alex, ci vediamo presto, grazie, ciao.
A presto, Paolo.
Okay, so thank you, Alexander. Yes, so now we have the pleasure to welcome Sylvie. And briefly, before, just to mention, because the question was asked how I personally met Paolo, and actually it was through Sylvie, because I started my PhD in Lille under the supervision of Sylvie, and I remember the day she asked me if I would agree to go to Italy to work with an Italian colleague, and that's how it started. So these were very important steps in my life, personal and scientific. So thank you. Happy birthday, Paolo. And Sylvie, the floor is yours.
Thank you very much. Is it functioning? Okay. Pierre, perhaps no. So, thank you very much that you stayed till now. First, but not least, I would like to thank, in name of all the participants, the sextoire of organizers who did really miracle miracoli. So it was not almost everywhere were perfect, but it was really totally perfect at all levels. Logistically, from a scientific point of view, everything around this room, incredible, the music and so on. So for all that beautiful context, thank you very much. So naturally, I am very, I don't know if it is correct in English, so emozionata, emotional, perché because we had a long way together, or not together, but parallelly and with a lot of meeting points with Paolo, and so since 26 years, we had we developed different thematics, and had the very deep pleasure to supervise several students together, and so it was not simple for me to think about a topic which could be for you of interest and new, because as several colleagues said, so with you what is really very pleasant is your continuous curiosity and way to develop new things with new methods. And so I thought, okay, I will not speak about some topics we discussed together, like, for example, time space Gibbs measures or PCA, or, but on some topic I discovered a short time ago, which is related to physical phenomena, which looks to be very important, but I didn't know anything, and is called depletion force. And indeed, the reason also why I took that decision to speak about that is that the situation in which I heard about that, it was in 2019, meeting, a conference in Yerevan, organized by Suren Pogosyan, and we spoke about him some minutes ago. And at that conference, there was Sabine Janssen and Dimitrios, and they spoke about that. I will explain in which way. So I thought that to speak about that here in L'Aquila, in presence of Dimitrios, is a nice coincidence, say. So what I will speak about is a work in progress, and it is in cooperation with my colleague and friend from Lille, Myriam Fradon, with a PhD student, Julian Kern, and Alexander, and both are, Alexander is postdoc, and both are working at the Weierstrass Institute in Berlin. So yesterday there was some small, say, unstable situation related to the dessert. So the solution which was found was optimal, I think, but I was occupied with that during the night, and so I would like to offer you another solution, which is done by donuts, frying in some, you will see. So we have 7 donuts, and they are frying in oil. So you are not hearing it, is a pity, because the sound is very nice, so like that. And because everyone is very hungry in this meeting, so it is just wish you a good appetite. And what is indeed for me interesting in that story is that the relative position of the donuts inside of that oil are in some way surprisingly stable. And so they are moving. Globally, the system is moving, but there is some stability in the sense that they are not touching. And now the question, as physicist, I am not physicist, but could be, so does it mean that they are repulsing the neighbors, and everyone is repulsing, and so they are staying at the largest distance possible, one from the others? Or, at the contrary, can we interpret that with the fact that they are attracting the other, but each one try to attract the neighbor, and due to the form of this recipient, at the end, the stable geometry of that moving system is this one, with a regular distance. So we will try to solve this question. And indeed here, what is for us interesting, it is the fact that it is a system with two types of, say, particle, of element. We have the donuts, we are big, not particle, but big sphere, and they are in an environment which is done by a very large number of very small oil particles. So, and this is exactly this mixing between two very different elements, which is for us of interest, and we will look at that. No, it is not what I wanted to do. So this concept of binary mixture models is indeed in different communities well used since long time. So let me just say some words about the physical context. We found in the literature a lot of names for that. And here indeed, so I will try to use always the same name. So we will speak about suspension and colloids. So colloids will be our main central concept. So these are for us the donuts. These are colloids, and they have a certain size, which is not so small. And not so small, for the physicist, it means to be between these two sizes. And so these spheres, donuts, they are in a, say, fluid. It is the medium. And this fluid is composed for us by the small oil particles. And in the literature, it is referenced as polymers. So I am citing a paper published in 2014 saying that indeed this mixture of two very different components have a lot of applications, and for that it is a field in full expansion. The research about that is very active. But it is also very interesting for theoretical physicists, because indeed one can play on different parameters, we will see what, and have a full quantity of very different behaviors, and for that it is used also by theoretical physicists. So very quickly, just a few original references. The model, precise model on which we will speak in a few minutes, was introduced by two physicists or chemical physicists, Asakura and Ozawa. And then it was studied by different communities, and a very nice paper on that, colloidal dispersion, 76, as you see, published in a very applied journal. And then there is one part, evolution in more theoretical studies. And indeed, in this paper of Lecker-Kerker, Lecture Notes in Physics, there is more developed the theoretical part, and in particular, this word depletion arrives, and we will speak about this depletion interaction or depletion force. And what will be, so the idea between this is we have a mixture. Our model is these donuts in oil, and indeed the oil is not interesting for us. We are interested by the motion of the donuts, but this motion is indeed the a result of the medium, so the oil particle. So the oil particle, even if we would not like to look at it, they are interacting with donuts, and the trace of that interaction implies, so create a new interaction between the donuts, which is this depletion. I will precise this in a few minutes. But before I do that, I would like to recall historically extremely well known example, old Brownian motion, which was for the first time identified as motion by Brown, so 19th century, and it was exactly that. It was a binary system. There was the pollen particle, so pollen object, say, this was one of the components, and this object was in the fluid. So you had, indeed, a binary system in which the large object showed motion, and the question was, where does this motion come from, and what is behind, and it took a lot of time to understand what this kind of motion was, and indeed, I had a look in some book of Cantoni, Lezioni di Fisica. I thought it was the right audience to show it. I didn't know till I began to prepare that talk. Cantoni had a very good intuition as physicist about the nature of that Brownian motion, which was only described in a right physical way by Einstein and everything we know about the description of the Brownian motion. So indeed, Cantoni, so I put the direct citation in Italian language and then the English, could identify that this motion of the pollen was the result of the collisions of the fluid in which this was. And what we will do is indeed look at this more precisely. There will be the donuts or the pollen as large sphere. We will think this as a sphere. And the fluid, we will describe it as an infinite number of very small particles, and we will look at the interaction between them. So what is this model exactly, this binary model? We have here the donuts, the black one, and these are the oil particles. So this is the most simple model introduced in the sense that the geometry is as simple as possible. The geometry is, we think that these donuts are really spherical, so it is very nice for all the symmetry it will induce, and also that these oil particles are spheres. And indeed, there will be an interaction between these, and this interaction will be as simple as possible, but not too simple to induce something new, interesting. So what will be indeed the interaction between the small one and the large one? The small one, they are very agitated, excited, so they will indeed, so the caricature of this model is they will not interact together. So an oil particle is not interacting with another one. They are just not feeling them. But they interact with the donuts in the following sense. The donuts are very hard, and they are not allowed to enter in the donuts. So the donuts are hard, and you have a well-known hard-sphere interaction. But how to do that? To modelize it, you cannot do it if the oil particles are infinitesimal. But then what does it mean? So this model from Asakura Ozawa is based on the fact that the particles in the medium, in the fluid, are very small, but nevertheless, they have a very small positive radius. So what does it mean that they cannot enter in the donut? It means that their center cannot be at a distance smaller than the big radius plus the small radius of the center of the donuts. So if you interpret this, you can you can design this, putting around the donuts a security zone, and the center of the oil particle cannot enter in that security zone. So indeed, now we have a set of parameters which is clear. First parameter, the big sphere with a big radius, the small sphere with a small radius, and the sum of these two radius. And this sum of the two radius will be called depletion radius. So it is infinitesimally larger than the large radius, but this infinitesimal will be exactly what will induce a new phenomena. So the small particle will move, we will see. They are not allowed to enter. So when they arrive at the security distance, what do? We can imagine there is a normal reflection, so they are reflected orthogonally to the direction where they arrived, and they continue. They don't see the other, but at some moment, perhaps they will see another donut, and so on. The donuts themselves, they are big spheres, they cannot enter naturally, so there is a natural hard sphere interaction and repulsion, but only between the dark, so donuts, they can touch, and when they touch, what you see is that their security zone are gluing in some sense, and this is exactly what will be of importance for us. So now, as I said before, I heard about that by Sabine Janssen and Dimitrios. They wrote and published several papers on that model. From the point of view of the statics, that is, they defined for this binary model a measure, and in particular, you can correct me if I say something wrong, what they discussed in Yerevan, it was a model B infinite. It means infinitely many small particles and infinitely many large particles, and on that, a Gibbs measure with all that interaction I described before, and then the trace of that bi-model to the a model with only large sphere, just forgetting that there are small particles in between, and the story we will see. So our point of view was to start from that model, but to introduce a dynamics for which the Gibbs measure they were studying is stationary. So this dynamics has then naturally two kind of unknown, the center of the donuts and the center of the particle. So because the effect, this depletion force, is interesting even if you have only two donuts, not infinitely many, but only two, it is interesting this phenomenon can be seen. We decided to restrict the number of donuts to a finite number, n, but you can also just think two donuts, they are moving, in this fluid of infinitely many small ones. So for us, up now, the system will be, for the big one, finite, for the small one, infinite, and interaction in between, and indeed, a motion. So let me now introduce some notation. The center of the donuts, we have n donuts. This is our fixed number. We have n center. We are in Rd. And to differentiate large and small, the large one, anything which is from a parameter related to the large one, to the donuts, has a circle on the top. And everything which is related to the fluid, to the small particle, has a point on the top. So we have X circles, so large donuts, and small one, fluid. So donuts will be, I hope, mainly red, and the fluid blue. So the system is completely described as soon as we know where are the donuts, the center of them, and where are the oil particles. And naturally, not any position is acceptable or admissible, but only the one respecting the geometry of the situation. The donuts have to be far away, the one from the other. So here we have 2R large, which is the radius of the donuts. And it is what I already spoke about. The small particle should stay at a security distance of the center of the big one, and this security distance is the sum of the two radius, and we call that air depth, air depletion. So just to put this in the framework of l'Aquila, we have here the donuts. This is the security region, and it means that this is the point with the center, a large center, xi, and any center of the small particle has to be outside this white zone. So now I introduce the dynamics which are interested in. Indeed, I said before the kind of interaction they have, and there is no smooth interaction. It is the simplest possible model. We have only hard sphere or hardcore interaction, hardcore between the big one and hardcore between the big and the small one. So the possible associated dynamics for that kind of interaction is Brownian motion for everybody, but under the condition that they do not overlap, because they don't have the right to overlap. And to avoid the overlapping between two donuts or with a particle, we have to use, in the framework of stochastic calculus, local time. The local time are these random processes we can add to the Brownian motion just to have a repulsive effect to the dynamics and to come back to the set of admissible position as soon as, for example, two donuts are touching, or as soon as an oil particle is coming too close to a donut. So this part here is, W is a Wiener process, is Brownian motion. Each donut is doing vibration, say, motion independently, each one from the other one. The same for the small oil particles. The coefficient is a variability of volatility in front of that Brownian motion is a priori much higher for the fluid than for the big one. And here, what you see, so I don't want to explain this too long time, but it is indeed a term with here n number of local time, so-called collision local time. They enter into the dance only at the moment here the oil particle K is touching the I donut, and so this random process will push away the oil particle in such a way that the position of them will stay admissible. So we have here a system of stochastic differential equation, which is a priori infinite. So we have n for the n donuts and infinitely many here. The existence of such solution is not trivial at all, because indeed we have as unknown a pair of each one of xi and the local time. There are local time for the collision between the donuts and for the collision between the big and the small spheres. So we have indeed a lot of unknown for which we should prove that a solution exists. Yes, certainly.
Maybe I missed this point. So the donuts and the oil interacts just due to the Brownian motion, or there is a force between them? No, they work around. Sometimes they meet, and then they are repulsed.
Exactly.
This is okay.
It is a unique. The unique interaction, and all the interactions are hardcore interaction.
Okay, due to this randomness, not
Exactly.
a force
So
between them.
just now, so here we see that the donuts cannot overlap. Here you see that donuts and oil cannot overlap, and that's all. But it is enough to create that kind of dynamics, which is not trivial. So, indeed, if we would have had a finite number of oil particles, we would have had a finite dimensional stochastic differential equation with a reflection at the border of some set, which is a set of admissible configuration. And this kind of problems is typically a score-out problem for which there exists a solution if the domain in which all that particles and donuts should stay is smooth enough. Unfortunately, in that situation, the domain is not smooth at all. There is a lot of corner and so on. So it is necessary to use to do a more precise study of the geometry of that domain of admissible positions, which are, if we have m oil particles, we have a vector with n donuts, m particles, and it is this random vector, a vector in Rd to the power n plus m. So geometrically, it is very difficult to understand which kind of form it has. And indeed, due to theoretical study, if we would have only finitely many oil particles, studies done by, in particular, the Japanese school in the 80s, end of the 80s, 86, 87, Saisho and Tanaka, could prove that under some geometric regularity of the domain, yes, there is a solution to the system I wrote, but when the system is finitely dimensioned, of finite dimension. So our job is to prove that we can go to the limit for an infinite number of oil particles and approximate the limit by finitely many such systems. So indeed now I would like to show some simulation of this bi-type system. So the simulations are done by this PhD student Juliet Kern, and we have 3 donuts and a lot of oil particles. So I think that you immediately recognize that there is a strange phenomena. These 2 large spheres, they seem to attract themselves, each other, and to like to stay close. They can touch, but they stay close. And the other one is not caring about. The other one is just moving its Brownian motion more or less independently of the rest. So indeed, what we see is exactly the phenomena we would like to modelize mathematically. It is, there is an attraction induced by the small particle to the large one. Okay, this is was not allowed. And this attraction is called this depletion attraction. And what could be a first physical explanation around, it was finished? Yes. Okay. So let me, can you let it just one moment, please? Can you let this, può lasciare l'immagine giusto un momento? Senza, ok. Dunque, there is this sea of small particles, and they are normally, take that. So the small particles are moving around, and there are so much that there is more or less, they push this big sphere in all directions, and the mean of that is just 0. But if two big spheres are close enough, you can imagine that around that, all that small particles are pushing in that direction, but there is nobody here because they are so close that no small particle can be between them. So there is the result, if you want, in terms of the vector, the sum of the vectors done by all these small particles around is in that direction. And here the same. All that small particles, they are pushing in that direction because there is a deficit of small particle in between. And so this dissymmetry induce indeed an attraction between the large one. So the large one have no attraction interaction at the beginning, so naturally, but this, it results, it is induced by the geometry of the system and indeed by the fact that the small ones are trying to, in a dissymmetric way, to push them together. So let us look mathematically what it means. Yes, please.
Is that something that you expect?
No, the third one is just as long as the center is not closer than the depletion radius to one other, this is just not feeling the motion of the other, and it is undergoing a Brownian motion. It could be, naturally it will be, so that at some moment it will be so close that it will feel the one. But
the two that are close together,
yes,
they don't move around. I mean, other than being
no,
close, they don't move.
They do, but indeed in this simulation, the space window is centered more or less around this motion.
So the scales in the axis.
Yeah, this is not natural.
It seems that it stays close to 0, 0, but are they significant?
It is,
or the center of the plot is where the two big spheres are.
Yeah, indeed, for convenience of the visual aspect, the center of mass was computed and there is a zoom on that. So for this reason, it is not a natural motion what you are looking, but it was just to see really what is going on.
Okay, thank you.
So, no, l'altro non ancora, per favore.
Allora dobbiamo ricondividere.
Perché?
Perché è condiviso.
Ok. Ma si chiude? Sì, va bene. Thanks. So now we are indeed in the situation where if we consider the full system with a binary model, we have the position of the center of the donuts, the center of the oil particles, and the measure I spoke about some minutes ago, which is a natural candidate to be the equilibrium, the reversible measure for the dynamics I introduced, is from the point of view of the donuts, the simple one, we need something which is stationary in space, so it is Lebesgue. This dx is just a product of Lebesgue for each donut. And then here, how do we put the small oil particles? Just a Poisson felt with this is the intensity of this Poisson. And what is not yet included in that is the fact that there is hardcore between donuts and oil, and this appears here in this way. So there is a plus because we consider the center not as a vector but as a point measure. So we have a point measure for the donuts, a point measure for the oil, and we do the sum of the point measure, and this should be admissible. D is the set of admissible positions. So we have indeed typically a hard-cut Gibbs measure with an indicator of admissible position, and then Poisson. Here we don't have a double Poisson, we have Poisson times Lebesgue because we have only finitely many donuts. So this measure is a good candidate to be reversible for the dynamics. And now, recall, we are not really interested by the oil particles. We would like not only to look at what is the motion of the donuts. So what is interesting is the trace of that measure just on the center of the large sphere. Then, once we will have that, we will look at dynamics having that trace as equilibrium measure. And then the last question we would like just to speak a little about is increase the density Z of the oil. So a lot of oil particles, so you remember the simulation, so much that indeed the donuts are no more free, so they are really disturbed by this large density. So what do that donuts do? And this will be at that point interesting because we will have a question related to optimization of configuration, and not densest, but you will see it will have some relation with the contact number problem and some problem of discrete geometry. But first, how to express this depletion interaction as we have seen it in the simulation. Indeed, starting from the reversible measure, the equilibrium measure for the B-type model, doing the integration with respect to the small particles, what comes out is for the large one, so for say 3 donuts, if n is equal to 3, you have here Lebesgue measure, just it remains Lebesgue. They have to be compatible, so they cannot overlap, and then appear in the projection density, which has an exponential form, exponential minus z, which is the density of the small one, times the volume of the union of the balls. The union of what? Of these balls with the security zone because the radius which appears there is the radius, depletion radius. So you see a measure with a density e to the minus something. This measure will carry the configuration with this term, when this term has its minimum, so we would like to have the minimum, the configuration for which this volume is minimal. This volume is the volume of the union. So here you have a typical situation. The internal big sphere, the donuts, don't overlap. Here they just meet, they touch, but they don't overlap. But the security zone overlap. And the security zone, they overlap here, here, and here. So how to have the minimum volume for the union? We have the union here, chuk, chuk, chuk. The minimum volume is when this intersection is maximal, to have all this as compact as possible. And how they can, it can be minimal. So when this is maximal, and it means that really they just touch, and then we have this beautiful geometry for the intersection. This is in dimension 2. In dimension 3, you would have naturally some volume. And when this is maximal, we have configuration of donuts with highest probability. So indeed, suppose that the small radius, this security zone, is really much smaller than the big radius. And in that situation, you cannot have intersection of three such spheres together, only 2 by 2. So it means that the induced interaction between the donuts is a pair interaction. These two are interacting because of this surface. These two are interacting due to this surface, and these two are interacting also. So arithmetically, the volume of the union is equal to the sum of the volume, it is this term, minus the volume of the intersection, and the volume of intersection depends directly on the distance between the center. And it is now modelized by this function of the distance between the center, and this function is the so-called interaction function, depletion interaction function, depletion interaction. We will see in the next slide that it has a nice form. Let me just do 2 remarks at this moment. This function phi is negative, so from statistical mechanics it means it is an attraction. We have seen it was an attraction, definitely. And indeed here you have the parameter z, which is including that interaction in a multiplicative way. So it is proportional to the density of the small oil particle around. It is directly proportional. So when we will increase this density in the medium, it will increase proportionally. So let me show you. So all this was well known. It is nothing new. In dimension 3, you have an explicit expression for this interaction. So the interaction U is the distance between 2 centers. It is a polynomial of 3rd order. In dimension 2, what we can see here, it is a little more complicated because it is an arc cosinus, and here there is a square root. At the end, if the small radius is very small, we can approximate by power 3/2 of the distance between the center. And here once more you see the surface which has to be computed to obtain indeed this interaction. So now let us go once more to the back to the one dynamics which has this measure with this induced interaction, with this depletion interaction as reversible measure. Now we have to add some term, which is a gradient term, gradient of this interaction, depletion interaction, and this is indeed the dynamic which could see. We have the simulation, but I don't have so much time, so I will not show it. To understand better what is the motion of the big sphere if we just forget that they are in a sea of small one. So let me say some words about this asymptotical behavior if the density of the small one tends to infinity. What you can see here is that the reversible measure for the donuts has this form, exponential z, and this sum on all pairs of donuts of this function with a power function. So, which kind of configuration will be the most probable if we are increasing z? If we increase z, we are looking for this term, to maximize this term, the sum. And what we have seen before is that this interaction, indeed, between the donuts, this depletion interaction, is a very short interaction, short range interaction, because it comes on only when the donuts are very close, as we have seen before in the simulation. So here, when can this be optimal? When the pairs are as close as possible, all the pairs, as much pairs as possible. And then we have here something which is indeed maximum when this is minimal. So what are we looking for? If we have 3 donuts, we look at the position in which they are pairwise colliding. And if we have 4 donuts, we look at the position when 4 are colliding pairwise as much as possible. So let's show me you. So here we have 4 donuts. How much pairs are just colliding? 1, 2, 3, 4, 5. So this is a maximal contact number between 4 spheres. Here we have 1, 2, 3, 4, not 5. So this is not optimal as position. This also not, this also not, and this, once more, it is not the same pair. Now this pair is touching here, it was this one, but the contact number is the same, is 5. It is the optimal number for 4 donuts. If you have 5, 6, 7, the optimal, so the maximal contact number can be computed, and indeed the best configuration is the Margaret configuration truncated. So this is for 7. Now take 1 away, it is 6. Takes 1 away, it is 5. So this is now the best contact number. You have 1, 2, 3, 4, 5, and this is touching also this one. So this kind of configuration are exactly what is done with the highest probability if you have a density for the small particles around which explodes, and indeed Please, could you show the simulation as last? There is one more simulation when we see how they glue together as clusters, and these clusters have a very specific form, and it is indeed for 2 or for 3. So let me begin, and then we push the dynamics after 1 minute, and then after 2 minutes, and we see. And I will conclude with that. Please, can you go to 1 minute? So you see, as soon as 2 are together, there remains the time that the third one is arriving. Here, the 3 are looking to take that position, the best one. And in some times, here we will have a cluster with 4, and they are looking for the best position as 4, and it is what we have seen before, not as a square, but the other position you see is here. This is naturally not completely stable, but now they are really in the best position, and there is a small motion around. And naturally, all these finite clusters are sometimes separated, but they can go together if we are if we have a long time, we can see that at the end there will be the best cluster of all these 4 plus 2, 6, and then 8 or 14 big particles together. So thank you very much. Can I come back to my slides, please? Yes. Okay, thank you. So this is not what I wanted to do, but okay. So let me close the mathematical part of my talk now. So this was just a flavor of what could be done in that direction. I think, as you can imagine, this is a simple model geometrically, and also with no specific interaction between the particles. Each kind of generalization could be studied, and I think it is only the beginning of some connection between statics, dynamics, and then asymptotical properties connected with discrete geometry and problem of optimization of configurations. Thank you very much.
Okay, thank you very much, Sylvie. Are there any questions? Yes.
Yes, thank you, Sylvie. About the scaling, so you showed the existence result based on this Japanese author's previous result. So I wanted to ask you the following. So if you define the same thing in a finite volume, and you have a number of big, a number of small with those radius, And can you pass to the infinite volume taking the density fixed or something like that? Would the existence of the system be valid?
Certainly, the system indeed is the same one, but you have to put some boundary conditions. So if you think at a finite volume,
periodic, whatever you like.
Yes, indeed, if you are taking a reflection on the border, the problem when you let the volume tends to infinity is always to prove that it converges to a dynamics without that reflection at the border. So normally it is not so simple with hardcore at the border, so you have to smooth the border,
Yes.
and then you have one parameter more, and you have to exchange limits. So it is technically complicated, but so heuristically it is natural to do that. But the problem is to exchange the infinite, so the limit in the number of spheres with the limit in the reflection you have at the board. So these both parameters.
So there will be a condition on the density, right? So the density should be smaller than something. Is that?
Yes, naturally the density should be something related to Poisson, so not it does not have the right to explode.
Okay, there is another question.
Hi, so thank you for the talk. So you have a Brownian motion both in the dynamics, both for the macroscopic and for the microscopic, right? But also, let's say, in relation to the first quote by the Italian physicist, one would expect the Brownian motion for the macroscopic particle to emerge as from the collisions of the microscopic particles. So I was wondering, is there a reason why you put also some noise for the macroscopic particles?
For the big one, no?
Yeah, for the big one, yeah.
Indeed, this noise of the big one was what was historically observed by Brown, that the big one were moving in a small manner, but they were moving like a Brownian motion with our words today. And the motion of the small one was not observed because it could not be observed because of the at that time there was no way to observe that so microscopically. But indeed, it is the same story. They observed the trace of the motion of the small one. Both had a vibration, but with different scales, and the trace remained random. So this is my personal interpretation. I am not a physicist. I could not be completely sure, but it is what I would.
So how would the results change if you would set like the variance to sigma to 0 for the big particles?
In the big particles?
Yeah.
If you put, so indeed, look, for example, this problem which appears to the best position, it could be reached only if you have this mobility, this flexibility. So the Brownian motion, this motion of the large one is the one you need if you want to go towards optimality.
Okay, thank you.
Okay, let us thank Sylvie and all the speakers of the afternoon again. Do you want?
Yes, I would like.
I don't know because we have some glimpse
with some words and some photos for Paolo, just to remember together some very nice moment. And indeed, I will do so. I apologize, but now I have to speak in Italian. It is more simple for me. So, infatti, ora vi mostro giusto 4-5 foto andando indietro nel tempo. E l'ultima occasione bella che abbiamo avuto di incontrarci, però sfortunatamente solamente online, era la difesa di Alexander, che è qua davanti alla lavagna, la difesa della tesi. E dunque eravamo, Paolo era nella commissione e si è fatta l'anno scorso a Potsdam, sì, con grande emozione perché dunque era il risultato di 4 anni di lavoro e Alexander aveva fatto la tesi di master con Paolo. Una situazione di prima era con Giovanni, dunque sfortunatamente la difesa stessa, non ho più trovato le foto neanche Giovanni, ma dopodiché Giovanni ha avuto un premio della tesi migliore in matematica in quell'anno e dunque c'è stata una cerimonia molto prestigiosa davanti alla colonnata del castello di Potsdam e questa è la foto. Vorrei ricordare questo convegno che abbiamo fatto a Levico Terme, infatti a quel momento il mio gruppo di probabilità faceva parte di un graduate school che era a Potsdam Berlino e avevo detto che noi potremmo organizzare la summer school in Italia e Paolo è stato di una gentilezza e di una effettività grandiosa e ha organizzato in una maniera veramente bella a Levico Terme questa graduate school dove là c'è un sacco di gente che veniva da Berlino e da Potsdam e alcuni italiani, è stato un momento estremamente simpatico. E facciamo un salto nel tempo indietro e ci ritroviamo nel 2006 con facce che voi riconoscete. Dunque, infatti era una visita di lavoro e abbiamo fatto una gita con la bicicletta per vedere questa casetta che dunque non siamo all'Aquila, è attorno al lago di Potsdam e è davvero la casa d'estate dove Einstein è stato. Einstein ha lavorato dal 2000.
Perché ho pensato che lì magari gli sono venute le idee migliori.
Comunque,
no, mi ricordo di questa cosa perché ho detto voglio vedere il bagno, perché qui chissà che cosa è uscito da questo bagno. Scusate.
Einstein ha abitato a Berlino dal 1918 al 1933-32 e è stato attirato dal governo per dirigere un gruppo di fisica e gli hanno detto che gli avrebbero costruito una casa per il fine settimana e l'estate dove voleva, solo che ha aspettato anni, non è venuto niente, dunque alla fine si è cercato lui stesso un pezzo di terreno al lato dal lago perché lui amava fare la barca a vela e ha costruito una casa di cui lui stesso ha fatto i piani, tutto in legno, tutto concepito in un modo estremamente moderno, incredibile e dopo la riunificazione delle due Germanie hanno ritrasformato la casa che nel frattempo aveva avuto tanti usi e ora è un luogo di riunione per scientifici e dunque ho potuto anche organizzare qualche incontro là, ma in questa gita noi siamo arrivati, abbiamo visto la casa e abbiamo dunque potuto goderci anche il giardino molto bello da dove si vede il lago e tutto il panorama. E dunque torniamo alla difesa di Pierre-Yves nel 2002, che infatti è stato a Lille a quel momento, dunque Paolo era a Milano, io ero a Lille qualche anno prima, e infatti quando Paolo ha fatto il suo cammino aleatorio entro Milano, Padova, Verona, io nel frattempo facevo un altro cammino che era Lille, Parigi, Berlino, Potsdam, e ci sono state delle interazioni a pari più o meno tutto il tempo. E dunque così, una volta di più, vedete facce sorridenti che siamo stati felici di accompagnare nel loro